Very good morning to all of you. Today we are in the third day of the PDC session. The first talk will be given by Dr. Samuel Bernard, whom I know for a very long time. I'm replacing Thomas Fisher as the session chair since he's on his way, and in order to make sure that we start on time, I'll be acting as the chair for the session. The first talk will be given by Dr. Samuel Bernard. He's from the Institute of Research for Ceramics, CNRS, University of Limoges. And over to you, Samuel.
Thank you, Ravi. Good morning. Guten Morgen. So as you mentioned, my name is Samuel Bernard, coming from the Institute of Research for Ceramics in Limoges, as I say, the French city of fine porcelain. And I'm delighted to give a talk dedicated to polymer-derived ceramics. And first of all, I would like to thank Ravi and Günther for inviting me. I was here for the first time 10 years ago, so this is my second time. And of course, I traveled more in Brazil, but I will try to come more in India in the future, okay? And today, I would like to speak about from precursor synthesis to functional materials, especially used as catalyst, at the core of energy storage and conversion devices and electrode design. Oh. Oh, I have no pocket, maybe. So I guess it's better. Okay. So here are all the co-authors of my talk, all the PhD students and postdoc fellows, as well as some of my colleagues working on PDCs going from experimental to modeling. My talk will be shared into three parts. In the first part, as an introduction, I will speak about Limoges porcelain and polymer-derived ceramics, and I will give you a short introduction about our Institute of Research for Ceramics. Then I will go through science, and I will speak about transition metal-based catalysts in the context of energy storage and conversion, especially in the context of hydrogen release. Especially, we will use such polymer-derived ceramics route to design high-specific surface area silicon carboxynitride-based compound, immobilized nickel nanocatalyst for electrocatalytic water oxidation. Then I will finish by some conclusions and future prospects. So, as probably you know, ceramics have been discovered in southern China about 20,000 years ago, and then its production use extended over the world through Europe, and to finish in France, especially in Limoges, around 250 years ago, because in the south of Limoges, in the city called Saint-Triège-la-Perche, we have discovered this white precursor, you know, which is called kaolin, which is one of the compound to prepare porcelain. And because of this discovery close to Limoges 250 years ago, the production of, we say, hard Limoges porcelain started in 1771 and was developed in 1773. Then, so the production started and continued progressively. So I should mention that porcelain starts with precursors made of kaolin, as I mentioned, which gives the whiteness to the porcelain, with clay to allow vitrification of our materials, and we add also quartz to offer hardness to the materials. Then you form a barbotin, as we say. You add some compound inside to keep the fluidity of your materials. Then you have a shaping process, and you finish by a two-step fire in order to then some finishing, and you produce your porcelain. Nowadays, we have around, I would say, 30 industries producing porcelain from these three precursors, but kaolin, the production of kaolin stopped in Limoges. Now we have kaolin from other countries like New Zealand, Germany, but also some other parts in France. And in Limoges, we have around 1,200 employees working to produce porcelain. There is a strong link between traditional ceramics and advanced ceramics and also polymer-derived ceramics, which have been started around 50 years ago in Limoges, especially starting from the creation of a research laboratory dealing with nitride compounds in 1975, as you can see here, and this laboratory belonged to CNRS and the University of Limoges. Then, later in the 80s and 90s, nitrides met polymer-derived ceramics, especially through the nice work of Professor Paul Goursat. Paul Goursat developed polysilazane chemistry, in particular in collaboration with Professor Corioux from Montpellier. And so the activity dedicated to PDC was, I would say, quite high level in France in the 80s and 90s, especially in three places in France: Montpellier with Professor Corioux, Bordeaux with Professor Nalin and Professor Dunoguez, and finally Limoges with Professor Goursat. Then, in 2010, I would say the mayor of Limoges started to develop a sort of ecosystem in the north part of Limoges, which was fully devoted to ceramic production, going from school and finishes to industries via the European Ceramic Center. So it was around 2010. Then later, CNRS took the decision to develop the PDC's activity in Limoges. It was in 2016. Then I integrated our laboratory in 2017 from Montpellier. And our Institute of Research for Ceramics, was created in 2018. So nowadays, we are around 200 people working for processing, I will describe later, and we have a strong connection with academic, but also a strong connection with industrial partners. Here are our campus. This is our institute here, with the engineering school fully dedicated to ceramic production, and some startup here that develop product coming directly from our institute. Since, I would say, 10 years, we were able to create more than 15 startups from our research and development. Some words about our institute. We are around 225 staff, around 150 permanent staff. We develop our research through 4 departments: ceramic processing, plasma and laser processing, structural organization, and multi-scale characterization of materials, and the last one dedicated to ceramics developed under environmental constraints. And our main objective is the transformation of matter involved in processes of bulk ceramics and processing used in surface treatment. Our institute is closely linked to our characterization platform. We have, I would say, almost everything to analyze your materials at different length scale, except solid-state NMR, for instance, but we have a strong collaboration with Paris, especially with Professor Christelle Gervais. And our activity dedicated to polymer-derived ceramics is involved in these 4 departments. In particular, we have a strong expertise in the design of nitride and carbide materials, but we start to develop other systems prepared from preceramic polymers. The majority of these materials, I mean ceramics derived from preceramic polymers, are direct application for transportation, especially fibers and matrices. So I cannot speak today about these matters because we are mainly industrial partnerships. And of course, you can understand that some information are confidential. But today, I will speak about the application of polymer-derived ceramics for energy. Especially, I will speak about porous nanocomposite, which means that we can generate in situ nickel nanoparticles in a PDC matrix. Here are some applications in energy we target. So let's move to science now. The interest of transitional metals stems generally from their partially filled d orbital that allows to provide several or variable oxidation states, which is very interesting for homogeneous catalysis, but also they have a strong ability to form complex intermediate with reagents via temporary bonds that can be offered because of they use their 4s and 3d electrons. Therefore, they are very interesting for heterogeneous catalysis. Especially such materials are highly interested in the context of hydrogen, especially the hydrogen production from lightweight inorganic hydrides, such as sodium borohydride, but also from water by electrocatalysis, and this will be the topic of my talk today. Especially the first row of transition metals, I mean non-noble transition metals such as cobalt, nickel, iron, are very interesting for these applications because their hydroxy or oxide counterparts are stable in alkaline media, which are generally used for such reactions. Transition metals as nanoparticles, because it's better to use nanoparticles for catalysis, can be prepared via top-down or bottom-up approach. And as bottom-up approach, there is a strong interest in the in-situ growth methods because you can prepare in one step the support and the catalyst as nanoparticles. And one of the most interesting in-situ growth method is the polymer-derived ceramic route. So I will go through details on this route. So here is the process. So I think you know very well the process now. Just a few words about our work on PDCs. We mainly use polysilazane as a preceramic polymer, and these polysilazanes are used to generate, I would say, ceramics in the silicon carboxynitride system. Polysilazanes are very interesting because they are highly reactive towards transition metal complex to prepare inorganic materials. I mean, inorganic because you can generate metal nanoparticles, which are distributed in a silicon carboxynitride matrix, but you can also prepare metal linked to a p-block element, such as carbon, oxygen, nitrogen, and silicon, which are distributed homogeneously in a silicon carboxynitride matrix. And such inorganic materials, I would say nanocomposites, are very interesting for sustainable application to be used as a self-supported catalyst. Here are some typical examples of the generation of non-noble transitional metal nanoparticles in a silicon carboxynitride matrix, starting from the work of Dr. Günther Motz more than 15 years ago. And you can see that a lot of people attending this conference are involved in these papers. And particularly, I will speak about this last paper we recently published in Nanoscale Advances in collaboration with Günther, but also in collaboration with Professor Yuji Iwamoto that is expected to come today. And especially, I will speak about the immobilization of nickel nanoparticles in a high-specific surface area silicon carboxynitride matrix for electrocatalytic water oxidation. So let's speak about our work. As probably you may know, water can be split into dihydrogen and dioxygen by electrocatalysis. And one of the means to perform this reaction is to use alkaline electrolysis cell, because this is the most mature technology which exists. Alkaline electrolysis cell is composed of 2 electrodes, a cathode to release hydrogen, and an anode to release oxygen. And this system is very interesting because you can use non-double transition metals because their oxide counterparts are stable in alkaline media. So the catalyst is the oxide transition metal. So it means that our transition metal is a sort of pre-catalyst, okay? There are several issues relating to this reaction. I mean, the release of oxygen. First of all, the thermodynamic potential for water oxidation is relatively high, 1.23 volt versus a reversible hydrogen electrode. And the sluggish kinetic of this reaction impose high energy to overcome the activation barrier and to trigger the reaction by electricity. Therefore, you have what we call an overpotential because you provide a higher energy than this thermodynamic potential. And one way to decrease this overpotential and to be closer to this potential is to use catalyst, especially catalyst based on non-double transition metals. Here is our process. We start with this well-known polysilazane, Durazane 1800. Why we use this? Because after pyrolysis, it is well known to form silicon carbon nitride ceramics with free carbon inside. And you need to have a conductive materials to be applied for this reaction. Therefore, we use this polymer and not PHPS, for instance, because PHPS has no carbon. We use nickel chloride because nickel is one of the most interesting transition metals to be used for oxygen evolution reaction by electrocatalysis. And so we perform the reaction at DMF reflux overnight, and we form, after the process, a solid polymer in which nickel coordinated silylamino ligands, which are present in the polysilazanes, but also siloxane ligands because of the reaction of DMF with Durazane at reflux of DMF and in the presence of nickel. I should mention that we use this silicon-nickel ratio of 2.5 just to have at the end of our process around 48% of nickel in our materials to be active for the reaction. Once the polymer is prepared, we perform the pyrolysis at relatively low temperature, 500 degrees C, under argon atmosphere to generate these nickel nanoparticles in a silicon carboxy nitride matrix. So why such a low temperature? Just because we know that the specific surface area of the materials evolve during the pyrolysis, and you reach a maximum around 500, 600 degrees C. Also, we observed by TGA that the conversion of our polymers is almost achieved at this temperature of 500 degrees C. So you can see that we don't have any chlorine element at the end of our process, but we have still hydrogen residue because our materials is not fully converted into an inorganic materials. And you can see that the relatively high carbon content in our materials. We have a strong excess of carbon because we use nickel chloride and we remove during the pyrolysis chlorosilane. Therefore, we form a carbon-rich materials which was targeted for our application. We analyze our materials by XRD after the pyrolysis at 500 degrees C. As you can see here, we have mainly cubic nickel, but you can see here relatively broad XRG peak relating to the formation of this metastable hexagonal nickel phase, which has been identified during the conversion of nickel carbide into cubic nickel at a high temperature. And this hexagonal nickel phase is well known to be highly active for oxygen evolution reactions. By Rietveld refinement, we were able to calculate the content of this phase, around 85% of cubic phase and 15% of hexagonal phase in our materials. TEM confirm XRD results, especially this selected area electron deflection is consistent with XRD results, cubic and hexagonal phase. And as you can see here, there are two series of particle size. The biggest one, around 50, 70 nanometers, made of cubic nickel. But these biggest nanoparticles are systematically recovered by carbon layers. The smallest one, around 10 nanometers, only made of hexagonal phase and without carbon layer around the particles. Then we finish the characterization by BET, and as you can see, because we stopped the pyrolysis at 500 degrees C, we were able to develop a relatively high specific surface area, close to 310 square meter per gram, with a relatively high content of microporosity. And based on this profile, we can confirm that our materials is made of aggregated particles which develop, as you can see here, a slide-shaped pores and mainly micro and mesopore. So therefore, I would say that we have almost all requirement to apply such materials for oxygen evolution reaction. We have nickel in two phases, cubic and hexagonal one, and we were able to develop the specific surface area of our matrix. Therefore, we expect that the nickel nanoparticles are accessible for the reaction. So we apply these materials for electrocatalytic water oxidation in collaboration with our partner in Poitiers, which are expert in electrocatalysis. Okay, I'm not an expert in electrocatalysis, but I will try to be clear. Here are the results. Especially, you can see here that the colorimetry associated with the Ne2 plus, Ne3 plus oxidation wave increase, which means that there is a surface reconstruction of our nickel nanoparticles. This means that nickel nanoparticles are accessible. This was our first objective. And here, upon electrochemical cycling, you can see that the oxygen evolution reaction activity increase. And after 200 cycles, we were able to have a potential of 1.59 volt versus reversible hydrogen electron to provide a current of 10 milliampere per square centimeter, which means that our activity increase with cycle. This means that the nickel nanoparticles are more and more accessible upon electrochemical cycling. And we suggested that the carbon layer, which are around the biggest nickel nanoparticles made of the cubic phase, was removed because we are in an alkaline media, and therefore the nickel nanoparticles are more and more accessible. This is why the activity increase upon cycling. This result is very interesting because we have a potential as low as 0.36 volt, which is very, very low and highly promising because we have only 0.15 milligrams per square centimeter of nickel in our materials. So now let's move to the conclusions. So there are a lot of talks dedicated to transition metal containing PDC in this workshop. And I hope I convince you with the interest of these materials for electrocatalysis. So there are a lot of work to be done, especially to mix several metals in order to develop the catalytic activity. And one way is also to go to the electrode design. Especially, we are working on the extrusion of these materials to prepare this 3D electrode for the oxygen evolution reaction. Maybe I can show you an example. I hope that the video will work. Here are our process accelerated by 100 times. So this is our catalyst with a special preceramic polymer. So this is the raw materials. So this is in a glove box. So this is our final materials. Then after we have the pyrolysis, and we just have a volume shrinkage of 35%. Therefore, we can keep the shape of our materials, and such materials can be used as electrodes. This is under investigation, and we hope that we can have very nice results on these materials. So I would like to finish my talk. How can I put full screen? Oh, thank you. So I would like to thank all our team in Limoges working on this polymer-derived ceramics. And before finishing, I would like to give you some announcements, especially this special issue dedicated to polymer-derived ceramics, in which Günther and Ravi are involved. So deadline is relatively close, but if you would want to submit a paper in this topic, we can discuss to extend this deadline. And a final announcement about this HIWAC conference, International Workshop on Advanced Ceramics, which will be held in Limoges at the end of September. So please do not hesitate to be in touch with me to submit an abstract, and I will be very happy to welcome you in Limoges and to enjoy the life. Thank you very much for your kind attention.
Thank you very much, Samuel, for the excellent presentation. We have time only for one question. Yeah. Yes, please.
Thank you. It's very interesting work. I mean, it's quite similar what we are doing also. So I just have a question about, first, a simple question, how much nickel it was in the material, because it seems like too much nickel.
We have
the weight ratio of the nickel in the silicon oxycarbide in the final product.
We have around 40 weight percent of nickel.
40
exactly 43 weight percent. This was the maximum to be introduced.
Okay. And because we do some similar work, and we always see this when we have a cubic nickel carbide, cubic nickel, we see this carbon layer is surrounding this.
Yeah.
And we have several work showing that the carbon or nickel catalyze this carbon formation, like the carbon diffuse inside the nickel and then segregated to the surface, which you have observed also. Have you tried to compare the lattice parameter of your nickel FCC with metallic nickel in the literature? Most probably, maybe you have nickel still inside the lattice. Have you compare the lattice parameter, or we do EDX mapping in the nickel carbide, in the nickel to see if it's carbide or pure nickel?
No. So, but what I can mention is that the pyrolysis is at 500 degrees C. And we observe that at 300 degrees C, just below this temperature, we form nickel carbide. And probably nickel carbide is decomposed at higher temperature to form nickel, cubic nickel with this carbon layer around. And this carbon layer is kept until 700 degrees C because we didn't work above this temperature. And we are trying also to use carbon-free preceramic polymers. And with carbon-free preceramic polymers, we don't form this hexagonal face of nickel. I don't know if I answered to your question, but
You answer my question. Maybe we can discuss this later because this is also interesting for us. We have
Yeah?
several things we can work together.
okay.
Thank you.
You're welcome.
Yeah, I think in the interest of time, we will go to the next speaker. I
Thank
will
you.
hand over it to Thomas, who will continue from here.
Thank you, sir. Sir, I request Dr. Ravi Kumar to present the memento to Dr. Samuel.
Yeah, thank you, Ravi, also for taking over, stepping in for me. I'm still having to try to grasp the Indian traffic in the morning. Sorry for being late for that. But without further ado, I would like to introduce the next speaker, who will be Suresh Kumar, who is working in Kanpur at the DMS RDE. And he will give a presentation on development of process technologies for continuous silicon carbide fibers and silicon carbide composites. So, Suresh, we're looking forward for your invited presentation. Thank you.
Thank you, Session Chairman, for nice introduction. So, actually, I joined yesterday only, so I was not knowing that how many presentations of this kind have been. So, I just quickly go through that abstracts. So, fortunately, there were not many presentations on this topic, except that one or two who have talked about this composites. So, as Session Chairman, I am a scientist at DRDO, Ministry of Defense, and then we are working on polycarbonylane based the silicon carbide fibers as well as making composites. So that my whole presentation will revolve around this particular diagram, where actually the conversion of polydimethylsilane is converted to polycarbonylane, and this polycarbonylane in turn is used for making silicon carbide fibers as well as making the composites. So just for completeness of the presentation, so if we go through the material chart for the high temperature applications, so these are the temperature, this is the strength. So we find the polymers which are very, very high strength, but they're very low temperature use, and that some superalloys as well as for ceramics, they can go for high temperature as well as reasonable good strength. So if we find that silicon carbide, silicon nitride, alumina, so they all are at this peak. So this shows this material can be used for high temperature as well as they have the good strength also. So once we go for this temperature versus that temperature as well as strength. So the metals, they deteriorate for their strength as we increase the temperature, but the ceramics, if we see the carbon-carbon composites or carbon silicon carbide or silicon carbide, they retain their strength very, very high at high temperature also. But from this also it is not very clear, because that temperature alone will not define that whether this material can be used for that other applications or not. So then it comes to the time. So that what time we want to use this material. So if for the shorter applications, shorter duration time, let's say that few seconds or maybe 1 or 2 minutes, like for the missiles, we can use the carbon-carbon or carbon silicon carbide, which retains with their strength at high temperature. But for the longer durations where the oxidative environment is there, for example, for this, engine applications or the aeronautical propulsion, so that the time is very, very long, and that oxidation environment, so this material cannot be used. So then it will be only silicon carbide. So once it go for that high temperature application for the longer duration under oxidizing environment, then we can find there are many reinforcement. If you see, so the different type of reinforcements are there, starting with the different grades of silicon carbide fibers. We start with the nickelon, high nickelon, then Tyrano, ceramic, and the other grades of silicon carbide. Then the oxide fibers like Nextel and other fibers, and then carbon fiber, of course, they are there, and apart from some whiskers and particulate. So by that this total focus will be for this range. So from these two slides that I could explain that importance of the silicon carbide fiber. So when we see that this if is that much important, what are the other different applications? So the first is the jet engines. The jet engines, as I said, there's a different combustor, turbine engine, turbine blades, shroud segments. Aerospace, the different, this liquid propulsion engines, and then thermal protection system, propulsion, and the power. This is actually again is a very this is a great use for the silicon carbide fiber. So this is again actually in the different form of that earlier this graph. So what we can say, the silicon carbide fiber technology, this offers at least about 200 degrees Celsius more than the superalloys of the nickel-based superalloys at 1/3 density. And because of this reason, when it offers a higher combustion temperature, the lower density, the fuel efficiency goes more than 6%. So and there are definitely there are the different advantage or that superalloys for the carbon-carbon, oxide-oxide ceramics. So what is the process which are involved for the making of silicon carbide fibers? Though that we say the silicon carbide composites are very much important and they enhance that temperature, usable temperature as well as the efficiency. So apart from the making of the precursor, which I will be talking in the subsequent slides, so the spinning of the polycarbosilane, that we have to convert that material, the polycarbosilane into the fiber, followed by its stabilization, mostly it is done under air, then pyrolysis, mostly it is done under argon, and then weaving into that cloth, then making the composite, testing, and then component. So it's a tremendous amount of this research efforts are required in order to reach to the component fabrication. So these are the classification is generally actually just for that again that most of you might be knowing this one. So this is the generation 1. The generation 1 of silicon carbide fibers are made by using the polycarbosilane, where the stabilization is done mostly by air, and where that oxygen content in the silicon carbide fiber of the order of 10 to 15%. Here actually that excess carbon is there, and the silicon carbide, of course, the nanocrystalline size is slightly low. Then high nickelon, which is mostly actually made by this Nippon Carbon and Ube industry, where with that EB curing method, here the oxygen is reduced, but the carbon content is still high. In the third generation, where the extra carbon as well as the oxygen is removed mostly, and that is a totally silicon carbide fiber, and this kind of fiber only can be used up to 1500 Celsius use. So that our focus is for that making of this grade of fiber, just to understand and then to establish entire process know-how, and then finally moving to this one. So the first thing is that what the work actually we have done at DMSRD. So the conversion of dichlorodimethyl into the polydimethyl. This is the precursor for making the this polycarbosilane, and there are a lot of criticalities. Though the reaction looks quite simple, is the simple Woods coupling reaction, where the chlorosilanes are reactive with sodium, but that you know that handling of the sodium in the large quantities and then handling of the chlorine base this precursor is very difficult. So that we have established the process for 2 kg making of this particular grade of PDMS, and then we are now that scaling up to 5 kg batch. So these are the typical process conditions, and this is the where actually that the silicon to silicon bonds comes with this FTR. So then conversion of the polydimethylsilane in turns to polydimethylsilane. This PDMS is a non-meltable, non-soluble, and we cannot use as such this PDMS for any purpose. So we have to convert it into a soluble, meltable, the polymer called polycarbosilane, and this is done at atmospheric conditions. And then we have established the process for about 5 kg synthesis each batch. And then the two different actually processes we have established for making of the fiber as well as for the composites. And this is this particular curves convert to that where that SiH, and this is this peak, which signifies the polycarbosilane, and this only provides the flexibility as well as the meltable feature of the polycarbosilane. So now for that conversion of the polycarbosilane into the fiber is not that straightforward, though it looks when we read that any textbook or the paper, it looks quite simple. So this is this information I have taken from this published literature, published literature. So this is the typical molecular dispersion, molecular weight dispersion, And the importance is the viscosity. So the viscosity should go as low as about 10 Pascal second, and it should remain stable for that spinning temperature. So this is the condition. And then after the repeatable heating, cooling, that also that not much significant change should happen. Otherwise it will affect the this fiber diameter. So if we see the spinning point of view, the PDI should be low as possible, viscosity should be low as possible, thermal stability should be high as possible. But when it comes for the stabilization, the softening point should be higher as high as possible. So this is contradicting. When the viscosity is low, so you cannot have that high softening point. Then this also that it's a defect-free fibers, it is essential. Then pyrolysis point of view, the ceramic yield should be very high because that we should have the low shrinkage. But if you have the ceramic yield high, means that higher cross-linking, and the higher cross-linking means that the softening point will be high and that your viscosity will not be low. So there are so many contradictory requirements are there for making the fibers. But finally, we have made that this polycarbosilane, which is having a required polydispersive index as well as a stable viscosity for more than about 1 hour. Then it comes for the spinning. The spinning again is the key for making of the fibers, and that any defects are generated at this end, you cannot overcome them, and ultimately that your fibers will be very weak. So there are the different parameters with reference to the PCS parameters. It's the melt temperature, the molecular weight, and the PDI, the viscosity, the gel content. They are very important. Then the machine parameters also equally important. We cannot ignore them. If by machine parameter, we can have that good fiber as well as that bad fibers also. The spin rate, pressure, the nozzle diameter, nozzle length, winding drum. So there are so many. So that all these things to be carefully studied and have to finalize that what should be the range for the operation. So this is that typical scheme that I would like to show. Here that PCS is fed and then it to be melted and then pressure to be applied, either pneumatic or hydraulic. And then below this one, the winding drum should be will be there. So this is the screenshot of that what the winding we have done. So this is the flow rate, and flow rate depends on that so many these parameters as I explained. And that ultimately we are interested that what should be the pressure for given diameter. So that the given diameter, if is this PCS is the PCS nature also. Ultimately, if it's a shear thinning type, you have a different property. If you are shear the Newtonian type, you are different. So that we have modeled this one, and then for the given pressure, we can see that we can effectively control that what is the flow rate and the diameter of the fiber. And using this one, we have made the fibers, and this is the typical the screenshot of that one. So then again that we have done several combination studies that what should be the temperature, what should be the diameter, what should be the pressure. All those mean ultimately to find out that what should be the fiber diameter for a given pressure and for a given type of polycarbosilane. So after successfully establishing the spinning condition, then the next step is that stabilization. And the stabilization that as that I have shown, there are three generation, and the generation 1 and 3 is oxidizing stabilization. We also followed this one, and with where there is a SiH. The SiH is the reactive bond, and the reactive bonds where oxygen is inserted to get the SiOC linkage, and this gives the this cross linking and ultimately enhance the mechanical strength of the fibers. So this one actually is a summary of so many experiments. The effect of the fiber radius at a given temperature. I would like to show these are the experimental values were this well studied from that. You can see that for that 9 micron radius, that stabilization is completed in 50 minutes. But for 21 the micron radius, the stabilization is completed about 300 minutes. So that shows that if you're that the batch to batch variations are there, you cannot have the same process conditions for that each batch. You have to be very careful while the selecting the time and temperature. When it comes for the temperature, is even more sensitive. For 120 minutes, you can say is about this 100 hours, while in case of that about this 190, it's only about 50 minutes or so. So ultimately, that I would like to show that temperature time has to be selected based on that this fiber diameter, and if there is variation in the fiber diameter in the bunch, the properties are not going to be uniform. And then this is the typical that how that strength increases with that oxidation. So this is the as spun as well as that when that total after stabilization, this is the strength. The third and the final step is this pyrolysis, and the pyrolysis is the key to get that ultimately the mechanical properties of the fibers which you are making all the efforts. So these are the typical stages for that pyrolysis. So let's say just for that with this figure, if you have that improper pyrolysis, you will be land up with the powder, and then if you have that good pyrolysis conditions, you will be landing with that fiber which is having strength. So this is the first one where the dehydration takes place, because the polycarbonate is having a lot of hydrogen. So first the hydrogen goes out, then the methane, and then small hydrocarbons will come out. And this, so that generation 1, that if you restrict your pyrolysis conditions up to about 1300 Celsius, you will be land up with the generation 1 grade of fiber. And if you increase the pyrolysis conditions to about 1500 to 1800, the generation 3 grade of fiber you will get. And this actually just to give a feel, that suppose that we don't allow the fiber to the shrink axial direction. If we start with 30 micron, you land up with 15 micron, and about 80% volume shrinkage takes place. So this is the key where that fiber will go for the lot of micro cracks at the surface, and then ultimately they will lower the mechanical properties. So this is the summary of the results. That if you go with that the improper stabilization, your fibers will be simply, they will get fused together, and if you have that good stabilization condition, the fibers are separated. And these are the mechanical, these are the XRD, these are the mechanical properties. So the generation 1 equivalent fibers that we are able to make successfully in the tows about 500 mm long. Though that spinning, there is no limit, that even several kilometers of long fibers we are spinning. But the pyrolysis, that is a limitation. We are going in the batch wise, about 500 mm long tows we are getting. And then I believe that the first time we have made in this country to make the fibers having strength about 2000 MPa and modulus about 200 GPa. We have also generated the total process condition. Now that we are moving for that pilot plant, this production of the silicon carbide fiber, the entire the know-how starting for the polycarbonate to that pyrolysis, what are the different parameters and rate conditions. Now that I will move to that second topic, the making of the carbon silicon carbide composites using the polycarbonate what we have made. So the these are the typical process conditions. We have published also this work earlier. So that first to make that reagent solution, we are using the DVB with the polycarbonate, and that is used as a reagent material to make the this UD composites. All the parameters are studied for UD, followed by 2D and 3D. So many different type of compositions as well as the different type of thickness were studied, that what is the effect of this one. And this is the typical these properties, that with that the PIP route what we have made at DMSRD, the properties are on par or slightly better than that what the published literature in that area. Then that was not the aim to make the laminates. The ultimate aim to make the components, and then the feasibility is to make that the nozzle. The nozzle presently that all the missile complex, the nozzles are the carbon phenolic nozzles, and then in the future we would like to replace them with the carbon silicon carbide material, and this is the attempt to make in that direction. And this is the typical nozzle we have demonstrated to make, which is having a diameter about 300 mm and then height about 375 mm. Then another this product we are targeting is the TPS, is for that this re-entry type, this reusable type of vehicles, where that lot of this material saving as well as that it should have a different type of features, because the repeated use, that it should retain its mechanical properties for that subsequent the thermal shock as well as the oxidizing environment. So we have made the laminates, we have studied that how that its thermal and mechanical properties, residual properties are there. We have exposed that cut sample with the oxyacetylene flame, and then we have retested them. We can see that even after 5 thermal shock and then this oxyacetylene flame testing, that the strength is reasonably is about 150 MPa. That's what I can say, is about 150 MPa, and it's a good way. And then we are now that making some protection of this composites to further enhance these properties. So this component also we have made, and then is the feasibility is demonstrated, and then now we are going for the larger size. This is another actually very, very good application of this liquid polycarbosilane, that apart from that solid polycarbosilane which is used for making fibers as well as for this composites, the liquid polycarbosilane comes out as a the byproduct of that synthesis process. And this is excellent precursor for making use as a silicon carbide depositing in place of the MTS. So that this process also we have established. And then we are also establishing that other processes to give the seal coat in terms of this hafnium carbide, tantalum carbide, and silicon carbide using this MTS also we have. So these are typical plasma testing for the tantalum carbide, this coated carbon silicon carbide, and this shown the excellent results. And then this type of this work we would like to extend for that structures also. Then this was not the aim to come here all the way from the extreme end of the country. I wanted to propose that some of the collaboration topics, then I'm sure that some of you might be interested. So we would like to develop this silicon carbide boron nitride ceramic precursor. Though I have seen the Professor Ravi's their startup, they said that they have this precursor. So that this precursor we would like to use for the composites as well as for the fiber. So these are some scheme also we have generated that what the work share would be. Then second is this chemical stabilization of the PCS fiber. As of presently that we are working on this oxidative stabilization method, we would like to establish another this alternate method like this stabilization using cyclohexene, where the oxygen content can be limited. So this also is a very good this topic, and we would like to collaborate in this area also. The third is this high temperature testing of silicon carbide fiber. What are the mechanical properties I have shown? Those things are tested at room temperature. We would like to go for high temperature testing for silicon carbide fibers. So this also is another one. Apart from that one, that our group is we are expanding the different directions. So that CMC design, they are the other interest for the collaboration. CMC designs, NDT of the CMCs, material modeling of precursor, the process for USTC precursors, and the process development for fiber reinforced USTCs. And this is the actually that our foreign friends, I would like to give this offer. If the pilot plant level PCS fiber spinning equipment design, or that may be that machine selling, so that perhaps that our country can approach them. With this, I would like to acknowledge the support of and then our DG NSM, DRDO, and Director DMSID, and my that colleague officers and the staff of the Ceramics and CMC division. Thank you with this.
Thank you very much, Suresh, for being perfectly in time and for this very nice overview of this silicon carbide fiber production. The papers are open for discussion. Yes, here.
Thank you very much for the nice presentation. My question is, you described exactly the process which was developed in Japan 50 years ago by Yajima, which lead to the processing of the Nickelone 200 fiber. What is the difference of your process?
I can say is one difference that what the Yajima proposed is a synthesis of the polycarbosilane using a pressure route. And pressure route synthesis of the polycarbosilane is not that easy to scale up. Tomorrow, if you want to go for production of silicon carbide fiber at the rate of, let's say, few tons of fiber per month. So this high pressure, though that we have that high pressure reactor also, but we know that several times that with a small leak, it will become a sort of bomb type, and then you cannot extinguish that fire. So this reaction mixture is very, very pyrophoric, and it's very, very difficult to control any leakage or any fire if it happens in the pressure reactor, because the pressure will be of the order of 100 to 150 bar. 100 to 150 bar at temperature about 500 degrees Celsius, and that reaction products are methane and hydrogen. Then you can imagine that what will happen. So we have established another route which is at room this atmospheric pressure, 1 bar pressure, and temperature also slightly lower than that one. So that's why our the reaction time is slightly longer, but we are able to manage that.
Okay. And another question, if I have time, how much you can produce at the moment of the SiC fibers?
At the moment, actually, that our aim is not for the production. Our aim is to establish all the process parameters which are essential for the production, and then to establish that what are the effect of the different parameters. So those things successfully we have demonstrated, and then I'm quite sure that maybe in years to come we will be in the production level also.
Okay, thank you so much.
Other questions from the audience? If this is not the case, thanks again, Suresh.
Yeah, thank you.
Thank you, sir. I request Dr. Thomas to present memento to Dr. Suresh.
So the next presentation, being ready to be plugged in, will be given by Professor Ravi Mohan Prasad. He's professor at the Indian Institute of Technology in Ropar, and it will be an invited talk about progress in polymer-derived poroceramics for gas sensing applications. Now we wait till everything is being hooked up. I'll be there.
Hello.
Perfect. Professor Prasad, we're looking forward to your presentation.
Yeah, good morning, everyone, and thank you, Chair, for the introduction. First of all, I would like to thank Professor Ravi Kumar for inviting here, and I'm coming to my undergraduate institute after a long time, and just seeing the campus, how much development has occurred. So with the progress what I have seen in the IIT Madras, I would also like to present my progress in the last 10 to 15 years in the area of polymer-derived ceramics, especially in the area of gas sensing applications. Okay. Well, this work, at the moment I say last 10 to 15 years, definitely I was not at IIT Ropar at that point of time. So I will be, I'm really thankful to Professor Ralph Friedel and Professor Alexander Gurlow. Definitely has moved to TU Berlin, but that time we were working at TU Darmstadt. These were my PhD mentors. Professor Udo Weimer for helping a lot with the gas sensing facility, and Professor Yuji Wamoto with supplying lots of membrane supports, as well as for very nice interaction in this membrane area. And definitely the moment I moved to India, my PhD students have helped me a lot in development of the lab, and definitely without the funding support from DFG and DST, it was difficult. Okay, so this just a brief thing about what we are doing at IIT Ropar right now. Definitely continuing some of the work for the gas sensor membranes and anode materials. We are also working in the area of high pressure hydrogen storage type 4 cylinder to store hydrogen at 700 bars, and also working on metallurgy department for the corrosion resistance and novel high temperature composite materials, and also in the area of automotive application for in situ generated PDC-based metal matrix composites. Well, today I will be talking mostly in the area of PDC with the gas sensors. So this is a brief outline of the talk. Definitely I will talk about the limitation of the gas sensors and a brief introduction about the gas sensors. And I think in the last two talks, we have already seen the how the porosity is being developed. So thank you very much. And definitely I won't say exactly its result. It's difficult to compile everything in the 20 minutes. So I will be giving the highlights of the results and what was the development happening, what led us to choose from this sensing material towards this one. Okay. Well, a brief introduction about the gas sensors. So it's everybody knows what exactly the sensor, but here in the area of chemi-restricted gas sensors, basically, if you have, let's say, tin dioxide-based N-type sensors, so under the oxidizing gas, you see this is the resistance curve, this is the concentration, so you will see an increase in the resistance, whereas under the reducing gas, you will see a profile of decrease in the resistance. So this is basically with respect to N-type semiconductor, because in my most of the results are really showing such kind of curves. That's why it is very important to bring it here. But instead of commercial one, in the lab scale, the sensor needs a sensor kind of support, which has integrated electrodes. On the top, you can see, and the back side, the heater. They're made of platinum. And the sensing material has to be coated using the screen printing method here. Okay, so the mesh is there, and your powder is being mixed with proper kind of solvent, and then it is screen printed to get this kind of sensors. Okay. With this introduction, I would just like to tell what was the need of working in this area. So these are quite well-known gas sensor materials, but if you see, one of the major problems with this kind of sensors is what we call lack of selectivity. What exactly it means? For example, if you see this particular, so this is with respect to tin dioxide sensor, and if you see the nature of the reducing gases, let's say hydrogen, CO, and methane, they're almost similar the moment I go from here to here. As well as, and let's say if in the mixture we have hydrogen and CO, okay, and some concentration is there. And if you want to know what is the percentage of hydrogen and CO, the sensor, if it is not being doped with something, it is difficult for it to identify, because the interference effect of hydrogen, CO, and methane will be there, overlapped. So we have to, if we want to see the effect from one of the gases, we have to remove other interfering gases. So this is what is called a lack of selectivity. Other thing is quite well known, metal oxide sensors. So it will try to get reduced at high temperature under certain concentrations. So this is what we call as lack of stability under harsh conditions. Where over the last 20, 30 years, there are lots of methods have been developed by controlling the temperature of the application of the sensors and using sensor array where we have different kind of sensors for different kind of materials. But we wanted to work using the PDC, like using PDCs as a filters for eliminating this kind of interfering gases here. So this is what I'm going to present here. Well, the moment you think about a porous material, and definitely you would try to see the gas has to go to the sensor surface, okay? So definitely the different kind of mechanisms will be playing. I'm not going to discuss in this detail. This capillary condensation and surface diffusion, these are mainly occurring at low temperature. So it's not very much useful to define the mechanism in high temperature sensing applications. So mainly the Knudsen diffusion and the molecular sieving applications is much more applied. And here the gas permeance is inversely proportional to square root of the mass of the molecule. When the molecular sieving, this works only when the pore diameter is very near to the gas molecular diameter here. So, and you can see here also the permeance of the gas increases with the temperature. So the moment I keep increasing the temperature, I can see lots of permeance of the small molecular gases. So mainly this and this two effects is playing a major role in the separation of the gases here. So just for the focus for the hydrogen and CO here, you can see the molecular diameter of CO is around 3.7 and hydrogen about 2.9 angstrom. So you need to really, if you want to really separate one of them, so you need to develop a membrane, although I can say the filter with a pore diameter of about 3 angstrom, definitely a quite challenging task. But the PDC, why it can be helpful? As you know, during the cross-linking reaction and during the ceramic formation, as we have seen in the previous one, we have the generation of hydrogen, methane. And so the moment the gases is coming out from these matrix, it tries to generate the interconnected pores in the finally amorphous ceramic. And that is the basis of generating the pores in this kind of ceramics. Quite easy concept here, okay? So the first material was SiBCN here. So it was based on the cyclosilazane and hydroboration reaction at very low temperature. And so this was the polyborosilicate here. And finally, to characterize it, you need to do the powder-based, and finally, we found it was microporous at 800 degrees Celsius here. Yeah. The moment you keep increasing the temperature, because of the viscous behavior of the system, the pores are not stable. But anyway, this is the 700 to 800 is a transition stage of polymer to ceramic, or almost completed also, definitely with some amount of residual hydrogen, but it is not going to affect much performance there. Okay. So in order to do the coating of this one, if you keep for longer time, this was one of the issues with the SIBCN. We have to keep the system at low temperature, but the moment doing the coating of the sensor here, the moment you keep it out, the cross-linking was quite faster here, and that was helpful. So, and the coating of the sensor, so this is your SNO2-based sensor. So this was a substrate I've shown before, and the screen-printed sensing layer. And so the dip coating was done. It was in a control, which was taken out and finally pyrolyzed to get multi-layers of membranes of SIBCN. Okay. And so this is showing after one-time coating, we got a thickness of about 1 micrometer. Okay. So let's try to see what was the performance of this kind of membranes, coated supports. So what you see here, this is the gas sensing under carbon monoxide, and this is under hydrogen. So the black profile shows for uncoated tin dioxide, and the red one is for membrane-coated SNO2. Okay. So now what you see here, even the membrane-coated and coated one both are able to sense the gases based on the change in the resistance. Okay. And in the case of hydrogen, also they're able to sense it. So it means here, in this case, my purpose was to stop the sensing of CO. I should not see more change in the resistance under the CO gas here. But that did not happen here in this case, definitely because of the pore size was quite larger. But what we found here, if you see, this is for the uncoated, and this is at 530. Under high concentration of hydrogen, the sensor was no more stable. Okay. So this brings a new paradigm of using this kind of coating for stabilizing the sensors under harsh radiation conditions there. Although we wanted to get a selective sensors, but we try to protect the sensors under such kind of reducing conditions. Okay. So just a brief mechanism of this, what we proposed here. The moment this kind of reaction is happening, okay, and some of the pores are in the range of 4 to 6 angstrom also. So there the channel works like a Knudsen diffusion mechanism. Okay. So where it's inversely proportional to the square root of the mass of hydrogen and H2O. So it means the permeance of the hydrogen towards the sensing layer was 3 times more than the water vapor which was coming out. And therefore this reaction is appearing to be shifting towards the left side. And that is what we proposed, the stability reason behind the SNO2 sensors in such kind of harsh reducing conditions there. Okay. So this was, we started with this concept, but we did not able to achieve, but we went to the different direction in this case. So now we realize that SN2 sensor may not be very useful if I take the basis of this material. So we moved to a new material, which was gallium nitride. Okay. We try to, and we also know the issues with the SIBCN, because we have to operate everything at low temperature. So we went to okay, now it is called a durazane, so it's a polysilazane. It was amylolysis, and we found silicon nitride was formed. I'm not showing all the characterization because of time limits. So it was very nice microporous silicon nitride was obtained. And this is quite compatible to coat on the gallium nitride sensors, because even gallium nitride is produced from amylolysis of gallium oxide. So this was the best combination. And so let's try to see what the result we got after this one. So right now, please try to concentrate on this, I would say light blue-green, what color? This one, the upper curve. So this is the membrane coated, and this dark blue is the uncoated gallium nitride sensor, okay? So what you see, gallium nitride coated sensor is definitely sensing the CO, whereas the silicon nitride coated gallium nitride is not sensing too much CO. So what we assumed, whereas in the hydrogen case, everything was sensing, right? So initially, the moment we did measurement of membrane coated and coated one, so we were very happy that, oh, it worked very nicely. But later on, the moment we go to the chemistry, so, and it was really difficult to produce such kind of nice membrane. So what then we did, we tried to do the treatment of the gallium nitride sensor, which is already produced, okay? Again with the ammonia, because the moment we try to make this membrane, the system, the silazane, and then ammonia is already there. So we were thinking maybe ammonia is doing some role in doing all this thing. So this is what expected here. Ammonia tried to make some changes in the existing gallium nitride. And you can see here there was a decrease in the response for CO just by treating the ammonia here, okay? Hydrogen was remaining the same. So we tried to see the chemistry of this thing, and we found, so the upper part is with respect to the as received gallium nitride, which was produced and kept for a long time. And we can see that definitely in this kind of nitrides, you always see amorphous surface. So this can be also seen. And this was after treatment with ammonia. So what we found that the big particles of gallium oxide were present on the surface of untreated gallium nitride. And after treatment, the size was reduced. And effectively, the weight percent of the oxygen, okay, was reduced from 4 weight percent to 2 weight percent. So definitely residual oxygen which is present in the surface, and this is sensing is basically the surface phenomena, is playing a major role. So this is what we proposed here, that the moment you have a gallium nitride, okay, so if you keep it for longer time, the surface oxidation is happening here. At the moment after longer time, it tries to produce Ga and O2 here, and mostly goes to the gallium oxide. So based on our analysis, what we observed that the moment you have oxygen, lots of oxygen is happening in gallium nitride, they are more sensitive towards CO, but not the moment it's very much pure gallium nitride. Okay, so this is a new way of understanding that what we found that response of the gallium nitride towards CO sensing was because of oxygen contamination, totally different concept. We were trying to, we were thinking here that silicon nitride is stopping the flow of CO, but finally we came to like different results. So one time we used SIBC and we moved to a different direction of stability. Other time we moved to a new concept of how the sensing is happening in the case of nitride-based materials. So finally, based on this experience, okay, parallelly we were also working in the silicon oxycarbide. So here we took a vinyl polysilaxane here and tried to coat with a membrane. So our main work was in the area of hydrogen separation. So based on that concept here, so you can see here the membrane one time coated gave a nice, very thin kind of membrane, SiOC membrane on this kind of porous supports. I'm not going into detail of this thing. And this is the profile of permeance with the temperature. So if you see the permeance of hydrogen with the CO and CO2 here and SF6 is quite increasing, okay, largely increasing. So indicates that the porous channels are definitely supporting the permeance of the hydrogen and stopping the flow of the larger molecular gases here. So based on these results, very soon we try to now coat the gallium nitride because we know this problem with the SNO2. Okay, so we learned over there, so we try to use the gallium nitride. And then with the good performance of SiOC, as you have seen previously, we try to coat it. And this really confirms that the coating of the SiOC based on the EDS elemental mapping, SiOC, and as well as gallium nitride. And what I try to put here, like gallium nitride sensors, the moment you do the X-ray diffraction, okay, because the depth of the penetration of the X-ray is so high, you cannot avoid the gallium nitride. And that's why, and because the SiOC amorphous, you will always see the profile same as gallium nitride sensors here. So to confirm this also cross-checking here, we have to go for the Raman here, and you can see that because the Raman depth of penetration is not so high, so I cannot see the peaks of the gallium nitride in the case of membrane-coated gallium nitride sensors here. So this really confirms a good coating of SiOC over the gallium nitride. So after this thing, we try to see the gas sensing performance of, so this is red one is the membrane coated gallium nitride, and black one is uncoated gallium nitride. Okay, so you can see here the gallium nitride. Again, just to say, this is not really a 100% pure gallium nitride, it's a commercial one, and after keeping it for a long time, as we have seen, it always have some sites of the oxygen contamination. So this is what is sensing here, okay? But the moment the membrane is being coated here, you can see the sensing towards CO was highly reduced in this case. Whereas in the case of the hydrogen, you can see the profile remains the same. Definitely because of the SiOC is occupying the surface of the gallium nitride, there will be some reduction in the performance here. So this finally proves our destination to obtain, how to obtain the PDC-based membrane-coated sensors for selective detection of hydrogen with respect to CO. Okay. So with this thing, I'd just like to summarize what we have seen in the case of SIBC. Although we wanted, finally, the aim was selective hydrogen to CO detection, but SIBCN was not helping in that, but it tries to give a new perspective of stability of the sensor under such harsh conditions. And from this silicon nitride-based process, what we obtained, what is the issue with the gallium nitride, what is basically playing a role in the CO sensing in the gallium nitride sensors, and finally, the best combination what we found was PDC SiOC-based gallium nitride for selective hydrogen detection with respect to CO. Yeah, that's all from my side. I tried to explain. Thank you.
Thank you very much for this very nice insight into the sensing and filtering behavior of silicon carbide materials. Are there questions from the audience? Yeah, first here, Sanjay. And then here.
Thank you, very nice work. I was just wondering about the mechanism of detection of CO, because it's a reducing gas, and I think you need to form CO2 somehow, and that's why oxygen contamination is a must for in your case. So it's not the gallium nitride, but it is probably the oxygen or the overlayer. So how does this compare with gallium oxide then, pure? Because that's also wide bandgap material and equally sensitive towards CO.
Yeah, so in the case of, I hope it's audible. So in the case of most of the gallium oxide, metal oxide, so the phenomena is like, you always have some amount of, let's say it is different atmosphere, oxygen, it is under oxygen. So oxygen at a high temperature, it tries to form O2 minus, or very high temperature, it makes O minus. And there basically the CO reacts with the O minus, okay, O minus, and tries to produce CO2, and the electron is being sent, and therefore there's a change in the resistance over there. So this is the mechanism of, in the case of gallium oxide. Gallium oxide is very much, what we try to show here, that gallium oxide kind of thing, or amorphous kind of oxygen coating on the gallium nitride will be helping in the case of CO sensing, okay? But if you take a pure gallium nitride, freshly prepared, put very nice characterized, then it is not going to sense CO. That's a simple concept we observed.
Thank you.
I think here was another question.
Yeah. First of all, thank you, Professor, for sharing the nice activity on silicon oxide carbide coated gallium nitride. It is really fascinating. Just my thought of, actually my question is from different perspective. Say, we wanted to build up this platform based on three: aerospace, defense, and environment. I think you really address the environmental point of view. Just want to know if it's possible to control the porosity of the pre-ceramic polymer coating so that it can be used for meaningful filtration, ultrafiltration, or nanofiltration purpose.
Yeah, very nice question. So as I said, when I started my PhD, the main work was separation of hydrogen with the carbon monoxide and CO. That was my main topic, okay? And this came parallelly, okay, integration of these one. So, well, because of the time limit, I did not able to discuss how, so it took almost 2 years to get to know how to control it. So one thing is, if you see most of the PhD work or the research work, they try to do this cross-linking and then pyrolysis at, let's say, 150 Kelvin per hour or 200 Kelvin per hour. So what, from my experience, what I observed that if I try to decrease this pyrolysis rate, let's say 50 Kelvin per hour, so that was the limitation with the furnace. So I can see there is a large improvement in the kind of porosity. And if you try to see the TGA profile, okay, so the moment it is at the transition of polymer to ceramic transformation, at that point, if you try to stabilize your system, okay, through some means, but if you go beyond 900 and 1000, it is not going to be stable. Definitely some porous materials you can also see at 1700 because of carbothermal reduction that we have also seen, but those are not very much useful because different reasons. So the thing is here, but now some of you may say that 800 is not a complete conversion. So what I would like to emphasize here, the moment we try to make this membrane, we keep it for a long time, 15 days to, and even the whole measurements goes for multiple rounds, so 1 month or 2 months of. So there is no issue even if some residual hydrogen is there. So you have to control the heating rate, and you have to get exactly at what temperature after multi-iteration of temperature of pyrolysis.
Thank you. There's one last question here at the end.
A very interesting talk. I'm just trying to understand what is the mechanism of permeation, because you have explained some 3-4 permeation mechanism. Because the substrate is, I assume it is a dense, or is it porous gallium nitride? So is it a permeation or is it a sorption?
So substrate is, okay. Yeah, there is no board for me here, otherwise. Yeah, so what you see here, first is the substrate,
yeah,
and the sensing layer is there, and then you have a porous substrate on there. So that allows the gas to go through the porous channel and come to the sensing surface.
Okay, so that's not. Because substrate is dense, but there is a opening for the
yeah,
so there is a permeation.
Yeah, the filter is a kind of a porous channel.
Okay, thank you.
Sure.
Okay, thank you very much for this nice discussion. Let's thank the speaker again.
Thank you, sir. I request Dr. Thomas to present memento to Dr. Ravi Mohan.
Thank you.
So we're coming now to the end of the session with 2 young researcher talks. And the first of which will be from Melanie Wynn from the University of Limoges. And she will present her talk on mechanosynthesis and version of highly crystalline hexagonal boron nitride precursors. Melanie, the stage is yours. We're looking forward to your presentation.
Yeah, thank you. Hello, everybody. Thank you for the introduction. So yeah, I'm a postdoc at IRCR laboratory. And so I'm going to talk about mechanosynthesis and the thermochemical conversion of highly crystalline hexagonal boron precursors. So this work is part of the zeolite project, which is in collaboration between the ICG and and the L2C labs in Montpellier in France also. And so the aim is to elaborate a UV LED based on hexagonal boron nitride zeolite composite to be used as a white light device. And so the process is to take molecular BN precursors and introduce them into the zeolite using high pressure, then convert those precursors into boron nitride upon heat treatment to finally use these composites into a UV LED prototype. And so at ESR Lab, we are focused on the elaboration of the molecular precursors using the PDC route. So this talk will only be about the precursors and the resulting BN powder. And so we choose hexagonal boron nitride because it's known to have a strong far UV emission, which could be enhanced by the confinement in the zeolite. But for this, we need highly crystalline materials. As for the insertion into the matrix, we are aiming at small molecular precursors, so they can be easily introduced to the heart of the matrix. And for this also, it would be preferable if they could be in the liquid state. And also, in order to preserve the matrix and to have less energy impact, we are aiming at transformation at the lowest temperature possible. Okay, so we start investigating the transformation using ammonia-boron complex as a precursor. Indeed, with temperature, ammonia-boron will start to polymerize into polyammonoboron and polyiminoboron. Then, upon further treatment, we can obtain amorphous boron nitride, and finally crystallized, but at very high temperatures. So this precursor is a good starting point because a sample heat treatment is needed to produce boron nitride, since we have only nitrogen, boron, and hydrogen in the composition, and we have the white stoichiometric. It is also meltable. So this is good for the insertion in the matrix because it's liquid at around 100 degrees. But one drawback is that it releases a high amount of gases during its transformation, around 130 degrees, and this on a short span of time. So it can be a problem. And also, we need very, very high temperatures to reach BN crystallinity. So we decided to investigate the modification of ammonia-boron with lithium via mechanosynthesis. Indeed, lithium is known to promote boron nitride crystallization. And also, the product is viscous, stays viscous for a few hours to a few days upon synthesis, which is, again, good for the insertion step. So it all starts in a glove box, where we place into a ball milling reactor our precursors, that is lithium amine and ammonia boron. And we do this in a defined molar ratio between boron, atomic ratio between boron and lithium. We studied ratios of 1, 3, and 5. Then we ball mill this at 250 rounds per minute for 5 minutes. And we obtain, after some time, a white powder composed of various entities like aminolithium aminoboron or lithium aminoboron, or even most probably lithium substituted PAB or PIB. Then this powder is pyrolyzed at 1000 degrees under ammonia, and eventually calcinated at 1200 to 1800 degrees under nitrogen. And so first we studied the impact of the ratio. So you can see on the diffractogram here the results for R equals 1, 3, and 5 pyrolyzed at 1000 degrees. So we can see numerous peaks, among which we have reflections from hexagonal and rhombohedral BN, which are ill-defined around the 42 degrees to theta region. And this is representative of turbostratic BN. Turbostratic BN, like hexagonal BN, is a layered structure, but in which the BN layers are ill-aligned one to each other. We also form an oxide that is lithium borate, For R equals 1 here, we form a phase that we named lithium BN, which is due to the insertion of the lithium in between the BN layers. When we look at the second graph here, where we have the results of the powder treated at 1,400 degrees, we can see that there's no more lithium borate, and that the lithium BN phase for R equals 1 has also disappeared. And we see that the BN is much more intense, the peaks are much more intense, and we can observe a clear impact of the ratio. Indeed, as the ratio gets lower, that is with an increase of lithium content, we have an increase in BN crystallinity. And so the R equal 3 and R equal 5 samples are still turbostratic, whereas R equal 1 is highly crystalline and pure hexagonal BN. And so it is known that the lithium borate can promote BN crystallization. Indeed, those compounds can melt at relatively low temperatures, that is around 750 degrees. And so they can dissolve the polycrystalline turbostratic BN that can then easily recrystallize into well-organized BN. And so that's what happened for our sample R equals 1. So we decided to study it a bit further. So here you have the high temperature evolution of this sample with diffractograms at 1,000, 1,200, 1,400, and 1,800 degrees. And so we can see that at 1,200, we lost the lithium in circulation, but we still have our lithium borate that only evaporates at 1,400 degrees to leave our highly crystalline BN. And between 1,400 and 1,800 degrees, we can hardly see any difference between the XRDs. So we decided to do thermal investigations on those powders. And so at 1,400 degrees here, we see plate-like particles, which is expected for a layered structure, but they don't have any specific morphology, except some of them that are starting to show an hexagonal feature. At 1,800, then we have mostly hexagonal particles. All of them are hexagonal, and we see very well-defined angles when we zoom in. Okay, so to conclude, we were able to achieve the mechanosynthesis of a BN molecular precursor made of ammonia boron modified by lithium, and it is suitable to be tested to be inserted in the zeolite matrix. We saw that the key parameter is the ratio of boron to lithium, and that the ratio of 1 is needed to have this highly crystalline and pure hexagonal boron oxide. And so we were able to synthesize this phase at a temperature as low as 1,400 degrees. And at 1,800 degrees, we even saw that we had very nice hexagonally shaped particles. And to our knowledge, this has not been reported at such low temperatures yet. We will continue the work and try to lower further this temperature in order to obtain still a very good crystallized BN, but at lower temperature to save energy and have even less impact on the matrix. And in the further future, we will think about using this hexagonal BN powder as a thermal conductivity enhancer for organic polymers, and also to elaborate very large boron nitride sheets. Thank you for your attention.
Thank you very much for this very interesting talk, and also for staying perfectly in time. The paper is open for discussion. Are there questions from the audience? I don't see anything, then I will start with a question. I was just wondering, you mentioned at the beginning the infiltration of this porous matrix with the aminoborane, but then with the lithiation of the aminoborane, I think this one is not, how did you do the incorporation in the matrix?
Yeah, so this is just being started with the lithium aminoborane, but it stays viscous for a few hours to a few days after synthesis. So we do it at that stage, and it's the same way. We put all this in a pressure apparatus, and under pressure with a little bit of heating, we can then set it into the zeolite. Yeah.
So you infiltrate using the viscous precursor, so it's not a gas phase infiltration, it's a liquid viscous infiltration.
Yeah.
Okay, thank you. If there are no other questions, I don't see anything. So thanks a lot, Melanie, for the presentation.
Thank you. I request Dr. Thomas to present memento to Dr. Melanie.
So the last presentation before the break will also be a young researcher's talk given by Jakob Denk from the Chair of Ceramic Materials Engineering of the University of Bayreuth. And his title is going to be Novel Carbon Ceramic Electrospun Nonwovens with a high oxidation stability and a combination of low thermal and high electrical conductivities. Thank you very much. Thanks. So Jakob, we're looking forward to your presentation, and the stage is yours.
Okay. Okay, perfect. Thank you for the kind introduction. As I said, I'm Jakob Denk from the Chair of Ceramic Materials Engineering in the University of Bayreuth. And today I want to present you about my latest research topic. The motivation for this was that we wanted to develop new flexible carbon ceramic fiber material with improved oxidation stability from polyacrylonitrile and organosilazanes. The reason was that carbon fibers start to oxidize at around 400 degrees C, and SiC fibers, which are the alternative, are super expensive. They start at around 2,000 euros per kilogram. One limitation was that polyacrylonitrile cannot be melt spun, and thick ceramic fibers are not so flexible. So the idea was that we use electrospinning technique, which directly leads to nonwovens with diameter in the nanometer range and can be used for polyacrylonitrile and our organosilazanes. Maybe not all of you are familiar with electrospinning, so I want to explain it briefly. In electrospinning, you continuously pump a polymer solution out of a syringe. On the way out of the syringe, the droplets start to electrostatically charge on the needle. And because you put a voltage here, you get the formation of a Taylor cone because of the electrostatic charging, the voltage, and the surface tension of the solution. Because of the applied voltage, the polymer is accelerated, and a formation of a jet starts. On the way downwards, the solvent almost evaporates completely, and you collect fiber mat directly in nanometer scale. The other basic thing I want to explain is how carbon fibers are produced. Normally, they are made from polyacrylonitrile. They are first oxidized at 200 to 300 degrees C. On this way, you get cyclization reactions. You come to the structure from the linear molecule. And afterwards, you have a pyrolysis in inert gas, where you come to a more or less pure carbon structure. This is done at around 1,000 to 1,500 degrees C, where you get amorphous carbon with a high tensile strength. Or if you graphitize it at even higher temperatures, you can get high modulus, but a lower tensile strength then. And then in commercial fibers, of course, you have some surface treatment before the fiber is finished. But as I said, you have the big disadvantage that the carbon fibers start to oxidize at around 400 degrees C. So in the past, my group had a very nice idea. They made hybrid polymers of acrylonitrile and the durasanes from Merck. And after pyrolysis, we experienced a high oxidation stability. The more silazane was in, the better the oxidation stability. And the slower, or at higher temperatures, the oxidation started. The reason for this was that we have cross-linking reactions between between SiH and cyano bonds, which lead to SiN bonds during the pyrolysis. And during the pyrolysis, you get carbon nitride nanocomposites, which act as a passivating layer and are the reason for the high oxidation stability. Now I come to my work. We wanted to go forward and did electrospinning of pan and silazane blend. Then after the electrospinning process, you come to this polymer nonwoven, which we, as carbon fibers, oxidized at up to 300 degrees C, and then pyrolyzed to this carbon ceramic mats. For the nomenclature, this is the name we gave them, and X is the weight percent of organosilazane in the polyacrylonitrile. And after these temperature steps were optimized, you get to very flexible fibers. I can show you a video. I hope it works. Does it work? Yes. So we compared our fiber mats with normal printing paper. And you could see that even with a lot of folding and pressing, we got a very stable material. And yeah, it did not break. It didn't have any cracks. And the fibers were super flexible. Hope the microphone works again. And the fibers were super flexible. So, and you can also, like in the paper, you see some folding marks, and this you don't even see in our flexible nonwovens. Okay, and yeah, here you have the pictures and also the same pictures of our fibers, and as I said, they are in nanometer scale and very flexible. What we then did was, of course, some analysis. We did Raman and wax measurements. And there you could see the typical D and G line for carbon for all different composites. So we have a lot of graphitic and amorphous carbon in our material. The same you could see with wax measurements. We didn't see the carbon, the silicon structure, because probably the intensity was too low. And we see the big graphitic carbon peaks. So we have amorphous carbon structure in our material. Then we did elemental analysis and silicon NMR, and there you can see the calculated structure, the calculated composition in polymer state after oxygen stabilization and the pyrolysis state. And you see that because of the electrospinning was done in air, you get some oxygen which reacts with the durasane. And of course, also in the stabilization process, you get more oxygen in. Also, you can see that nitrogen and hydrogen decreases because of the pyrolysis reactions that take place. In solid state NMR, you see a big silicon oxide peak and different ceramic environments, and yeah, a mixture of all these composites, all these species. But yeah, as I said, we have a very high oxygen content in our ceramic. What we then did was we measured electrical conductivity over a relatively wide temperature range, and we saw a good or very high electrical conductivity for all different composites. It decreased a little bit or slightly with higher silazane content, but it was all in the same order of magnitude. What we also did is to show again the folding and the good electrical conductivity. We did another folding test where we folded our nonwovens for 5,000 times and simultaneously measured the electrical resistance, and it stayed constant over all these 5,000 folding times, and also the membrane did not break. So as I said, a very flexible and electrical conductivity material with high electrical conductivity. So this was basically running over a whole night. Then what was very surprising to us, we also measured the thermal conductivity with different techniques, in-plane and cross-plane, our nonwovens, and we could see that we have a very low thermal conductivity, and which is actually comparable to our aerogels. And this even decreased with higher silazane content. And what we have now is we have a material with high electrical and very low thermal conductivity, which is very rarely. There are not so many materials who have such properties. And how rarely? We obviously, in this graph, we looked at over 3,900 different materials, and we are here. So there are basically not really other materials who have such properties. So we have a very unique material. Now, of course, it's interesting why we have such properties. And the reason is we did STEM and STEM EDS measurements, and there we saw this island in the sea structure. So we have some carbon interfaces and we have some ceramic interfaces. And the carbon interfaces, we call it the sea. It's a reason for the good electrical connectivity because the carbon is still connected. And the ceramic is the island in the carbon sea, which, because of the interfaces between the carbon and the ceramic, acts as a good thermal insulator because it's a reason for phonon scattering between all these interfaces. And on top come of course, the boundary scattering between these different nanofibers. What we also did is, because we wanted to get a material with high oxidation stability, we did burning experiments. And the burning experiments we did with LOI tests, it's a limited oxygen index. It's often used for polymers. And there you measure, or there you determine at which oxygen content in the atmosphere your material burns down on its own. And for carbon, it completely burned down. Where is my mouse? For carbon, it completely burned down at already 80% oxygen. And our hybrid material could not burn down even at extreme conditions of 100% oxygen atmosphere. So this burns down in seconds, and this can't be ignited. Doesn't matter how long you try to burn it. So here you also see it in the pictures. And what we also did was we tried to burn it in a normal metal flame for 5 minutes. The carbon is completely gone. With 10% silazane, you see maybe some white spots. And with higher silazane contents, you don't see any defects of the burning. So we also have a very high flame resistance in our material. Now I want to summarize my talk. As I said, we did electrospinning of various pan-silazane compositions. We successfully processed flexible nonwovens with pyrolysis. We analyzed this island in the sea microstructure, and we had a very unique material with high electrical and low thermal property, as well as a high flame resistance. Then thank you all for your attention. Also thanks to my coworkers who helped me. And of course, thank you to DFG who were doing the funding for my work. Thank you very much.
Thank you very much, Jakob, for this very intriguing information and results. Thanks very much. Other questions? Yes, here in the back.
Very interesting work. So I have just a question because you showed that you use different weight ratio between Zaban and Silazane. Do you see any difference in the flexibility in the final product? Like which percentage you have shown in this video?
Not a very, I think this video was made with 40 or 50%. Actually, they're all very flexible. Pure carbon is not that flexible. It breaks more easily than the pure silazanes, but they're all very flexible.
All are very flexible.
Yeah,
Okay,
you can fold all of them and bend them.
So independent of the weight ratio in this case?
What is it?
It's independent of the weight ratio?
It's independent, yes.
Okay.
More or less independent.
Thank you.
Okay. Then, other questions? I just have a very short one regarding the solvent you're using for electrospinning. What are you normally using there for polyacrylonitrile?
We use DMF because DMF is one of there are not so many solvents who can dissolve polyacrylonitrile.
Okay, and the evaporation for DMF is
we
still
also,
because it's quite tricky sometimes.
we also added some acetone so the DMF is kicked out faster.
Okay, good. Thanks a lot.
Yeah, you're welcome.
So there are no any other questions. So thanks, Jakob, for the nice presentation
Thank
and
you,
the
Jakob.
discussion.
I request Dr. Thomas to present memento to Mr. Jakob. I now request Dr. Ravi Kumar to present memento to Dr. Thomas.
Tea break. So we are reconvening at 10 past, no, 5 past 11. So enjoy the tea and then we come back at 5 past 11. Thank you.
Welcome back, everyone. Now, moving to the next session of the day, I would like to call Dr. Suresh Kumar for chairing the session.
Can I be electrified?
Okay, it will work. So, may I check that? It will be off.
It is on.
Is it?
It is on now. So.
In this session, we have five lectures
Okay,
to the five talks two are keynote lectures and three, one is the invited talk, I think, and two from the young researchers. So I would like to talk. I would like to call first first speaker, Dr. Michael Sepper, and he is chair materials technology, non-metallics and composites at Germany. And then he will be talking about the processing and characteristics of ceramics, polysilazanes. So I think this is going to be a very interesting talk. So I welcome him to this talk and then ask him to make a presentation.
Thanks, Suresh, for your kind introduction. First of all, good afternoon, ladies and gentlemen, namaste. And I may say thank you to Günther and Ravi for making this idea from last summer so fast working to have this beautiful workshop here in Chennai. So my presentation today is a little bit more related to polysiloxanes as oxygen-containing pre-ceramic polymers. And in the first part, I may let you know where I come from, where the heck is Magdeburg. Magdeburg is in the middle of, somewhere in the middle of, almost in the middle of the northern part of Germany, still in the eastern part. And actually, we have two famous suburbs. The one is Hanover. The other one is Berlin. So other people call Berlin a big money sink, and we are in between. So it is halfway between both. And Magdeburg actually has its highest inclination angle of the sun at AM 1.15, which gives you a degree of 62 degrees or so. And so this is an amount of energy which comes down when we have a sunny day at June 21 of, say, 850 watts per square meter. So it's a lot of energy which might be converted. But so this is an ideal situation. The real situation yesterday was this one. So for those who haven't seen this before, and also for some Germans haven't seen this for a long time, this is, so the white powder is snow. So we have a temperature difference from here to Germany, to Magdeburg, which will appear as a thermal shock when coming back home. Okay, so first I introduce some, or with some slides we see here, we have some ceramic parts all made from polysiloxanes. These are micro parts, these are macro parts, these are CNTs, and all this actually can be prepared and can be transferred into ceramics with a high reproducibility, and I may focus on some of these parts here, and we'll start now. So first we'll give some motivation and some basics before coming to some examples, and here we see the polysiloxanes. So there are some structures given in the literature. We have those random structures, those ladder-like structures, cage-like structures, those partial or open cage structures. What all they have in common is we have one Si surrounded by three O atoms, and the fourth valence actually is occupied by H or by an organic rest. And actually from this, we have this complex decomposition behavior, which leads to a composite ceramic when pyrolyzed actually under exclusion of air. So the polysiloxanes are available as liquids or as powders. they have a huge variety of organic entities here, methyl, phenyl, vinyl, hydrido, or simply OH in specific cases, or partially. We have a low average molecular weight, which make them soluble in organic solvents. They are mostly composed of T-functionalized silanes. However, when actually synthesized, one can add D or tetra-functionalized or D and M silanes in order to terminate the structure, in order to loosen the structure for properties generation. And last but not least, they are available as resins, as rubbers, or even as silicone oils. Next slide shows us that due to the great variety of R, actually we have a great number of different cross-linking processes shown in this next slide. So the most popular might be the condensation reaction here. So you don't need any catalyst, which resides actually after pyrolysis in your system. We have the catalytic Si bond formation here between a vinyl group and an SiH group. So the alcoholysis might play a role in cross-linking in the liquid to solid transformation, or we have the hydrocoupling, and we have heard yesterday that also the functionalization with acrylates play a role for photocuring. So far, a little glimpse into the cross-linking, which is a very important part within the processing with silicones. And the next slide shows how gases are released. Here we have investigated a great variety of different polysilazanes, and you see so that the pattern actually repeats in the first part. So up to 400, we have the release of oligomers, we have condensation reactions and the release of condensation products. And then the second part actually, so the temperature works hard with the organic rests, which are occupying the fourth valence of the silicon, leading to the release of corresponding gases. So that means in the case of phenyl polysiloxane, we have the release of benzene, for instance, or when having methyl polysiloxane, a CH4 methane is released. So actually, this was also published by, in a little bit broader context, was published by Jamila Ollier, Balul Ollier, and here actually we see that condensation reactions play a role. We have a set of cleavage of SiCH3 bonds, SiH bonds, SiOH bonds. We have loss of silicon-based species. We have redistribution reactions. We have homolytic bond cleavage of SH bonds. And actually here you see we have the cleavage of SiC. So what happens to the gases which release? So we have shown a couple of tens of years ago that when introducing nickel, so we have heard talk about nickel introduction into polysilazanes today in the morning. When introducing nickel, it is reduced, nickel as nickel acetate, it is reduced to form nickel nanoparticles which are stabilized by the matrix. It was shown in this paper here. And so they act as catalysts for the formation. You see it here at 850 and at 1000 degrees C in argon to form carbon nanotubes in situ without any carbon-containing pyrolysis atmosphere. So again, when pyrolyzing our polysilazane, then here is a glimpse into a member of the formula. We get silicon oxycarbide glass and free carbon, and it was shown a couple of years ago that we have a ratio of almost or of approximately 3 when a molar ratio of approximately 3 when analyzing silicon oxide and silicon carbide. So that means so this ratio actually is predefined in our molecular precursor. And so what is non-bonded carbon, we have also seen this in several talks, is free carbon, which might crystallize as a function of the temperature and form more or less a turbostratic carbon responsible for providing electric conductivity. And last but not least, here we see that we have a strong correlation of the carbon content in the polymer versus the carbon content in the ceramic residue. So that means we stay at this relation here, at this ratio, almost something like 3. And so the carbon content actually increases, the free carbon content increases with the carbon content in the polymer. Last but not least, for those of you who are not experienced with loading those materials with particulate fillers, actually what happens during pyrolysis, so this is a nightmare for everybody who is trying to actually generate parts. So we get porosity and cracks or even shrinkage, which might be up to 80% in volume. And to compensate this shrinkage, actually we can add fillers, particulate fillers, and here they are addressed as inert or even as reactive fillers, depending on their reactivity between fillers, ceramic residue, fillers, pyrolysis atmosphere, and so on. And with the fillers, actually, you can dilute these nasty effects here, the porosity formation, the unwanted porosity formation, or you can actually overcompensate this and can actually have a part which is near net shape. Moreover, you can tailor, you can imagine this, you can tailor a wide range of properties as a function of the filler addition and the pyrolysis atmosphere, pyrolysis parameters, temperature, and so on. And we will hearing a talk tomorrow, which today, I'm sorry, not tomorrow. We're hearing a talk in the afternoon which will deal with particulate fillers with a negative thermal expansion and which actually leads to a NTE or a very low CTE in PDC tapes. Okay, so far some introductory remarks dealing with basics of the polysilazanes, and we will be coming now to some more processing related stuff. So I have skipped the microstructure because of it's too short the time today. Actually, this is a scheme which tells you the entire story. We have the shaping processes. We can apply plastic shaping technologies. We have the cross-linking here as shown in one of the first slides, which can be processed by several means of functionalities. So this is overlapped, and then we have the pyrolysis where we can control the microstructure in a very wide range. Actually, so the thing is that cross-linking and shaping actually needs a lot of attention in order to be correlated actually with the structures and the resulting materials as well as the surface properties of the materials. So here we have a short glimpse into a viscosity shear rate diagram. We have here the shear rate versus viscosity of a polysiloxane, methyl polysiloxane at 90 degrees C at different shear rates. You see we have a shear thinning behavior. We have it here also at 90 degrees C with a little buried composition. Here without, here with fillers. You see that fillers act as a viscosity modifier in this context. However, what we learned from this, actually we can use this for estimating which process can we apply for shaping. And in this context here, we are in the processing window for extrusion, for injection molding, for melt compounding, and so on. And when we are able to modify our viscosity with liquids, with solvents, then we have this curve of the viscosity versus shear rate, and actually here again we have a shear thinning behavior, which is very important if you add fillers that you avoid filler sedimentation. However, fillers are necessary to compensate shrinkage, to modify actually or to tailor desired properties. So in this context, so here we have seen this is the viscosity only, and the next slide shows us how important the cross-linking is. We see here on the left coordinate the viscosity versus shear rate, on the right coordinate and the upper part. Actually, we have the cross-linking behavior as a function of the temperature. So we have the shear rate, the viscosity actually, and the shear rate here on the red curve. The viscosity actually increases, decreases first, and then with increasing temperature, the viscosity increases. So this points out that we have the cross-linking process here triggered by temperature. And actually here we need more correlations between those processes here and the resulting ceramic materials. Next slide shows how we can apply this behavior. We have two processes here as an example. We have the tape casting, we have centrifugal casting. And so both in common is that we generate planar, however, in this case, bended planar structures, but we rely on the viscosity shear rate function that we have shear thinning. So shear thinning actually avoids after the viscosity or after the shear rate decreases that we have a viscosity increase, and this actually avoids the sedimentation of fillers. And as said, this can be done for centrifugal casting and tape casting, and this is shown. Actually, examples will be followed. So next issue is the solubility of pre-ceramic polymers. So when processing in a fluid state, in a liquid state, and for this you have to know what is the solubility of the pre-ceramic polymer in which solvent, which actually is used. And in this sense, actually, there were a great number of measurements. So this table actually starts here, and it might end somewhere here. Maybe 30 or 35 solvents have been investigated, and then it has been defined. So the Hansen solubility parameter. So what is within this sphere here is a solvent for a given pre-ceramic polymer, and what is out of this sphere is a non-solvent. So that means the non-solvent actually influences also the solubility, and if we mix two polymers with two different types of solubility, actually we can trigger the demixing of the polymer, of the two polymers, and this may result in structures which can't be obtained from other methods as from those demixing processes. So actually here you see the unique methods of, or the unique thing leading to those structures which can't be obtained by other processes, and I come to these structures. So these are structures from those demixing processes. Here we have the different compositions. We have silane, we have methanol as different solvents, and non-solvents. We have two different pre-ceramic polymers, and you see those very nice structures having those holes. The question is, what can you do with it? Actually, we have an enlargement of our surface area, but when adding fillers, you get those very nice net-like, grid-like structures. And those structures, actually, as a coating, might be useful for loading with catalytic active components or so on. You can make catalysis on surfaces. So it is not designed for a specific application here. It is to show that those processes work, and you never will obtain ceramics from other processes, from demixing as we have it here. Next shows some results from tape casting. So on the left-hand side, we have a tape, a polymer-derived ceramic tape, pyrolyzed at 1600 degrees C. We have no warpage. We have a shrinkage of between 5 to 15%. So the flexural strength is moderate to high with respect to the porosity, and it can be scaled up to a size, say, a little bit larger than an A4, maybe an A3 sheet of paper. And those tapes actually can also be used for making those lightweight structures. Here we have a corrugation, corrugated tape formed by tape casting, and here we have it attached to a face sheet, and with this actually we have a high temperature lightweight material. And so the same is here. You can also use polysilazanes, can foam it, can convert it into PDC foams, and here actually we have applied face sheets on top and on the bottom with a binder consisting of a pre-ceramic slurry, and we have it co-fired and received this lightweight core structure with 2 face sheets. Actually, a very nice mean to control porosity is to, was it the bell? Yes. Oh, I speed up. To control porosity is to fire at high temperatures. Now you see it here, 1350, 1500. It is a mixture of silicon and silicon carbide, what was given into the system as fillers. And from this, actually firing at high temperatures, we have different porosities. You see it here. We can control the pore diameter as well the porosity. And so this is because of several reactions we have. We have carbothermal reactions, disproportionation, synproportionation as pore forming reactions. We have the material forming reactions here, the silicon carbide formation when firing in nitrogen. We have the silicon oxycarbide nitration, oxynitride formation, and from this actually we can have a high temperature stable material which consists only of these both components. And this can be used for host material, as a host for crystallization of zeolites. And here you see that the porosity as well, the composition actually can be used for the control of the zeolitic morphology. Here it is the MFI5 structure, the silicate 1. Last but not least, we can use it for foaming. And our last results on this is using PDC or making PDC foams by the combination of freeze casting and reticulated foaming. And this gave these very nice open structures with galleries here and access to the inner part of the struts. So I may conclude. We have seen that there is a great variety of processing means when having polysilazanes. We have a wide availability, a wide range of compositions of those materials. We have several cross-linking mechanisms. We can use solvents and fillers. However, we have to understand more the interaction between solvents and the material itself. And actually, we have access to parts which we would not have with other means of processing, for instance, the demixing structures. So, however, we have some disadvantages. It is the oxygen content in the polymers, but here we have to distinguish between pyrolysis below 1200 and far above 1200. And in my opinion, we have to spend more time on this state in between, say, at comparatively low pyrolysis temperatures. So we have heard talks yesterday with some shifting in the properties when hydrogen is absorbed and so on. And here we have to make it more clear. And when pyrolyzing at 1600 in nitrogen, actually you have seen that we can generate a real high temperature material. So far I may have a last sentence, so something like it looks that we have a real low-cost opportunity for ceramic processing, and so the charming thing is that we can obtain parts we never would obtain with other means, as with pre-ceramic polymers and with a polymer shaping. Thanks.
First of all, thank you very much, Michael. Just want to know that what kind of solvent you are using for tip cast, to develop the tip cast slurry? Is it, and just to know that it is it the, whether you are using PDC for the stream or it is the PDC modified, you have some master batch, you added some PDC into that, and that you are using for tip casting.
So for tape casting, the master batch actually consists of a polysilazanes. We have filled it with silicon and silicon carbide in order to get a high temperature, stable material. And so the viscosity modification, in order to have a low viscosity, to have shear thinning, we have modified this with methyl-free ethoxysilane, with a monomeric silane. So this gives you this.
And what kind of solvent you are using that is compatible with both the master batch as well as, or PDC, as well as it is effective to disperse the?
So actually the silanes are highly compatible with this. And if you shift to methanol also, you have to investigate the range of solubility. Okay.
Thank you.
Very nice talk, Michel. Maybe my question is stupid, but you mentioned that some of the polymer display a cage type structure, right? Is there any interest to store some gas inside or capture some gas inside?
No, so this is the structure of the pre-ceramic polymer, of the silicone.
Yeah.
So I have no idea if this is possible. So
Okay.
I guess this has never been investigated, but might be a good idea to stiffen the material and to try to.
Yeah, because they are stable in air, such polymers, right?
Yeah.
Okay. Yeah, maybe.
Okay, last question. We are running out of time. Already we are 30 minutes delayed.
Yeah, nice work. I appreciate. You showed some viscosity decreased and then increased with increase in the temperature, right? And you said some cross-linking. Is there some special mechanism for this cross-linking that actually showed?
So actually the cross-linking.
Again, increasing of viscosity, that is.
So the increase of viscosity as function of temperature depends on the cross-linking mechanism. So when cross-linking with OH groups, when having the condensation cross-linking, actually we can assist this, or we can trigger this either with the temperature, or we can assist this with some catalyst. So aluminum acetyl acetonate may be used for cross-linking in this specific thing, but temperature also helps.
He was asking, with the shear rate you have shown, the viscosity was, in one case, viscosity was going up with shear rate,
Yep.
with the same with the constant temperature. So he's asking for that, whether
okay.
any special mechanism for that.
So when having constant temperature, actually you need more catalyst. So this is a problem. And the catalyst, aluminum acetyl acetonate, actually you introduce aluminum, and so if this is desired, it is okay. But if it is a residue which is undesired, actually then cross-linking might be better to trigger this by higher temperatures.
I have two questions. I have liberty for asking that. Yeah, this flexure strength you have shown is about 100 MPa with the porosity with the 10 to 35% of porosity. So is there any mechanism to reduce the porosity further to enhance the mechanical strength?
So actually we can do an infiltration process.
So that if the powder, if you increase the powder percentage, the filler, so that the processing, any challenges are there?
Yeah, so the challenge is when the filler load is higher, then actually the viscosity is higher
So
as
that's
well.
why I'm asking, whether any limit is there, that beyond that porosity cannot be, that you cannot control beyond that?
So actually we can control it in a small window. But so if it is needed, infiltration might be useful for eliminating porosity.
Okay, thank you. Thank you for this.
I would now request Dr. Suresh Kumar to present the memento to Dr. Michael Schaeffler.
Thank you. Thanks.
So we have a second talk from Dr. Jürgen Mertes. So he'll be, I think he is heading printing chemicals, Merck, Germany, and he will be talking about the polysilazane properties and commercial applications. I think this will be very interesting to many of our industry partners, in which way the polysilazane can be used for the industrial applications. I invite Dr. Morgan to give his talk. Thank you.
Sure? No, it doesn't work. No, it works. Good. Yes, thank you for the invitation to speak here. Thanks to Ravi and thanks to Günther. And it's really a great pleasure to be here in such an audience with so many experts in ceramics. I have to admit I'm not an expert in ceramics. I'm more or less an expert in coatings and maybe polysilazanes, but ceramic is a pretty new field for me. And I was really impressed to see how many works are done with the polysilazanes in conjunction with ceramics. And I hope that we can, let's say, do a good business also in future and support the business from the Merck side, because there's a lot of potential for the future. So many new applications, new routes. I think about these additive manufacturing, the electrodes, and also the lectures we saw this morning. So very, very nice. Thank you for that. So before we come to the polysilazanes, I would like to start with a short introduction of Merck. Merck is a company which is 345 years old, one of the oldest companies in Germany, still operating. It's family-owned. 70% is family-owned. 30% is on stock. And the family is looking for the next 350 years. So you can see this is not a short-term activity. It's a very, let's say, future-oriented family behind who really seeks and tries to keep the company running. We have roughly 64,000 employees. We are very international, so the employees coming from 139 nations. And the revenue last year was 22.2 billion euros, which is just a nice coincidence. 2022, 22.2 billion. And the target for 25 is 25 billion. So that's very clear communicated. So not all people are working on polysilazanes, unfortunately. So only a small part is dealing with polysilazanes, and polysilazanes is part of the chemical business, which is summarized under the electronics business unit. And the electronics business unit is a very interesting business unit, not only dealing with the PHPS, but also dealing with materials used in the production of chips, like polymers, like anti-reflective coatings, and so on. So this is one of the major activity in the chemical field of Merck. And if you're using a mobile phone, if you're using a laptop or computer, often you see the sign there's Intel inside, but not only Intel, it's also Merck inside. But we are not allowed to put the sticker on every computer, for example. So we are enabling, and this is the same with the polysilazanes. And polysilazanes, they have an interesting history. As you can see here on the left hand, it was first, let's say, invented or seen by Rochow in 1921. And it was just seen as a lab curiosity. They took some chlorosilazanes and reacted with ammonia. And they saw, okay, there's something coming out. It looks like a polymer, but no use of it because it's not stable, it's reacting, so get rid of it. And even in 1966, Rochow stated for the organic polysilazanes, the only conclusion possible at this time is that polysilazanes have no use. Interesting, isn't it? We are talking about polysilazanes now, and just have a question here on the table. can you really imagine that the polysilazanes have a future and you can make money out of this? I guess at the end of the presentation, we can all answer the question here, and we can have a short poll, and I guess 99.9% will say yes. Okay, history for the polysilazanes. Starting with 1999, Clariant was the first company who really tried to make a huge business out of polysilazanes. And the business was sold to Clariant in 1999. And this was mainly for the inorganic polysilazanes. Because the inorganic polysilazanes at that time were already used mainly in the electronic industry, the AZ Electronic Materials company bought that part from Clariant and integrated that into their portfolio. And Clariant, on the other hand side, bought the organic polysilazane from Kion in 2006, and that came to AZ Electronic Materials in 2011. So everything was combined in the AZ Electronic Materials company. And what happens? In 2014, Merck came to AZ and said, okay, you're a nice company, interesting materials, fits very well with our chemicals we are already producing, and they bought and acquired AZ Electronic Materials, and that's the reason why I'm now here under the label of Merck. Honestly, I was also with the electronic materials before and had also some contacts with the polysilazanes. So Merck and polysilazanes, it's a very unique story because it's kind of island within a huge company. Island means we are more or less the only producer of inorganic and organic polysilazanes in the world. Market share is tremendously high. There are some small competitors. We have nice growth rates. We are expecting year-by-year growth rates of about 10%, which is nice business. We see and we believe in those materials because we see these outstanding properties of the polysilazanes, scratch resistance, heat resistance, and so on. I will come to that later on. And as I said already yesterday, it's a nice coincidence that we are here in India. We are producing the material, the organic polysilazanes, exclusively in India. We have to distinguish between the two groups of polysilazanes. So I guess we already heard it before. We have this PHPS material, which is the inorganic part, only consisting of Si and N and H atoms. And we have the organopolysilazanes. And you see the wrong button. This one. And you see the structures here on the bottom. These are the three elements which will be combined then to the different grades of the organic polysilazanes. Sometimes, as if you think about polymers, you have in mind that this is a straight line of organic materials. In this case, we expect and we believe that these are complex structures of different ring materials. 4 rings, 8 rings, 6 rings. So pretty much complex. All these materials are very easy available. So we are producing this in tons, and not only in 10 tons, but even 100 tons. So if you are really seeking and looking for those materials, it's easy to contact us and get material. You can easily buy it. I think the curing mechanism, many people of you spoke about already about the curing mechanism. The main point is the PHPS is very reactive. It reacts mainly under ambient conditions, so with water vapor to SiO2. If you have an oxygen-free atmosphere, you can go to the silicon nitride. With the organic silazanes, it's a similar route, but you have then this carbon content, which is still in the material, or it's partly hydrolyzed. So 2 different materials, 2 different routes. Before I come to the application and the differences, I would like to show you this nice picture. This is the production site in Kopoli, where we are producing the organic materials. This site was founded by Clariant. And what is really exceptional is that 80% of the staff is already longer than 10 years in the company and dealing with polysilazanes. So that makes it a very easy operation. People know what they are doing. For the inorganic polysilazanes, actually we have 2 production sites. The main production site is in Japan. Why Japan? Because Japan is close to our customers in the electronic business. And we have one small site in Wiesbaden, which will be closed by end of 2024, and everything will shift to Japan then. Applications, I would make a difference between the PHBS applications and the OPSC applications. And by far, the most important application for the polysilazanes, for the inorganic polysilazanes, is electronic fields. As you can see here, this one. As you can see here, the gaps in the chips are going very, very small, and in some cases they are even lower than 5 nanometers. So the Apple M2, for example, is a 5 nanometer chip, and you have to fill the gaps completely up to the ground, and that's a challenge. As you can see in the next three pictures on the right-hand side, there are 2 competitive technologies, the CVD processes, and you can easily see that the dielectricum is not really going to the base, to the ground. Only with the PHBS you are able to fill the gaps completely. And that's the main benefit, and this is because the PHBS is a very, very low viscous material. It fills the gap instantaneously. And the challenge here is, and that's also why, let's say, the production costs are pretty high. You have to assure that these electronic processes are running always at the same process, so there are no variations possible. And even the materials you are applying in the chemistry to be very, very constant and reproducible. And that's a challenge, and that also makes a price. Another application for the inorganic polysilazanes are barrier films for flexible substrates, like displays, like photovoltaic, OLED lighting, because even very thin polysilazane, inorganic polysilazane coatings are very flexible. So as I said, at the end, you are receiving an SiO2 layer, which is more or less glass. Glass is brittle, we all know. But if you're going down to 100 nanometers, then these coatings become very flexible. So that's the reason why we can also use, or our customers using inorganic polysilazanes for such kind of applications. Another point is really the flattening of the surface. Flattening of the surface is pretty important. If you think about voltaic cells, photovoltaic cells, if you have a rough surface, you have a lot of, let's say, reflections which are not giving the right properties or not the right energy to the cells itself. And here you can really smoothen out the surface. And you see here, just with a very thin layer of about, it's 100 nanometers, you can flatten out this CVD process material from 13 nanometer roughness to less than 2, roughly 1 nanometer, which is a very good thing. And also here, the encapsulation of photovoltaic cells. This is also a, let's say, technical application already. We have some companies in Europe who are using this for this kind of application. The organic polysilazanes, they have a much broader range of application. And honestly, this summary is far away from being complete. This is just a selection we see as a vendor of the raw material. We never deliver the material directly to the end user because normally the end users are always looking for formulation. That means doing some additives in there, some surfactants, whatever is necessary, some fillers. And just some headlines here to give you a flavor where we are. We are in automotive. Automotive is everybody thinks, okay, this is a easy to apply material, and it's not a rocket science area. But automotive is one of the biggest markets we have for the organic polysilazanes. So the nano materials are mainly consisting of polysilazanes. Transportation is another point. I come to that later, and industrial. And here are the headlines according to the properties of the material. So we have this high temperature stability. We have the water-dirt repellency. We have scratch protections, and we have corrosion prevention. And here are some nice examples where you can see also how good the material is. So we have here some pictures for the scratch resistance. We have the polysilazanes compared with siloxanes and fluoropolymers. And when we are talking about the gloss retention, that means 100% gloss retention is no attack. So we have croc meter going 50 times, 100 times with a certain weight above the surface. And with the polysilazanes, you see nothing after that. With the siloxane, the gloss retention is 71%, but even here you can see on the picture, there is already an effect. And with the fluoropolymer, we are pretty bad with only 51%. A huge application is the so-called easy-to-clean anti-graffiti application. When you travel around the world, you see buses and trains full of graffiti spraying, and it's damn difficult to get rid of it. It requires a lot of harsh chemicals and mechanical interactions to remove the graffitis. And here what you see maybe as a first eye catcher is this panel, this metal panel, and there's a permanent pen going from left to the right, and the right-hand side is coated with polysilazane. And you can see that the material do not stick to the metal, and you can use a dry cloth and just remove the material very easily from the surface. And that's one of the benefits the Deutsche Bahn is taking, let's say, benefits from. You see the old coach, even the changing color is very obvious because the surface is flattened. And the surface is protected against graffiti. And there is a new evaluation. Everybody wants to get greener and more sustainable. Also, Deutsche Bahn is looking for that. Because currently, the process is not as easy as shown on the right-hand side. Here, till of today, you have to use certain chemicals to remove graffitis. And they want to get rid of this. And we developed, together with a partner, a formulation which gives an even better cleaning of the surfaces. And we are very close to the picture on the right-hand side, just using pressurized water to remove the graffiti completely. But not only from the steel, but also from the glass. It's very nice. Corrosion, everybody wants to protect surfaces, and corrosion is one of the biggest enemies for surfaces. And here are some tests showing that the polysilazanes are not so much superior, but comparable in corrosion protection properties. This is important if you combine, let's say, the demands of anti-corrosion and easy-to-clean properties. So this is a combination of both. Thermal barrier. Yes, ceramics. Huh? I guess you know more about that than me. But this is just also eye catcher and a diagram showing the high stability of the polysilazanes compared to the siloxanes and the fluoropolymers. Because in many applications, siloxanes are still the standard materials for heat-stable coatings, but the polysilazanes are superior. And just having in mind, polysilazanes are coated on a very thin coating. So maybe the thickness is 1 micron or less. And with the fluoropolymers and the siloxanes, you have 20, 30, 50 microns. That's important for applications when you're weight sensitive, like airplanes. Every gram is 1 gram too much. So they're always looking for very thin coatings, which gives the right properties of the surface. I guess Günther know that much more better than me, but this was exhaust pipes just coated with polysilazanes. I guess inorganic on the outer wall, inorganic in the inner, and then an additional organic polysilazanes on the inner sphere, and treated at 1000 degrees C for 1 hour under oxygen. And you see the difference afterwards. The pipe, coated with the PHPS looks like brand new, where the uncoated one looks pretty ugly. Additive manufacturing, okay. This is a pretty new publication, I guess still in press. They are using Durazane 1500, the unreactive part of the Durazane family. So 1800 I heard many, many times, but 1500 is the one without the vinyl groups. And they put some monomers into the mixture, some initiators and fillers, and they produce these nice parts. And after pyrolysis, you have this ceramic parts. And fillers are necessary, and I guess we heard it also many times, to get a more stable structure. I come to my end, that's good. Here we see just a short comparison between the different materials, polysilazanes, siloxanes, and fluoropolymers, polymers. And the main benefit here is the water contact angle that corresponds to the easy-to-clean anti-graffiti properties. You have a very high scratch resistance, which is good for the automotive industry. Pencil hardness for the organics is maximum 5H. For the inorganics, we can go up to 9H. So very, very rigid coatings like glass. We have a good stain repellency and a stain removal. And just at a glance, in a nutshell, if you compare the polysilazanes in coatings with other materials, you see that they are all beneficial in mostly all regards and all applications. We can trigger also and tweak the properties of the material by changing the chemistry of the polysilazanes if necessary and if feasible. A lot of coating applications. We are doing architecture. We are doing, as I said, cars. We are in the airplane industry. So that's very interesting. And honestly, I also believe in the future. And looking forward, what do we have in mind? So one is anti-fouling. You know that the marine coatings are under discussion because of microplastics. So this could be also an interesting field for the Durazane and polysilazane materials due to the durability of the material, the coatings. And we have the additive manufacturing, and also driven by the pandemic situation, the antiviral, antibacterial coatings. And last but not least, I would like to say thank you for your attention.
Thank you for an excellent presentation. We'll have 2-3 quick questions. Okay, so I have one question. This application you have shown, so what are the cost for these polysilazanes, and what are the packing size which are available for that normal cell?
We have these pH-based materials, which are commercially available, and the organic ones. And for the organic ones, we have this Durazane 1800 with the vinyl groups, and we have the 1500 with the methyl groups. So these are the standard grades we have. And then we have these pure compounds, which you can mix according to your needs. This is, let's say, special request. But because the company is in India, we are pretty flexible to do some, let's say, also special mixtures.
Okay, thank you.
And they are available. Yeah.
And now request Dr. Suresh Kumar.
We have one more question, so please.
Thank you. Just a question about the anti-fouling you mentioned at the end. For what kind of membrane or application, for water or for air filtrations?
The main focus is on marine coatings, on boats. So for salt water. Mm-hmm.
Okay. And this is for like coating for ceramic supports. Okay.
It's really the outer sphere of the boat to protect them from getting biomaterials stick on, but also prevent the material to degrade in the water. Because the microplastic comes from abrasion of the water towards the boats. And we believe that could be beneficial for using the durazanes.
Okay, thank you.
Welcome.
Thank you.
And now request Dr. Suresh Kumar to hand over the memento to Dr. Jürgen Martes.
Okay, thank you. In the back.
So we have a third talk from a very young startup CEO. So Mr. Dr. Ganesh Babu, he is a founder and CEO of Sira Tetwa Innotech Private Limited. And then we'll be very happy to listen him. And then I think that he has made several new compositions, first time in the country, and it will be very beneficial to all of us. So we welcome Dr. Ganesh Babu for his presentation.
Am I audible? Yeah. Hello everyone. Very good morning to all. And thank you, sir, for your kind introduction. I take this opportunity to take you all through the Sira Tetwa's journey, where I'll be explaining in a couple of minutes about our motivation, the reason for starting this company, and the vision what we have for this company, and also what is that we offer for the ceramics stakeholders. So Sira Tetwa Innotech focuses on the development of non-oxide ceramics materials, and we produce these non-oxide ceramics materials through polymer-derived ceramic route. And we have incorporated our company at IIT Research Park, and we founded our company at last year, April 2022. So please allow me to give you a few interesting aspects of space sector and defense sector. So in the case of space sector, if you take, every year we launch almost 180 of launches are made all over the world. And what about the 10,500 tons of space debris, which is already there in the space environment? And do you know what is the reason for this? And the reason for this is it is all one-time usable launch vehicles. And in the case of defense sector, if you take, and the world's lightest battle tank, what we have in the world is just weighs 33 tons. And the conventional battle tank, what we have is weighing around 65 plus tons. That is a lot of compromise on the tactical mobility. And this all happens because of the choice of materials. And what is the solution? The solution is that the material should have a high strength and high temperature capability, and should also have a light weight. Do we have such material? Yes, we have such material. This implies that now it is possible to make a reusable launch vehicles, thereby the space environment become more affordable and cleaner. And also we can produce next generation battle tanks where it will be lightweight and also performs better, better ballistic performance will be achieved. So what is the material we have? Yes, it's a non-oxide ceramics material which can withstand greater than 2000 degrees centigrade, and also it is lightweight and it maintains its high strength even at high temperature. So if everything is great about non-oxide ceramics material, what is the bottleneck? The problem is achieving this non-oxide ceramics which is processable, shapeable, and multifunctional. So the current technology what we use to produce this non-oxide ceramics is a powder route which is rigidly designed, and also requires very high temperature. For example, when I say non-oxide ceramics material, immediately people will talk about silicon carbide. So if you want to produce the silicon carbide through this powder route, you require very high temperature, that is in the range of 2000 degrees centigrade. And also you require very high pressure to produce this material. And the next difficulty is the shaping of the ceramics. So for example, if you want to produce fibers using this powder route, it is very, very, very difficult. And also, if you want to produce any complex shapes, also it is very difficult. And the machinability is the next issue. For example, you cannot machine the problem because of the inherent nature of the ceramics, which is having hardness and also which is brittle in nature. So all other things, the main issue comes here is when you use this non-oxide ceramics material for strategic sectors, it comes under embargo. You cannot import to the country. So what is the solution we have? As I was saying in the previous slides, we produce this polymer-derived ceramic route to produce this non-oxide ceramics. Thereby, we can use this low-temperature processing route, where the same silicon carbide now can be produced at the temperature greater than in the range of 1200 to 1400 degrees centigrade. And it is easy to shape. And machining is very easy as like plastic. And now it is locally available. So at Saratatwa, we provide a wide range of pre-ceramic polymers. So we start, this schematic is very known in the PDC community. Yes, we supply silicon-based pre-ceramic polymers, also metal-modified silicon-based pre-ceramic polymers. And these kind of polymers are available, some of the polymers are available currently in the markets. And these kind of silicon-based pre-ceramic polymers can be used at the temperature greater than 1500 to 1600 degrees centigrade. And also it finds a vast application in the energy storage applications, where you can use it for the lithium-ion battery, anode and separators can be used as. But what we provide is beyond silicon and silicon carbide based pre-ceramic polymers at Saratatwa. So we came out with a new family which will have a non-silicon based metal modified pre-ceramic polymers. And these kind of pre-ceramic polymers will produce a ceramic called ultra high temperature ceramics. The meaning of ultra high temperature ceramics is can be used beyond 2500 degrees centigrade. And this is not commercially available worldwide. So this is what the new things we have brought in Saratatwa. So to give a small examples, one of such pre-ceramic polymers are shown here, where we produce zirconium borocarbide using boron modified polysilazanes using as a pre-ceramic polymer. And the interesting factor about this pre-ceramic polymer is that you will have a processable viscosity in the range of 200 to 250 CPS. And also it is soluble in common solvent and has very high ceramic yield. And we combined all these important properties for the pre-ceramic polymer. Along with that, you will be getting a near stoichiometric zirconium borocarbide at very low free carbon, which is very, very important to use it for the ultra high temperature applications. So to test this potential of the pre-ceramic polymer, we used as a TPS coating for the CMCs, where we ablated at 1500 degrees centigrade. And we found that the substrate is completely intact and was functional. So what else we can do with this pre-ceramic polymers? So we can produce adhesives, IGSTC based adhesives. We can also use as a coating for as a TPS and EBS coatings for the CMCs. And also we can use as a matrix resin for CMCs. So our Saratatwa non-oxide family is growing. So we have another kind of products where we produce high temperature ceramic labels. These high temperature ceramic labels are generally used for the steel industries, for mapping the billets during the processing of the steels. The currently available market, for example, the steel industry will go to a temperature of 800 to 1000 degrees centigrade. So the label should withstand that temperature. The current labels that is available in the market cannot withstand that temperature. So there was a company at Goa has approached us to develop such products where we have used this pre-ceramic polymer technology to produce such high temperature ceramic label. And you can see here, we have done a bar coating on this coating, where you can see that at different temperature the testing has been carried out, and the ceramic label was completely intact even at 800 degrees centigrade. And we have tested this material in industrial environment also. It was performing very well. So let me bring to your next domain of the Ceratattva what we does. We also provide ceramic processing instruments, and we came out with a novel instrument called ceramic fiber processing instrument, which we call it as ultraspinner. I want to ask you a question. How many of you have worked on electrospinning unit to produce fibers? Thank you. Yes, even I have also used electrospinning unit to produce nanofibers, where I found that if I want to produce a small fiber mat, let us say 50 into 50 mm square, it requires 6 hours to 8 hours to produce such small fiber mats. With the technology what we have developed, you can produce the same size of fibers in just 1 minute, which is 10,000 times having a higher production rate as compared to the existing conventional route. And also we are not applying any high voltage in the case of where we apply high voltage to produce fibers in the case of electrospinning. Here we do not apply any voltage. We use a normal voltage and to produce these fibers using centrifugal forces. And I do not want to talk more about this electrospinning unit because tomorrow there is a separate talk given by our COO, Mr. Raghunath Sharma. And I request everyone to attend that talk if this ultraspinner is more exciting to you, where he will be explaining how we can change the diameter of the fiber by changing the collector distance, by changing the RPM, how we can control the diameter. So everything will be explained by Mr. Raghunath Sharma in tomorrow's talk. Still, you people have not convinced me. So we have a stall outside where the instruments is kept there. You can all come outside and we can show you. We will be happy to show you the demonstration of the product, where you will be getting both polymer fibers and pre-ceramic polymer fibers in a blink of an eye. These are a few examples that I am showing here, where it is capable of producing both oxide fibers, non-oxide fibers, and also silicon-based oxide fibers. So this is our core team. And I am happy to show you a glimpse of awards that recognition we have received in the last 1 year. And recently we have also won Boeing 2.0, where we received a check of 10 lakhs. Sir, how much time I have?
Another 5 minutes.
Yes. This is what we do for our customers. We save time for you. So before I say thanks to you, thank you. So before I conclude my slides, I want to say only one thing to our customers. Next time when you go and stand in front of glove box and fume hood and set up your slink line for synthesizing the pre-ceramic polymers, please remember that there is one company called Ceratattva Innotech, which can tailor a pre-ceramic polymer for you people. And we say that what we do at Ceratattva, you name the ceramics, we shape the precursors. Thank you.
Thank you, Dr. Ganesh Babu. Very emotional and excited presentation. So we'll have some 2-3 questions. We have 5 minutes, so we can discuss.
Yeah, very motivating history what you have done. So I will not be talking about the technical part. I will just ask like people asked in the Shark Tank. I hope you see this series, right? Shark Tank, right?
Yes.
So I just want to ask, what is the market right now? Are you in a profit side or break-even point has been crossed?
Sir, we have started, it is 9 months old company. We could able to sell 1 kg of resin to ISRO. And then we also sold some of the resins to CMET, and we are now collaborating with CUMI Ranipet to produce some of the coatings and also CMCs. So this is where we have, and the total market is having of $340 million, if I'm right. And having a CAGR of, yes, thank you.
That's great.
And by the way, she is Dr. Abha Bharati, our company CTO.
Thank you.
Thank you, Ganesh. I could see the bright future in the startup.
Thank you.
My question is, how are you managing in procuring the raw materials required to synthesize these kind of materials? Because when it comes to real-time products, you need large quantity of materials.
See, 80% of raw materials we are procuring in India, and 20% of course we are dependent on the other side, other countries.
Dr. Ganesh, I have one question.
Yes, sir.
This several USTC precursors you have mentioned. So actually, that what is the percentage of shrinkage? Because that if shrinkage is too high in terms of the volumetric shrinkage, so that use of them and then repeated infiltration will cause a problem.
Yes.
So you have to work on that one. Yes. So the if shrinkage is in control, then only that you will be able to sell at least for CMCs.
Exactly.
Coating and extra, perhaps you may exceed. And then he has pointed out right question. This raw material, this is chain. Now that 1 kg is okay. 1 kg, 2 kg, and then tomorrow, let's say if you get order of 1 ton. So the raw material, that the supply chain also you have to ensure.
Sure, sir. Thank you, sir. Thank you, sir.
Thank you, Dr. Ganesh. Like we discussed that, means I want to know what is the time taken for, required for you to create a new precursor, like new adhesive.
Like the company has been started in 9 months old, but almost 10 years it has taken for us to optimize all these pre-ceramic polymers compositions.
Okay, like now as we discussed the conductive adhesive. So what is your timeline you can deliver? Suppose today if you take the...
If the quantity is bulk, then regularly we are purchasing, then definitely we will be able to give you in 1 week.
Okay, okay, thank you.
Yeah, one last question. You are talking about this precursor, right? Is this to produce ceramic or to produce powders for making ceramics? You're talking about 1200 to make silicon carbide. Is that the silicon carbide component
for example,
you make at
okay, sir, it can be produced, both is possible. If you take only pre-ceramic polymers and pyrolysis, you will be getting up with powder. If suppose you are converting it to a component in the green stage level, then you can, when you heat treat that in the pyrolysis condition, then you will be getting the component. So both is possible. Sure. Fully dense, then we have to go to high temperature. Then this density will increase.
Okay, thank you again, Dr. Ganesh.
And now request Dr. Suresh Kumar to give the moment to Dr. Ganesh Babu.
Now I invite this our next speaker, Mr. Kaushik. He's a young researcher, and then he will be talking about the temperature and compositional dependent phase stability of precursor derived ceramics, nanocomposites. So I think he's doing research at this IIT Madras.
This is mic after you. Hello, am I audible?
So, good afternoon everyone. So today I am going to present on a topic temperature and compositional dependent phase stability of precursor derived high entropy carbide in SiO2 matrix ceramic nanocomposites. So this work was done in cooperation with TU Darmstadt This was done in the past 2 years. So this is the brief outline of my talk. So coming to transition metal carbides. So the transition metal carbides have high melting point as well as high hardness. So this helps in applications like making cutting tools, wear resistant parts, and also few aerospace applications. Also transition metal carbides were recently being used, starting from actually work by Levy and Bodart in 1973. They were reported as platinum equivalent catalysts for certain applications. So from then the research has been continuously progressing regarding transition metal carbides. However, the conventional routes have cannot be synthesized with high surface area because of in the solid state synthesis it is difficult to produce high surface area. So, but through PDC nanocomposite route, there is a possibility to obtain nanocrystallites without agglomeration. Also, so you can also obtain tunable porosity with varying specific surface area as per the requirement, and also there is a control on electronic conductivity of the material, because in the PDCs we have a free carbon in the matrix as shown here, which helps in obtaining electronic conductivity. So the amount of carbon, actually by varying the amount of carbon we can actually decide the change the electronic conductivity of the material, which is important in especially in electrocatalysis applications. So here you can see the PDC nanocomposites are usually can be produced by using metal organic precursors and mixing with polymer precursor and further pyrolyzed to obtain PDC nanocomposites. So in a work by Emmanuel Ionescu and co-workers, it has been shown that they have actually with metal modified silicon oxycarbides, they have beautifully shown on all the elements in the periodic table, like how they phase formation and stability happens in SiOC based ceramic nanocomposites. So here it can be seen that the elements marked in red. So for these materials, so because of the presence of oxide environment in the silicon oxycarbide matrix, so the metal has oxygen bonding, but in the red elements marked in red, it is actually the presence of carbon can actually cause carbothermal reduction. But in the case of red marked elements, it is thermodynamically not possible to have carbothermal reduction. However, for the elements marked in blue, the carbothermal reduction takes place. So this carbothermal reduction actually decides which metallic compound is evolving in the material. So the stability of the in situ crystallized phase depends mainly on this carbothermal reduction, and also the further stability after the carbothermal reduction or the oxide phase within the SiOC matrix. So coming to transition metal carbides, and so few people have attempted to synthesize tungsten and molybdenum, and also we have worked on vanadium based materials. So to synthesize carbides in the SiOC matrix, but here it was obtained that in tungsten it can form tungsten different types of carbides, and in molybdenum it is forming molybdenum silicide carbide, and in the case of vanadium it is forming vanadium carbide. But these three materials are actually well reported as catalytic materials, but there is further possibility to actually not only restrict to these few materials, but we can also increase the combination of these materials by actually making ternary carbides or quaternary carbides and so on. So, but the main difficulty here is the stabilization of ternary and quaternary phases. It is difficult within the SiOC matrix, and it is more complicated. So how can we increase the stability of such formation of such phases? To decrease the delta G, we actually increase the entropy. So by increasing the entropy, we can actually stabilize the phase and also obtain desired ceramics. So the main objective of this work is to synthesize a high entropy carbide within SiOC matrix. I have chosen these elements as a starting. And also the objective of this study is to how the stability will affect with the change in composition as well as temperature. So this is the synthesis method I have adopted. So here I have taken SPR684 precursor, and I have mixed 5 different types of metal based precursors along with polystyrene. Here polystyrene I have used as a porogen to create more surface area. So further after stirring and removing the solvent after the reaction, we have obtained a precursor, and this precursor was further pyrolyzed and also heat treated at various temperatures. Here I have chosen 3 different weight ratios between SPR684 and metallic precursors. So I have maintained 38%, 48% and 58% to observe the effect of composition. So first I have characterized the precursor. So here you can see SPR684 5M, here says the 5 metallic precursors I have mixed, and here it is the bare precursor. So here I have observed after mixing of the precursors, there is a formation of SiOM type bonds. There is actually a formation of small bonds here, small peaks with corresponding to SiOM type of bonds, which confirms the formation of precursor. So further in the XRT we have observed at various temperatures, we have observed the formation of a single phase and also a high specific surface area. So through TEM scanning the transmission electron microscope analysis, we have actually obtained confirmed the formation of high entropy carbide phase. So here you can see the elemental distribution of various elements. So wherever the formation of the crystallite, you can see the presence of all the 5 elements. Also in addition, we have observed that there is also a presence of concentration of silicon in the high entropy phase. So which says that there is also a plausible incorporation of silicon into this high entropy carbide phase. So further, to understand the stability of these phases with respect to composition, we have actually changed the composition from to 40 and 58% of the metallic precursors. So here we can see at 58% there is a change in there is a phase separation with when we went to 58% at 1400 degrees centigrade, and here we can see there is a clear peak shift when there is an phase separation, which indicates there is a phase separation instead of formation of a new phase. The existing phase has separated. So the carbide phase also has actually the peak shifted. So some elements in the high entropy phase has actually separated. So to observe also the effect of heating rate, we have we did very fast cooling of this heat treated material, and here also we observed that at 58% there is a phase separation, but here we have observed there is a formation of metal silicide carbide phase instead of metal silicide phase. So by this we actually deduce that the metal carbide is separating into metal carbide plus metal silicide carbide, and further it is this metal silicide carbide is further converting into metal silicide. So to understand why the phase separation is happening, so we did Raman spectroscopy, and we observed that there is a depletion of carbon, and there is no carbon present in the phase separated material, so which indicates that the carbon deficiency could have formed carbon vacancies in the high entropy phase, so which would have resulted to the phase separation. And I conclude by saying that we have successfully synthesized high entropy carbide in a SAOC matrix. And here we can see we have obtained a very high surface area. Also, we observed that the presence of silicon in the high entropy carbide phase, and the carbon vacancies resulted from the deficiency of carbon resulted in phase separation. So I acknowledge my group, high performance ceramics group and dispersive Westhofe group from TU Darmstadt, and also I acknowledge Ernst Ruska Center for Microscopy and Spectroscopy with for the TEM measurements. Thank you.
Thank you, Kaushik, for excellent presentation. So only one question.
Yeah, wonderful presentation. My doubt is already tungsten carbide has been a transition element and which has been used as a tool material. So what's the difference between the manufacturing of that and this? That was manufactured using sintering process, and what's the advantage in this actually by using a high entropy carbon?
So in case of this high entropy carbide, it was it was not part of my work, but previously it was shown that high entropy carbide actually showed more hardness compared to tungsten carbide also. And also in this case, we are mostly concentrating on catalysis. So in case of catalysis, actually through solid state route, it is difficult to get high surface area. So here we are getting high surface area. That is the only.
Yeah, okay. In addition, I have one more question. When the entropy is high, there's a high chance of material failure, right? Like how will it happen in your case?
Failure in
like in the normal tungsten carbide manufactured using sintering process, now we are not using it and we have changed into cubic boron nitride and etc. Due to the easy metal tool failure and wear resistance. Now in your case, when the entropy of the carbon itself is high, there's a chance of tool wear, like say for example tungsten carbide is used as a tool for machining process. So how can we solve that? Will that problem occur in your case for a high entropy transition element carbides?
I haven't actually much studied about this structural properties for these materials, but I have to. I
think this is an interesting question. You can discuss further in that lunch time.
Yeah. Okay. Thank you.
I would now request Dr. Suresh Kumar to present the memento to Mr. Kaushik Papagalu.
Thank you. Thank you.
So we are coming to the end of the session. Last presentation is we'll invite Mr. P. Arivagan, and he will be making presentation on synthesis and functional properties of multi-component high entropy. Again, this high entropy material has come. So he is also from IIT Madras. It is a very good topic, it seems.
So good afternoon, everyone. All are you in angry mode? I don't want to make you in angry mode to take a long time. So I short my talk in every quick shot. So my topic on this synthesis and functional properties of multi-component high entropy spinel nanoparticles. My overview of a talk, introduction and background and objectives, and how I carried out the experimental work and some significant results and conclusions. So the introductions talking about the spinel ferrites, it's have an AB2 structure consists of cubic rows packed with anions. So normally have four categories. Depends if you can consider the general formula. That formula. So it depends, and M2 minus 1 minus x, F3 is x, and M2 plus F3 plus 2 minus x in octagonal. That's so. X is the inversion parameter. That is the important quantification distribution to the M2 plus and F3 plus ion in whether the ions will, cations will be in a tetrahedral and octagonal sides. Depends upon the x values. You can categorize the 4 categories. If it is x value is 0, it is a normal spinel. X equal, if it is 1 is inverse spinel. If x equal to by 3 is a randomized spinel. And x between x the 0 to x is called mixed or partially inverse spinels. So in the spinel spheroids have a natural abundance and low cost protections. So there and some structural, electrical and optical magnetic properties. These are the applications of data storage, catalysts, sensors, ferrofluids, or etc. etc. So my background of is taken off the spinel spheroids is basically the properties depends upon the exact stoichiometry and inversion parameter, and that achieving this inversion parameter achieved by the control parameter, that is the synthetic parameters. These all conclude with bulk material. While go to this now, so the whole are totally changed because of that large surface to volume ratio. The inversion parameter is also varying, and accordingly the electrical, magnetic, optical properties also varying. So my talk is about, as I have taken an account of this background. I started with the synthesis of spinel from ternary to high entropy spinel oxides from using this plane spray pyrolysis technique, and the structure and functional properties are characterized. So these are the experimental flow works. I have taken the nitride precursors and is 1 molarity solutions with of 60 ml DNS water, just nitride precursor, DNS water. And this is all the reaction flow meters as a liquid petroleum gas I use as a heat flame of 20 SCCM and oxygen fluoride for oxidizer and 50 SLM. These are the composition we are synthesizing in single step reactions, the single step parameters. And these are the flame spray pyrolysis taken ultrasonic nebulizers. It's like in hospitals you use in ultrasonic for making, right? That ultrasonic nebulizers we are taking for creating the nebulizer precursor particles and create the chamber is in there, and we collect the sample in a single shot. So these are the achieved results of this. Every synthesized particles are in a single phase. It is with a space group of FD about 3m. There is no secondary stress in these samples. So radial refinement constant and occupancy factors is all mixed spinel structures. And FDR also confirmed these are there's 2 distinct observed bands near 600 and 600 for tetrahedral and 400 for characteristic of octagonal sites. And HSM confirmed that the particles are ultra fine size under the 25 to 50 nanometers, and EDAX analysis we have that the narrow distributions of some have little bit varying, but we confirm with the narrow distribution of the TM measurements also confirm this is the distributions are the 5 to 50 nanometer, and the SAT pattern is high crystalline nature, which is very, very important because we don't need that particles to the post crystallization. Okay, this is a single shot. And this is about with the DRS UV SPAT mechanism, you can vary the band gap between from 1.1 to 1.9 electron EV volt. All the materials with the direct band gap material and optical band gap with 1.1 to 1.9 electron volt. And magnetic is giving that the distributions of magnetic saturation is they have a narrow loop at a small amount of dissipate of energy, repeatedly investing the magnetization. So you can use the electrical applications like motor cores or transformer cores. You can use it. So after that, we have to check for the electrical properties also. We have taken the 3 samples that are right considering sorry. So 3 samples for taking the samples for spark plasma sintering and pelletized, and to do the current measurements, IV measurements, we have the resistivity of nearly all in the resistivity 6,000 and 2,000, nearly at 4,000. So this material exhibits you can see in the range of semiconductor region. And all measurements also confirm some have a mobility region. So it has, and the 3rd sample have without copper is a high electron concentration with a high mobility. So my conclude my talk. This we have synthesized in successfully the ternary spinel ferrite to high entropy oxide with a single step reaction using flame spray pyrolysis. X-ray reference confirms that all synthesized materials are single phase with single phase HRSM particles to be in 5 to 50 nanometers. The material exhibit a direct band gap nature with optical band gap 1.1 to 1.9 electron volt, and this, the system will have the magnetic ferromagnetic natures and high measurements and have the semiconductor natures. So we can conclude these materials can be used in semiconductor devices and light harvesting applications. This is a reference I followed. This is acknowledgements, and thanks to Professor Rasta Gandhi for Department of the Collaborative Work and DST Industry Project for establishing an MPhil and Sci Physics Department of Physics. Thank you.
Thank you, Mr. Arivaigan, for presenting in the time. So we'll have 1 or 2 questions. Yeah, please.
Okay, so very interesting work. So my 2 questions actually, but quite quick. Why you have used in particular these metals or this composition for the spinel? There is a reason for this?
This particular method, we can go every code, and as your ma'am told her, ask if I am giving the order, how long will be taken. So if you are considering this order, the single step reactions, do that if using FSP technique, is all the, and is not need any post crystallization and low cost effect because of we have taken the nitride precursors.
Okay, and my second question, it's related to incubation you have determined by, so you assume that all the atoms or elements you use came to the A site or occupies the A site, and you made this from Redfield refinement. But actually the electronic cubation or electronic number of this element is quite close and very difficult to get this conclusion from X-ray.
Yeah, so as you mentioned, this that due to the electronic density, since we depend from XRD, so we have a Raman also. So from Raman, we can conclude these are all the relative parameters to get that a mode of degree of inversions should be varying. So you can confirm it from that other also.
Okay.
He is having one more question, I think.
Yeah, first of all, thank you very much. Nice presentation, and we're happy to support this project. Thank you. Just a basic thing, you have been using the inorganic precursors for this. This is one of the advantage you can think of as far as the cost is concerned. But what are the main advantage, disadvantage of the spray pyrolysis process? What do you think?
Main advantages is on a single start reactions, and you are using that precursors or nitride precursors, and for using flames or creating just we are normally people is using methane gas for a fume of creating flame, but we are using it liquid petroleum gas with low cost at this effect, and this disadvantages we are looking for yield. So this is it.
Your friends are having many questions. Okay, one more.
Yeah.
Short question, very nice presentation. I see cobalt in binary, ternary, and every compositions of the systems in ESOs. What is the reason for that, and why do you choose such toxic element in such systems? And does this ternary also shows the different properties when it compares to the 5 elements of ESO?
Yes, of course, because there is that I told you before, right, that this is the synthetic control. That is depending upon the reaction parameters, that inversion parameters will vary from bulk to nano. That's why it will be you can differentiate the parameters also.
I think that we should thank him for the nice presentation.
I now request Dr. Suresh Kumar to present the memento to Dr. Arivaigan.
Thank you.
I now request Professor Gunther Motes to present the memento to Dr. Suresh Kumar. we now have a lunch break. So we'll be starting our next session at 2 p.m. So I request everyone to be back here by 1:55 at max. And whoever is not having lunch coupon can collect it from the registration desk. Thank you.
mais la matinée. Ah, c'est peut-être que c'est du matin alors.
Samuel,
Yeah.
with your permission, I'll take the bell.
For sure. Yeah, we switch with Michael because I should leave earlier. So Michael will replace me at this station, okay?
Okay.
That's good.
Okay.
So I just mentioned this to Ravi. I will come back at 5. So okay. Just at the end of the talk of the
So we have a chance to say goodbye.
Yeah. You can take a flower. No, not true. No.
Hello.
It's really one.
Thank you.
Good afternoon, everyone. Welcome back. Hope you all had your lunch. And this next session theme is ceramic technologies for futuristic mobility. And there's some change of plans. And so Dr. Samuel Bernard will be chairing this session since he needs to leave early. So over to you, sir.
Okay, thank you. Good afternoon, ladies and gentlemen. So it's my pleasure to welcome the first speaker, Ulf Bethke, from the Institute for Material and Joining Technology in Magdeburg, in Germany. And the title of his talk will be Electrically Conductive Polymer Derived Ceramics with Negative Thermal Expansion. So please.
Thank you, Samuel, for the kind introduction. And also a big thank you to the organizers, Ravi and Günther and their team for inviting me to this workshop and giving me the opportunity to give a lecture here. My talk is based on the PhD thesis of Anna Fedorova. She was PhD student in the Scheffler group some time ago and did a lot of work regarding PDC with fillers with negative thermal expansion behavior. And Philipp Heinrich was the master student whose thesis was built on the results of Anna, and he added as secondary fillers some metal or metal precursors, and we looked on the electrical behavior of the composite materials. You are all familiar with the normal expansion behavior of materials, which is normally an expansion when the material is heated, but there are some examples of materials where it's exactly the other way around. So if you heat these materials, the volume will actually decrease. And the most prominent example, which you may know from your local kitchen, is the Ceran material. It's the trademark of the Schott company in Germany. And it's actually a glass ceramic containing a distinct amount of a crystalline material in a glass matrix. And this crystalline material, it's a lithium aluminum silicate, has a negative thermal expansion behavior. And by controlling the crystallization process, you can obtain a composite material with a near zero thermal expansion. And this avoids some thermal stresses and cracking when you heat up such a Ceran cooking field. There are other examples more in the scientific field. For example, the zero-dur material class, it's also glass ceramic of Schott. And these materials are used, for example, as holders in large-scale mirror telescopes. So these pieces have dimensions of several meters, and they are machined with a very high precision in order to get a sharp image at the end. And any distortion or any thermal stresses inside the material will result in blurred images, and this is highly unwanted, and thus these telescope mirrors are also made of materials with a controlled coefficient of thermal expansion, and in this zero-dur material class, the CTE is exactly zero in the operating temperature range of these telescopes in order to get a sharp image. Here's a small list of NTE materials from the literature. Most of them were found in the last around 25 years. with some exceptions. The Invar alloy is well known since the 1970s, and the beta oil cryptide is even older. It was found in the 1950s, and the beta oil cryptide is the phase which is responsible for control of the CTE in the Ceran or zero-dur materials. And if you look in a more detail on the composition of these compounds, you see that they all, or nearly all, contain tetrahedral MO4 building blocks, and these tetrahedral moieties are of great importance for the thermal expansion behavior, or namely the NTE behavior, because the dominating mechanism behind NTE behavior is a concerted movement of these tetrahedral or polyhedral moieties during heating, which results in a volume decrease of the unit cell. It's called the rigid unit mode, and this rigid unit mode is one of the explanations, or the important explanation of NTE behavior. Beta oil cryptide was selected for the work of Anna and also for the work of Mr. Heinrich. It's a well-known NTE material, and here you can see the phase diagram of lithium oxide, aluminum oxide, and silicon dioxide. And oil cryptide is found here with equimolar amount of lithium, aluminum, and silicon. The crystal structure of beta oil cryptide is identical to the crystal structure of high or beta quartz. So it's a hexagonal structure, and the position of the aluminum O4 and silicon O4 polyhedra is identical to beta quartz. And for charge balancing, oil cryptide contains additional lithium cations, and these are found in these hexagonal channels along the C-axis. So it's actually a lithium-stuffed variant of beta quartz. The synthesis is quite straightforward. You can apply solid-state synthesis from lithium carbonate, aluminum hydroxide, and silicon dioxide, or you can also apply a sol-gel approach. We decided to use the solid-state route in our studies. The thermal expansion behavior of oil cryptide is anisotropic, so you only see NTE effect when you look on the dimension of the C-axis of the crystal structure. A and B have a positive coefficient of thermal expansion of 8 ppm. For the C-axis, you find minus 16 ppm. And when you look on the volumetric expansion, you have a slightly negative expansion behavior for the cell volume of beta oil cryptide. Anna already showed in her work that it's possible to obtain PDCs with oil cryptide as filler. The processing was as follows: as polymer polymethyl zesquioxane, Silvers MK of Wacker company was used, and this Silvers MK resin was mixed with 40 to 60 volume% of oil cryptide filler. Cross-linking was performed under pressure at 200 degrees centigrade, and then finally the samples were pyrolyzed in inert atmosphere between 800 and 1100 degrees. By dilatometry experiments, it was shown that it's possible to get samples with near zero to even slightly negative thermal expansion. The orange curve corresponds to a composite material with 60 volume% oil cryptide. When you decrease the oil cryptide fraction to 40%, you get a slightly positive coefficient of thermal expansion. One challenge in these materials is the mismatch between the CTE of the filler particles and the PDC matrix. You can see in this interface region between filler and matrix some thermally induced cracking, which also has been predicted by finite element simulations, where, as you might expect, the highest stresses are found in this intermediate region between oil cryptide and PDC matrix. This crack formation is a problem when you look on the mechanical properties, but it was shown that the mechanical behavior or the mechanical strength can be improved if you decrease the particle size of the oil cryptide filler fraction. Another problem is the reactivity of oil cryptide with silicon dioxide. In the phase diagram, I forgot to mention, There's a miscibility region between silicon dioxide and oil cryptide, which is to be expected as the crystal structure is very similar, and oil cryptide can dissolve additional silicon dioxide at elevated temperature. And the problem with this is that when this happens, the NTE effect is lost. So it's actually undesired if you are interested in composite materials with controlled coefficient of thermal expansion. And you can see in this XRD plot of a single reflection of the oil cryptide phase that you get additional intensity, additional phases with different lattice parameters when the pyrolysis is performed at higher temperature. And these are other phases with similar structure than oil cryptide, but with an increased amount of silicon dioxide and lost NTE effect. The idea behind the work of Mr. Heinrich was to combine these NTE fillers in a PDC matrix with metal filler or metal precursor filler in order to get an electrically conducting composite material. And the idea behind was that we get a composite and we increase the temperature and the volume of the material will reduce and bring the metal particles closer together. So we will increase the contact areas between the metal particle fillers and thus increase the amount of conduction pathways. So we would expect an increasing electrical conductivity when we increase the temperature, so just the opposite behavior of the typical metallic conductors. This was a general idea behind, and we switched to another polymer, so we used a more carbon-rich phenyl-vinyl resin, Silres H62C, also from Wacker, in order to get a free carbon phase during pyrolysis, which will also increase electric conductivity. The processing was as follows. Oil cryptide was again synthesized in a solid state reaction, and Rietveld analysis proved its purity. It was almost 96% pure beta oil cryptide. But if you look in a more detailed view on the reflection profiles, you see the splitting of the oil cryptide reflections. So you have not one oil cryptide phase, but three, which is necessary to model the reflection profile sufficiently. And you see some broadening of the reflections and also a shift of the reflections. And this is corresponding to a distorted oil cryptide phase. This is well known in the literature. If the ordering of silicon and aluminum in the crystal structure is disturbed and not perfectly ordered, this will result in a shift of reflections and also in an increase of the ratio between the length of the A and C axis. This AC ratio is an indicator for the degree of ordering in the oil cryptide phase. Pure ordered oil cryptide has a ratio around 9.38. And when there's some degree of disorder in the structure, this AC ratio will increase. And in the starting material, almost 85% of oil cryptide were in a nearly undistorted state, but around 9% belonging to this green curve here belong to a distorted oil cryptide phase with an increased AC ratio. Further processing was conventional, so we mixed the oil cryptide powder with the liquid H62C resin. We added cross-linking catalysts, and as precursor for the formation of the metal phase, we used copper oxide with a fraction between 1 and 15 weight%. The materials were mixed in a centrifugal mixer, and we obtained dispersion which was suitable for slip casting, and samples were produced in silicon molds by slip casting, cross-linked at 130 degrees centigrade, and finally pyrolyzed in inert atmosphere at 1000 degrees centigrade. The idea behind was that the pyrolysis gases will reduce the copper oxide particles and form in situ our corresponding metal phase. Characterization was done by micro-CT and XRD regarding phase composition and microstructure, and then of course the thermal expansion behavior and the electrical conductivity was investigated. Looking on the microstructure, it becomes apparent that the samples containing no or only 1% of copper oxide filler exhibit large amount of porosity, 50 to 65%. The reason for this is not really known, it remained unclear. But when you increase the amount of copper oxide to 10 or 15%, you see in the CT micrographs that the porosity is reduced. You get more or less elongated pores or cracks, and the porosity is reduced to around 25%, so significantly reduced. When you look on the ceramic yield, you find a trend which is in good agreement to the porosity. So the highest ceramic yield is found for the samples with 10 and 15% copper, and the lowest ceramic yield is expected for the samples without copper and with 1% copper. So the copper fraction has obviously an effect on the ceramization behavior. What might be possible is an effect on the formation of the carbon phase. Thus, lower amount of gases are released and instead form this free carbon phase. The second part was the investigation of the phase fraction or phase composition. And when you look on the oil cryptide reflections, again, you see the already mentioned broadening. It's much more pronounced than for the pure starting powder. So we also have the increase of the AC ratio indicating disorder, and we also see a significant broadening of the reflections itself, which also induces some kind of microstrain within the crystal structure. So this is pronounced for the samples containing copper, so the copper oxide or copper phase also has an effect on the degradation of the oil cryptide filler. Looking at the phase amount, it can be observed that the samples without copper or only 1% copper still maintain 30% of undistorted oil cryptide in contrast to 85% in the starting material. But for the more copper-rich samples, there's no undistorted oil cryptide material left, and all oil cryptide has undergone some kind of distortion in the crystal structure. The next characterization was done by dilatometry. Here you see as reference the expansion curve of the pure PDC oil cryptide composite with 60% oil cryptide. The black curve is a pure PDC matrix, and the red curve, I forgot to mention, belongs to a reference specimen in which we did not use oil cryptide or copper oxide filler, but the same amount of alumina. It's a reference sample containing a filler with a distinct positive thermal expansion filler. And this is obviously found in the dilatometry curve as well. The copper-containing samples fit well in between the pure oil cryptide PDC composite and the PDC matrix. So the thermal expansion behavior is like it can be expected. If you look on the CTE values, you see for the samples containing oil cryptide an increase from CTE of 1 ppm to 1.7 ppm when you increase the copper fraction from no copper at all to 50% copper oxide. The CTE of the pure PDC matrix is 2.7 ppm and the alumina reference sample more than 6 ppm. So the concept already also works. Despite the distortion we see in the crystal structure of the oil cryptide phase in our samples, we still have reduction of the coefficient of thermal expansion. It's not a zero expansion, but it's still a reduction of thermal expansion. When looking on the electrical conductivity, here you see the samples without copper oxide. So the oil cryptide PDC and alumina PDC samples, and here we have clearly an insulating behavior. The electrical conductivity is smaller than 10 to the power of -8 Siemens per meter. The temperature coefficient is slightly positive, but actually it's very low to almost no electrical conductivity at all. For the samples containing copper, we see an increase of the electrical conductivity by around 3 orders of magnitude, which is fine. but the conductivity values are still low, so they range in the order of magnitude of 5 to the power of 10, to 5 by 10 to the power of -7 Siemens per meter. So it's still on the borderline between insulator and semiconductor, so it's not the result we expected. And when you look on the conductivity curves with increasing temperature in more detail, you see decrease of the electric conductivity with increasing temperature. And also you will see there is no trend, no correlation of the electrical conductivity to the copper loading. So the sample with 1% copper is a higher conductivity than the sample with 10% copper. So the explanation for this is most likely that there is no formation of a percolating metal phase, which might originate from the copper oxide or copper loading, which is too low to form a percolation network. And most likely the electrical conductivity is maintained through the carbon phase, which forms by catalysis of the copper oxide. This is also known from the literature that transition metals are able to catalyze the formation of carbon nanotubes, for example. And this carbon phase is most likely the reason for the electrical conductivity, and this is also the explanation why there is virtually no effect of the copper loading itself on the electrical conductivity. Okay, to conclude my talk, it was shown that it's possible to manufacture composite materials with PDCs and fillers with a negative thermal expansion, and that's also possible to get 0 to slightly negative thermal expansion composite materials. Challenges are still found in the interaction between the filler and the matrix, for example, the thermally induced stresses, and also the chemical reactivity of the oil cryptide fillers with the silicon dioxide formed in the pyrolysis process. Then it was also shown that it's possible, in principle, to combine NTE fillers with a second filler for generation of a metal phase in the composite materials. And this has an effect on the electrical conductivity, but not the desired effect that we get metallic conductivity with a positive coefficient of temperature. So an increase in electrical conductivity with increasing temperature. So as an outlook, it might be of interest to switch away from the siloxane-based polymers to oxygen-free pre-ceramic polymers, for example, polysilazanes, in order to avoid the silicon dioxide formation and silicon dioxide dissolution in the oil cryptide filler. And the other point is processing related. So the formulation of the dispersions must be improved and optimized in order to get a higher amount of copper oxide phase and finally get the percolating network of metal particles in the microstructure for decent electrical conductivity. Thank you for your kind attention, and also thank you for funding and the Scheffler Group.
Okay, thank you for your nice talk. The talk is open for 1 or 2 questions. Yes, please.
Yeah, first of all, thank you very much. As you're planning for the NT, right, are you thinking for using this for high temperature application?
For what?
As you are planning for the negative temperature coefficient, are you planning to use it for high temperature application, or what is your plan? What are the applications?
We didn't have a specific application in mind. It was just the fundamental research approach to get a material where we have increasing electrical conductivity with increasing temperature and also metallic conductivity. It was just a combination, just for curiosity. So there's no specific application behind this.
Right. We could see the hysteresis loop, where actually you have achieved certain loop nodes for which you are getting the very good negative thermal expansion coefficient. Can you go back again?
This one?
Go back. Go back. You have shown the minus 2% hysteresis loop. Go back. Left side there is a. Yeah, yeah. This figure, right?
Yeah.
you have shown the hysteresis loop during heating and cooling.
Yeah.
That means you are likely to achieve certain good amount of thermal shock resistance with this product. And you also have shown the very good electrical conductivity. I'm not sure whether this cell can be used, can be used for high temperature application, so that you can use under a very thermal shock condition. You can use this product. Maybe you can think of that.
Okay.
Okay, thank you for your suggestion. Okay, we can close your talk. Thank you again for your very nice talk.
Thank you very much, sir. I request Dr. Samuel to present memento to Dr. Ulf Betke.
Okay, the second talk will be given by Mr. Kumar, professor in the Department of Metallurgical and Materials Engineering in India, and he will give us a talk on carbon ceramics and boride ceramics, sintering and high temperature typological characterization. So please.
Thank you, Chair. And first of all, thanks to Professor Ravi Kumar and his team for inviting. So I'll be talking about some carbide ceramics and boride ceramics using some powder sintering route. So it is a bit different from the way the workshop is actually going on, not actually related to the polymer derived ceramics. But I will try to have make you understand this high temperature tribological characterization of these important ceramic materials. So I understand after the lunch the session becomes more heavy, and I'll try to make you active. Okay, thank you. So yeah, before beginning this topic, I just want to introduce our group's activities. So for the last 12 years or so, we have been working in processing several ceramic materials by sintering, different sintering routes, and then understanding their microstructural characteristics, and then try to understand this microstructure influence on certain mechanical, thermal, and wear resistance properties. So for the friction and wear resistance, we use different types of tribological instruments, right from sliding to particle erosion to machining with different conditions, and we do several ceramics and mostly carbides and borides. So before introducing, let me just have a look of the national scenario at the high temperature tribology research. So our group is in Roorkee, nearer to Himalayas here, okay, and we are working mostly on the high temperature ceramics, bulk ceramics and their composites. There are few groups working on this high temperature tribology, mostly on the coatings and some alloys. So for this talk, I selected few important research results published in recent years from our group on the carbide ceramic, silicon carbide, and then borides, zirconium boride, and then we have certain other composites. So the idea is to have certain ceramics prepared via sintering and then try to understand this high temperature tribology. So because you know the silicon carbide ceramics are very famous for their attractive properties, and they are extensively used for different applications of structural, aerospace and other fields where the tribology is the major concern, where the friction and wear resistance needs to be controlled. But you can actually see the monolithic ceramics are prepared mostly by the liquid phase sintering, because these ceramics are highly covalent and less thermal coefficient, less diffusion coefficient, so we require
high sintering temperature. So liquid phase sintering is mostly preferred with certain additives. So whereas the additives have strong influence on the microstructure and then the properties, right? So, but all these additives try to give the sintering easy, but at the same time the properties are reduced. So there must be some optimum amount of such sintering additives, and then you must have a strategy to control the sintering chemistry, okay? So, but most of the available studies are done with a large amount of sintering additives where we need to compromise on certain properties. So our idea is to go with a certain sintering strategy to using very small amount of additives, at the same time having a resultant property superior. With this in mind, so we have done certain study on the amount of additives influence on the ceramics, monolithic silicon carbide ceramics prepared via hot pressing. So we used very small amount of 0.2% yttria and 3% yttria for the comparison, and we could able to produce a very highly dense material by hot pressing with different properties because the microstructure are actually different. So in the second one we got more like larger equiaxed and elongated, whereas here we have a little grain refinement with bimodal structure. So after having certain property difference with this hardness varying and the fracture toughness also varying and the strength, so we went on to understand the tribological behavior of such ceramics. So when we did this sliding wear against the commercially available tungsten carbide ball of these ceramics, so we could able to see there is a large difference in the wear rate. So the smaller amount of additive containing silicon carbide gave a very less amount of wear, and the one surfaces show it is completely fractured one. So there is no certain third body additive, third body coming in contact, because when there is no such a third body, and then these sharper indents of this counter body actually slide over here and produces lateral cracking, and then lateral cracking is observed here, which results into large amount of material removal. When you have a large amount of additive like 3% here, so there is a possibility for this yttria rich additive, and there are stresses at those interfaces of silicon carbide and then yttria, so you have a larger amount of material removal, so compared to the smaller amount. But interestingly, when we did this with a different counterbody of silicon carbide, entirely different scenario came in. So where you could again understand with the decrease in the amount of additive, of course the wear decreased, but the mechanism of the material removal changed completely from this fracture-induced wear to the tribochemical wear. The tribochemical wear is the wear that is the material loss because of the tribochemistry influence in the contact. So all these debris, you can see this long cylindrical debris are obtained compared to very equiaxed loose debris here. So these long cylindrical debris are the resultant of material removed from the contact, which is which is more viscous, and then because of the continuous sliding, these debris connect and then form a long cylindrical shape. These cylindrical shapes are more like rollers in the contact, and they try to reduce the friction and then the wear. So there is a mechanism change from the counter body, and then the influence of additive is also understood. So I mean, the processing difficulty was the major concern why people could not able to produce such a silicon carbide with a smaller amount of additives. But with our hot pressing technology, we could able to produce this sintered material with very small amount of additive, and then small amount of additive is found beneficial in reducing the wear. So this viscous contact layer is because of this silicon carbide oxidized silicon oxide, and then in the presence of the moisture where the test was done, moderate humid conditions of laboratory, where it forms this hydroxylation. So something, it is a very simple way. It is something like when you are doing a roti or a naan in your kitchen, and then you sprinkle some water on the dough mixture and then try to roll over there. So on the surface of the roller, you have got a dough coming on like a debris. So similar thing happening here, the rolling becomes easy, the sliding reduces, the friction reduces, the wear resistance increases. So this is very interesting study which we got. So again, we could actually see there are many properties of ceramics which could be used as reinforcement for this silicon carbide ceramics for improving the wear resistance further. So in our group, we have been working for the last few years in introducing several ceramic reinforcement in the silicon carbide, trying to understand the influence of such reinforcement on the wear resistance in terms of increasing the hardness or the elastic modulus. So one of the study I selected here for the very contrasting in properties of silicon carbide with tungsten carbide. Tungsten carbide having a very high modulus and then a compromising hardness compared to the silicon carbide. If you could able to have a very sintering strategy to produce a microstructural homogeneity, then we could actually have a very important ceramic material with improved fracture toughness and then the combination of such properties. Mostly these for the wear resistance, the hardness, fracture toughness, elastic modulus are very important. So we could able to actually change this tungsten carbide content and then the grain size of silicon carbide reduced with interparticle distance of this tungsten carbide reduced, but you can see the hardness actually reduced because of the tungsten carbide, but with a microstructural homogeneity, the hardness could be around 26 gigapascal compared to around 24 gigapascal here. But the fracture toughness is increased from 5.85 to 6.7 MPa root meter. This is because of the larger instances of having this crack bridging and then the crack deflection because of the tungsten carbide interaction with the crack. So with such kind of a successful demonstration of this new composite, we did extensive study on this tribological characterization of such material. So when the counterbody is changed, actually you can see the coefficient of friction behavior is also changed. So particularly against the steel ball, because of the presence of harder iron tungsten oxide, the friction actually increases with a larger amount of tungsten carbide in it. Whereas in the other cases of silicon carbide ball or tungsten carbide cobalt ball, there is a chance of decreasing the friction. So this is because of the interactive third body which is in contact while sliding is going on. For the tungsten carbide ball and then the steel ball, there is a tribochemistry which is more dominant, whereas in the other case, this is a more fracture. So again, this is because of the oxidation and the hydroxylation. So very interestingly, we did this study with changing the configuration by, so we did some reciprocatory sliding and then compared with the unidirectional sliding. So the reciprocatory sliding gave a very less wear compared to the unidirectional, because in the reciprocatory one, so the debris which is coming out of this material are unable to come out of this contact. So apparently these are subjected to continuous sliding and then the compaction that resulted into reducing the wear. So we did extensive study of this material with different configurations of wear, and then we understand there is a larger influence of this tungsten carbide content as well as the counterbody and then the environment, particularly temperature. So when the temperature was higher, right, 500 degrees Celsius, so because there is no moisture content in that and there is always a fracture happening, whereas at room temperature there is an oxide layer compacting, covering over there, reducing the wear. So we did even further study underneath the one surface. We selected underneath the one surface by F5B, focused ion beam, and then this material, this sample, this lamella were subjected to transmission electron microscopy, and then very interestingly we found there is a large activity of dislocations and twins inside the silicon carbide grains, whereas the interface with the tungsten carbide actually obstructing these dislocations, and because of these tungsten carbide inside this composite material block the substructures, so it can actually increase the wear resistance by arresting such crack. So when there was no tungsten carbide, there is the one surface cross section shows the large disruption with the large amount of deformation and fracture, whereas in the presence of tungsten carbide, such cracking is reduced extensively that actually reduce it to the wear. So this was one part of this, and very interestingly, I would like to
have your understanding, your attention on very recent study that we started with the silicon carbide particle, very impure particle, very cost-effective silicon carbide available in the market. We did purposefully this milling of this powder to reduce the size to nanometer by using steel ball and steel vial. So because of the contamination happening in the powder, so that contamination helped us to get some nitridation in the nitriding atmosphere heat treatment. So in the argon there was no difference in the weight, but in the nitrogen atmosphere there is a large difference in the weight. So this nano-sized silicon carbide, when subjected to prolonged heat treatment at around 1400 Celsius in nitrogen atmospheres, then we could able to have a silicon nitride presence over there. All this microstructural investigation shows the production of the silicon carbide, silicon nitride, nanowires or fibers or threads on the surfaces of the particles. So with this we proved that not only the chemistry of the surface of the silicon carbide, the morphology has also changed at the surface, which resulted into dual phase silicon carbide, silicon nitride nanostructures, which we could actually use it in aluminum alloy as a reinforcement and produced the composite by spark plasma sintering, and then identified that the wear resistance increases large. So these results are recently patented and very attractive. So I would just have another very important interesting study in our group going on with the electrical discharge machinable silicon carbide ceramics, because the silicon carbide are the materials which are very poor with respect to sinterability, and also because of the machining difficulty, they are having large limitations with respect to the applications. So we found a solution having a conductive reinforcement and also a strategic sintering, which can improve not only the properties for the wear resistance like toughness and modulus and hardness. At the same time, this conductive reinforcement can improve the overall conductivity. So we retained the beta silicon carbide as well as nitrogen substitution in carbon sites in silicon carbide and produced improved conductive silicon carbide composites. With changing the titanium boride reinforcement, we could able to have an improved conductivity as well as the mechanical properties. So this shows along with the silicon carbide titanium boride, there is a formation of liquid phase precipitate, which actually results into improved densification. At the same time, the conductivity increased. Even the carrier density also increased, and there is an optimum composition for the titanium boride addition. So the mechanical properties also improved. The high fracture toughness and hardness have resulted into large reduction in the wear, and we understood that the tracks are completely absent with any oxides. So it is basically fracture going on, which resulted into wear, and such a wear is reduced with the amount of titanium boride increasing. So with this we could able to address two issues. One is the wear resistance, at the same time the conductivity problem. So conductivity, because of the increased conductivity, we could able to do the electrical discharge machining successfully. So with increase in titanium boride content, the material removal rate increased, where the surface roughness actually decreased. So this is, we feel this is a potential material for many applications. So I just selected another study for hard ceramic materials. So boron carbide. Boron carbide, as you know, very famous material with respect to their hardness, but their fracture toughness is very less. Because of that, the applications are limited. But we could able to have a boron carbide with silicon carbide reinforcement. Such a composite is produced with varying additive chemistry. So we varied the oxide additives, aluminum oxide, yttrium oxide, and even the amount of such aluminum oxide, yttrium oxide ratio is also changed. And we could able to produce a boron carbide, silicon carbide composite with liquid phase sintered material. So this liquid phase sintering of aluminum silicate precipitate actually increases the sinterability. So we could able to produce this with a very low temperature of around 1600 Celsius. So far no one has reported this. And then all these microstructural investigation shows these this liquid phase actually is sitting over certain grain boundaries, and then because of this, the fracture toughness increased via this deflection of the cracks and the bridging. So the important result here is we could able to have a very less decrease in the hardness, at the same time having a consistent higher fracture toughness of around 6.5 MPa root meter. So such a combination of higher hardness and the fracture toughness along with the liquid phase sintered material which could be sintered at a lower temperature is a promising material for many applications of wear. So the wear is also is a function of such additives, and all this Raman analysis shows there is no oxidation, it is purely a fracture. The wear debris shows it is largely fractured material with the one surface showing abrasion and pull out. So there is no tribochemistry involved, but I selected one very important other material, boride ceramics. So where we could able to see such a tribochemistry influence in different configuration of wear, particle erosion wear. So we produce this composite material in our laboratory using spark plasma sintering so that these can be intended applications of such material. So zirconium boride silicon carbide is proved to be having oxidation resistance higher and then strength increased. So when the spark plasma sintering was done in multi-stage SPS, so we could able to have this higher displacement, that is the shrinkage to a larger extent with this combination of these stages, 1400 for 6 minutes followed by 1600 for 2 minutes, so that we have a density of around more than 98%. So there is no other phase possible because of this SPS being very faster and then no other reaction phase, and then all these silicon carbide zirconium boride are bonded, and hardness increased, elastic modulus by nano indentation technique improved. We observed it is an increase with the silicon carbide content, at the same time fracture toughness improved. So we have done the high temperature particle erosion by using silicon carbide particle stream. So when we did it high temperature, there is a large influence of temperature as well as the silicon carbide content. When the angle of impingement is changing, of course we have a larger amount of material removal by this erosion, because being a ceramic the fracture is more dominant, but at the same time when you have a larger amount of silicon carbide, then this pull out is reduced, at the same time the surface is become more protected with the oxide layer. So this is actually absent in room temperature conditions. So all this XRD analysis shows the formation of such oxides of borate and silicate or borosilicate, which actually protects this surface from the further wear. So we identified such a temperature dependence of erosion rate with a minimum at 800 Celsius because of this formation of such possible oxides. So this study of erosion oxidation reaction is useful in designing material composition for the wear resistance applications or supersonic aircraft component. So with this I conclude. We recently published one book from our studies on this friction and wear of ceramics. So I acknowledge all my PhD students and also my collaborators and mentors and also my all sponsoring agencies for generously supporting my activities at IIT Roorkee. Thank you very much for your attention.
Thank you for your talk. We have time for one question. If not, I can ask you a question. You mentioned the nitridation of silicon when you form silicon carbide, silicon nitride composite.
Yeah.
Yeah, this. No, just. Yeah.
Nitridation.
So you form silicon nitride at 1,400 degrees C, right?
Yes, yes.
Is there any effect of the ball milling? I mean, you ball mill in stainless steel, right?
Yes.
So there is a probably
Correct.
catalysis.
Yes.
Okay.
So because there is a reaction happening with silicon carbide, with this contamination, mostly this iron oxide, iron silicides are formed during this ball milling using the steel balls and in the steel well. So they actually, these structures are formed because of the vapor liquid solid interface mechanism.
Yeah, clear.
So these are actually very interesting. So These are not dominant at higher temperature, but a lower temperature of around 1400, we could able to see such structures and mostly on the surface of those particles. So the
probably iron.
Yes,
inside.
because of the contamination.
Yeah.
But that helped us to get such a dual phase nanostructures. Yeah.
Okay.
So
Thank you very much for your talk.
Thank you, sir. I request Dr. Samuel Bernard to present the memento to Dr. B.V. Manoj Kumar.
Thank you. Thank you so much. Thank you. Sorry.
So we can welcome the third talk and the last talk of this session. This is a keynote lecture given by Thomas Fischer from University of Köln in Germany, and the title of his talk is Molecular Precursors for Chemical Vapor Deposition. So Thomas, please.
Yeah, thank you very much for this nice introduction, and also thank you very much for this nice invitation to present some of our work we're doing at the University of Cologne, the research group of Professor Sanjay Mathur. And as we are chemists, we are looking into the molecular structure of our precursors and what we can do with them with different materials processing techniques. And we are not so much working in the classical sense of the PDC community, but to have a little bit of a link there, this is just a literature published work. So here you see that PDC-derived ceramics, in this case a 3D printed system, has been infiltrated, so vapor phase infiltration or chemical vapor deposited on the surface of a PDC-derived 3D sintered ceramic in order to close the voids and, let's say, to form, like in this case, silicon carbide interfaces, using as a precursor, which would be interesting from the chemical point of view, here a trichloromethylsilane and hydrogen, which is decomposing to silicon carbide and cleaving of HCl as a result. So CVD is mostly known to make thin films, make surfaces or functional surfaces on variety of 3D structures, of 2D structures. Let's say all the semiconductor industry would not be working without CVD systems, and they would also not work without the suitable precursors for that. There are many different parameters which are governing our CVD setup. So we have some kind of reactor. Mostly we work in a low pressure regime to avoid any gas phase reaction and have only to have these reactions on the surfaces. But of course we can have different energy sources. We can use lasers, we can have just joule heating, we can ignite a plasma. So there are different ways of decomposing the precursor to put enough energy to destroy the precursor we put in. So we know what we put in. Normally we know what we get out, but seldomly we know what really happens inside. And this is the decisive part where we control if our precursor works or not. And despite the energy, of course, we're looking at the pressure regime, so different pressures. Low pressures allow us really to exclude any gas phase reactions, but of course at a low pressure, we do not have much precursors available to have a fast film growth, so therefore the lower the pressure, the lower the film growth, but also the more defined the crystallization and also the purity of the film often is. But in industrial applications, you always have to find the sweet spot for the cost and, let's say, effectiveness of a process. And the geometry of the reactor also plays a role, but we're not going into that with these fluid simulations. As I said, precursors are a parameter. The reactor itself, how it's, if you have we can also make CVD on particles, for example. The energy, as I said, which kind of pressure regime and external stimuli, and I would go for that. And later on in this talk, on how magnetic fields can influence the growth of the film during the CVD process. And normally, people are working in large-scale CVD systems. This is still a laboratory system. The industrial-scale systems are several meters long. But we had a research project where we had like really small substrates. We have seen in the gas sensing presentation some hours back that they use, for example, this substrates, because we had also a project together with Weimar, and they have, let's say, using these kind of substrates. And there you're working on several millimeters. So here you have maybe a square centimeter of area. Here we're talking about, this is a substrate which is 3 by 3 millimeters. This is a substrate which is 1 by 1 millimeter. So it's really small substrates, but they have already a built-in hot plate. So we have these sensors that need to be heated. So we use this as a test bed for CVD, because directly these can be heated. If you tweak around a little bit electrics, you can also go around 1,000 degrees with these kind of substrates and these. But at least 850 degrees are feasible. And then you can do CVD on electrodes, so you can measure the electrical properties of the growing film. And as well, you need a reactor which you can put this in, because later on the joining is rather difficult. And we try to use it to understand a little bit what's happening in the gas phase, because it can be quite messy. If you have a simple precursor, what we have seen before, the silane, the methyl trichloromethylsilane, it can decompose in the gas phase, forming clusters. Then we have the hydrogen flowing around, we have the chlorine, we have the methyl groups. They can form clusters as well. They can be incorporated into the film. We have surface reaction, we have gas phase reactions. So it's really tricky to see what's happening. And therefore, often these systems are kind of, we know what we put in, we know what we get out as a film, but we do not know what's really happening. And of course, we know what kind of energy we put, for example, how much we heat our substrate. But in the end, we want to see what's really happening in there. And there we derived a system where we have a mass spectrometer directly flanged onto the system on these small substrates. So we have a small amount where our reaction parameters are very well defined in the surrounding of this small hot plate, having pressure sensors, high accuracy pressure sensors, electrical feed-throughs, and mass spectrometers and optical pyrometers to measure the surface temperature, and then try to see what's happening on the substrates. The system looks like this, a little bit messy, but it's a research setup. We have now modified it a little bit to have it a more nicer looking and more easy to use setup. But at the general point of view, we are collecting every second like 30 to 40 data points from pressure, temperature, and feed rates, and see how it's working. And most decisive point is a mass spectrometer directly flanged onto the reactor, because this allows us now, in an example, to monitor the whole process. Because what you know from mass spectrometry, we have the classical, let's say, call it one-dimensional mass spectrum. We know the mass of the fragment and its intensity. And this was this precursor. We had deposed the niobium isopropoxide. It's a dimeric structure. And if you look at over the process, you see here the scan number. It correlates with the minutes. So every minute we record one mass spectrum. Here we have this M by Z, so the mass we have here. And then we record a full spectrum. And there we see that it's not a constant system. So we see some things are growing up, some are declining, have a maximum. And then we see that the process is not as straightforward, because when the film is growing, our surface is changing. Therefore, the surface reactions are changing. Some surfaces react as a catalyst itself, and so on and so forth. But analyzing these three-dimensional systems is a little bit tricky. So therefore, doing some data crunching, and you see here a top view of this 3D graph. You can here see the intensity as a color code, and then you correlate it with the temperature of the substrate here in red, and also the pressure reading, and also the position of your valve, so you're opening the precursor or not. And then you can really follow at which temperature something is happening, because here we see directly that the pressure is steeply increasing at this temperature point. And then looking at individual slices throughout this, we can follow the overall change of if some fragments are stable throughout the whole temperature ramping, some are declining, or some are even changing throughout different temperatures. And looking into that, make a differential mass spectra. So some data crunching here, we can derive that this selective precursor is cleaving either its niobium-oxygen bond or the oxygen-carbon bond at a different temperature. So this regime here at lower temperatures, between 3 and 400 degrees, we are cleaving the niobium-oxygen bond, while at higher temperatures, we are cleaving the oxygen-carbon bond. And depending if you want to have a more oxygen-rich niobium oxide or an oxygen-deficient niobium oxide, you can tweak the temperature and get a different oxygen-to-metal ratio. But not only the process conditions are decisive, so looking at the sweet spot for the temperature processing, but also the chemistry itself. Just a repetition. So we're now looking not at the process itself, but just at the precursor we are using. And we are using this so-called precursor concept using single-source precursors. That means having, we have seen it with the niobium oxide already, the niobium isoprenoxide, where we have the niobium, or in this case we have silicon, for example, as a central atom, and we have an oxygen surroundings, like siloxanes, and we are supposed to get silicon oxide, while if we use directly carboxylanes, where we have the silicon-carbon bond, we are most likely get silicon carbide, so the classical PDC route, with the exception that we tried also to use not any additional reactive gases in the initial stages, so we can directly correlate the molecular composition with the materials composition. Later on, for optimization, you can also fuse in like hydrogen or oxygen to compensate for certain, let's say, residual carbon or something like this for the optimization processes. But initially, you were really interested how the molecule behaves without any additional reactive gases. And the advantage is then you can become more complex. For example, also for ternary compounds, we can think about having two precursors feeding it in, but each of these precursors have different thermodynamics, so decomposition rates, decomposition temperatures, so it's quite tricky from the processing point of view to get these in the right stoichiometric ratio, or you have to overfeed one of the precursor because it might not decompose as fast, so therefore you have to have a very inefficient process where you have to have an excess, maybe it's 5-fold or 10-fold excess of one part to get an even ratio in the material. And moreover, to have, with this kind of preformed structures, you get more homogeneous assembly of materials. Why? Because on the other hand, if you have different decomposition processes, you can think the macroscopic composition is the same one by one, but you might have purely phase A, purely phase B, core shell, shell core, or whatever compositions, but macroscopically, it's still the composition one by one. One example, what we did for example, the hydrothermal part, so this precursor was not used in this case for the so quite dated work what we did, but it's still valid. We see here using two precursors, so in this case the acetyl acetonates. We also see in the thermogrammetry we have two-step decomposition forming quite a heterogeneous particle size distribution while using a monomeric structure with cobalt and iron on the ratio 2 to 1, 1 to 2. We have a one-step decomposition and a more homogeneous size distribution, also with a composition point of view. But it's not, of course, not a general concept, but at the least we have a way of tweaking and tuning these kind of decompositions, also ending up in metastable phases, also processing at much lower temperature due to the already preformed molecular bonds. And therefore, we not limited it to, let's say, niobium or iron or cobalt, but the periodic table is our playground, even going to the lanthanides and a little bit of actinides, so thorium and uranium has also been done in our laboratories, exploiting the chemistry of different ligands with different properties, higher volatility, higher reactivity, higher solubility for different materials or materials processing techniques. And one illustrative example, which we published last year, is, for example, what Professor Mathur had mentioned yesterday briefly, that we have a bismuth precursor to provide. The initial idea was to make bismuth sulfide and just have a small change in the vicinity of this bismuth sulfur core. So we have one carbon atom extra. So here we have a hydrogen, here we have a carbon, so it's a terzbutyl, while it's an isopropyl group. And if you make a CVD out of that, after making CVD at 250 degrees C, using the isopropyl group, we ended up with very nice bismuth cubes. At the same temperature, using the terzbutyl group with one carbon more in the vicinity, we had nice monophasic bismuth sulfide. Another question was, why is it happening, and what was the reasoning behind that? Looking into the XRD, it's phase pure, bismuth, and bismuth sulfide, so nothing special about that. And also the thermogrammetry to see if it's a one-step, two-step decomposition. We see in both cases, so here the black curve is always a one-step decomposition, a little bit of reordering here, but this one yields it out to the theoretical bismuth weight loss, and here more or less achieving to the theoretical bismuth sulfide weight loss, which is quite clear here. So it's nothing about the thermochemistry here. Also checking different temperatures. Here we have at 250 degree, what you've seen earlier. Increasing the temperature, the morphology changes, but if you look at the XRD, it's the same phase with different ratio in the intensities, but nonetheless single phasic system. So with different surface reactions and nucleation parts, but from the phase formation it's the same. And also eradicating the substrate influence, working on glass, on silicon, on FTO. We also have different microstructure, but still the same composition. So it's either bismuth, or in this case, bismuth sulfide. Now the question is, where does it come from? Going back to the mass spectrometrical analysis, meaning, is something happening in the gas phase? Is it decomposing differently? And there you see now a generalized view of the different, now looking at a single or like a one-dimensional mass spectrometrical analysis. So just looking at how the compound is behaving in the gas phase, on not doing the whole process monitoring. We see here that we have different fragments. They have, of course, different masses, overall masses, because on the one hand we have the isopropyl group, on the other hand we have the terz-butyl group. But looking into that a little bit closely, we can see that either the carbon-sulfur bond is being cleaved predominantly, or the metal-sulfur bond is cleaved predominantly. That means if you cleave the metal-sulfur bond, if you cleave the metal-sulfur bond, then of course bismuth is our main product, where we and when we cleave the carbon-sulfur bond, the sulfur remains at the metal, and therefore we have the bismuth sulfide being formed. Still, it did not show us more information about why is it really happening, because we just see phenomenologically we have the formation of bismuth or bismuth sulfide. And therefore DFT modeling came in handy, and thermodynamic modeling, looking into the electronic structure of the two compounds, and also looking at the dipole moments. And there we can see that we have a dipole moment either directed towards the sulfur in the bismuth terz-butyl group, and directed a little bit towards the carbon in the isopropyl group. And this supports that thermodynamically it's more favored to cleave the sulfur-carbon bond in the terz-butyl group, while in the isopropyl group it's not so favored to form this purely carbon moiety, but the sulfur sticks with the carbon. So here we see a small change in the vicinity of a precursor yields us a total different behavior in the gas phase with it using the same parameters. Because this is quite unusual. In many cases, we have no distinction between simple changes in the vicinity. For example, with titanium, molybdenum, and indium. In all cases, either the terz-butyl group is yielding the metal sulfides, or the isopropoxides as the same. This is a special case, but illustrating quite nicely the influence of studying different varieties of precursors, although the changes might be minimal. With different cleavage. Now I'm coming to external stimuli. So how can we use external fields, in this case a magnetic B field, perpendicular at certain angles towards our surface, to modify or influence in some ways the film formation. Back there. We started with a so-called Friday afternoon experiment. I don't exactly know if it was really a Friday, but nonetheless, we just said, can we introduce, what happens if we introduce permanent magnets in our plasma CVD systems? We had some of these nice neodymium magnets. You can buy these as toys, something. We put them in the plasma CVD chamber. One PhD student did that. And of course, you see an influence of the plasma itself, because you have charged particles. And then we did a deposition of iron oxide. And what we see here, because what the student was studying is the photoelectrocatalytic activity of the material. And he was just looking at the morphology was more or less the same, but looking at the photocatalytic activity, it was different. We're having a maximum here with this, he called it perpendicular field orientation, so field orientation like this, and a deposition time of 2 minutes. So we had a difference in this when magnetic fields are present, and also in the XRD it was corroborated that we see here one of the peaks of the facets of 110 was more pronounced than in the others, or suppressed in the other. Of course, this was just putting it in without really much planning, to be honest, let's say, just seeing what happens, then make it more rational in the same process, because we can have process-to-process variations, etc. Now we have magnets put in a different orientation, so one north and south pole mixed. So now we have this parallel or perpendicular arrangement of field lines in the same process. And what happens? We see the same. So in one position we have a higher, here we see the photocurrent density. This is a measure of our catalytic activity, it's still increased for one compared to the other. So we have an influence even in the same deposition process. Also in the XRD, it's not very nicely resolved, but still we can see this hint of this additional 110 peak. And the morphology is, on the first estimation, more or less unchanged. But still, we are working in a plasma, and plasma is influenced by magnetic fields, so we can have a different plasma density. Then we said, okay, let's use this and go to thermal CVD. With thermal CVD, we're talking about 500 to 800 degrees C, so even neodymium magnets cannot withstand that, so we have to use external magnets. This was a little bit more of an investment, so we bought a quite powerful external electromagnet, and then we can have a CVD reactor inside of the magnetic field, and have here can vary the temperature, can vary the pressure, and vary the B field. And there we studied also the iron deposition, because still for this photoelectrochemical water splitting, either depositing iron films and then oxidizing, or also using our precursor concept, having single source precursors for forming iron oxide clusters, and then in a one step forming the iron oxides. Making long story short, we still see a significant influence of the formation of crystallites, also morphologically a change, but also in the XRD. But we could not really resolve what is the origin of certain peaks, because with iron oxide we have hematite, magnetite, and also machemite. Therefore, we asked the support of our colleagues from Research Center Jülich in Bessie to really see what kind of phases are these and how do they correlate. And there they had this nice X-beam, so the X-ray photoelectron emission microscopy. And there we can study like XPS, spatial resolved XPS in a beamline. And let's say, let's just go further. Here we can see different emission energies. And doing a lot of data crunching and principal component analysis, we can deviate two regions, more or less, with two distinct X-ray absorption spectra, attributing to a crystalline or amorphous regions. And therefore, using magnetic fields, this kind of distinction is more or less gone. We have more or less homogeneous orientation of the crystallites, also from a magnetic point of view, while if we do not have magnetic fields present, we have these larger domains in the micrometer range being formed. And it becomes more and more surprising. This is right now under investigation. If you use a precursor yielding normally chromium oxide, if you put in a magnetic field, we form a different structure, but also significant different phases, forming chromium carbide or chromium oxide, and switch it between these two with the predominant phases from the same precursor with magnetic field on and magnetic field off. And therefore, some investigations are right now underway because they upgraded the beamline, so the end station, the X-beam beam station is now upgraded in that sense. Then we can directly inject our precursors into the end station. So it's kind of real messy chemistry for the beamline scientists, but they allowed that, so we are quite happy with that. And now the first results are in on titanium oxide as a calibration system, on iron oxide, and we are hoping to get the next beam times also for the bimetallic systems and also for the chromium systems. Okay, so this was in general, let's say, a rough ride through the different effects of precursors using different fields, using different stimuli, different precursors, and monitoring the process in general. But this is, of course, not done by few of us, so all the group here has contributed to that, either by synthesizing molecules, working on CVD parameters, working on the analysis. So thanks goes to all the group and also the funding agencies supporting the necessary funds to run all the projects. So thanks a lot, and also thanks for IGSTC for the Indo-German cooperation. We're looking forward to continue the existing projects and also looking forward to new ones. Thank you very much.
Thank you, Thomas, for this very nice talk. So, some questions? Ravi, please.
Thomas, of course, it was a very interesting talk, particularly on the influence of the magnetic field on the crystallization process. What drives the formation of the carbide phase instead of the oxide phase? And how does magnetic field influences the crystallization pattern?
So chromium oxide and chromium carbide have different magnetic properties, either ferromagnetic or antiferromagnetic. So this being said, but we believe that in a first, let's say, rough estimate, it's not really the domains which are influencing the formation of the, because of the one phase over the other, because the magnetic field strength gives us maybe, if you correlate it to the temperature-wise, maybe 5 Kelvin plus or minus from the thermodynamics, so to stabilize one phase over the other. And they are too far away, so the magnetic field should not stabilize one phase more than the other. What we suppose, but this has to be correlated with the X-beam studies, that in magnetic fields, some charged particles or gas molecules, they can enrich in a magnetic field. So it's shown for nitrous oxides, for example. In a magnetic field, you have a higher concentration, a higher partial pressure of some gaseous species. That means in the magnetic field, the high density magnetic field, we have maybe a higher partial pressure of carbon species like methane, acetone, or whatever, while without magnetic field, they are diluted, so the chemical potential to react, so the carbide is reacting, or the carbon-rich species from the gas phase are reacting with the surface is higher with the magnetic field as without the magnetic field. But therefore, we need these studies, let's say, call it, let's say, angstrom per angstrom to see if what is being formed. We just know what comes out right now. But it's interesting to see, is there maybe just a chromium species being formed, which is then either oxidized or carburized, or is it really like oxide being formed, which is then being converted to the carbide, or vice versa? So this we need to study. It is still open.
Last question. Very interesting. Just quick question. So similar like magnetic field, it's possible for your machine also to check also electric field effect, like if you apply electric field to substrate, for example, and do deposition.
Let's say this we did with the how it's called, these sensor substrates, because you have these IDE electrodes, and then you can polarize or bias these electrodes. You have to be a little bit careful, because when the first film is forming, it gets a little bit conductive. Then you have a really high current at these first few nanometers. But there have been studies, not from our group, being done as you have in a CVD reactor electric fields, either outside or inside. This has been done and also studied, but we were more eager to study the magnetic field because it hasn't been studied yet. But electric field influences, we also studied for the alignment of certain, let's say we also grow fibers, so you can, or wires in the CVD, so you can align these fibers in electric fields. But if you directly polarize or bias your substrate, you have to be careful, because the first connections impede a very high current. So therefore you have to, normally you need to decouple that. We did it mainly with our existing electrodes. We were mainly measuring the resistance of the films, but therefore you can also bias that and have a field gradient across that.
Okay, thank you.
Yeah.
Thank you again, Thomas.
Thank you.
Thank you, sir. I request Dr. Samuel Bernard to present the memento to Dr. Thomas Fisher. This marks the end of the session. I request Dr. Ravi Kumar to present memento to Dr. Samuel Bernard for chairing the session. So now it's time for high tea. However, before going for hot beverages, there's a small announcement. First thing, I want you to submit your boarding passes, for the refund and all, and at the registration desk. Apart from that, there is this small event going on in Students' Activity Center. It's actually conducted by SPICMACE IIT MADRAS chapter, and it's a part of Virasat 2023. And SPICMACE is basically a volunteer event which involves participation of various artists from different fields. It could be either dance, music, poetry, painting, anything. And it will be performed by very well-versed and famous artists. And this time it's being performed by Sri Malavika Sarukai. And she is recipient of Padma Shri. It is 4th highest civilian award of Republic of India, given to artists who have done exceptional work in any field. and she is talented Bharatanatyam dancer. Bharatanatyam is South Tamil Nadu classical dance. Like every state of India has different marked dances, classical dances. And Tamil Nadu's classical dance is Bharatanatyam. So she's going to perform and it's going to be awesome. Actually, because of the, it has been going on since a few days, but because of our other commitments, we couldn't go there. But today, since we are going to finish it by 5:15, it's better if you go and attend that. So, yeah, after that. After visiting Heritage Center, if you want, you can go there. And it is at SAC. It's near to Taramani Guest House itself. We can show you the way. You must be knowing this OAT, right? Open Air Theatre. I think for... Okay. So, where is ICS, sir, here?
Okay. So, we'll be here at a Heritage Center. After Heritage Center, if you want to go directly to SAC, so SAC is here, near the swimming pool. So, there is a straight way from, after you come out of Heritage Center, near OIT, this is the straight way, you will directly reach SAC. Otherwise, if you are at Taramani Guest House, from Taramani Guest House, you come towards the ICSR building and take the first right, come here and take the first left, and then you will reach here. There, like this way also you can reach SAC, but most probably after Heritage Center, this way is the more preferable way. Any doubt? So yeah. If still there is any confusion, you can reach out to any of the volunteers. Thank you.
Test, test, check, check, test. Test, test, test. Can you hear me?
Ah, Ravi's famous call.
So, good afternoon, ladies and gentlemen. Welcome to the last section of our fantastic symposium with excellent speakers. I have the pleasure to share this last section, and our first speaker is Devinder Yadav. He will giving a talk entitled "Flash Sintering: A Novel Way to Sinter Oxide Ceramics." He is now head of Department of Materials of Metallurgical Materials Engineering of the IIT in Patna, and he holds a PhD here from Madras IIT. So a word to our speakers: be strict, be in time. I will be strict.
Sure. Okay, thank you, Michael. Well, thank you for staying back, and good afternoon, everyone. I'm Devinder Yadav from the Department of Metallurgical and Materials Engineering at IIT Patna. I'm an alumni of this institute. I did my master's and PhD in IIT Madras. So when Ravi called me, I couldn't say no to him, though I do not work on PDCs. But yeah, I would say I spent the best days of my life here at IIT Madras. So this is the outline of the talk today. I'll start with sintering before going to flash sintering. And then I'll share with you some of the results on flash sintering of zirconia. What is the effect of process parameters on the sintering kinetics? And there is a lot of debate in the literature about what is the real sample temperature in the state of flash. So I'll share some results on the temperature measurements. We'll compare the mechanical properties of flash sintered and conventionally sintered samples. And I'll touch upon something which we have started doing recently, that's on reactive flash sintering, where a phase reaction and sintering happens together. And then some results from the synchrotron source on pair distribution function, where we measured the real-time atomic displacements. Now, sintering, as we know, it's a very, very old technique. We start with the powders, we give it a particular shape to them, and then we subject the green bodies to firing, and finally we get a product which is very dense and strong. So it's the firing step where sintering occurs. Now, sintering requires high temperature, and you require sufficient time as well, because it's diffusion controlled, and the diffusion in solid state is basically a very, very slow process. Now, one of the characteristic feature of sintering, which you can see through your naked eyes, is the change in the sample dimension. So just by looking at the dimensions, you can make out whether the sample is sintered or not after the firing step. I come from Patna, and just outside my institute, there is this kiln. And every time I go outside, I see some smoke coming from the kiln. I know that there is some sintering going on. Right. Now, flash sintering, let's understand this with the help of an example. So if you take 3 mole % yttria stabilized zirconia, it's one of the zirconia ceramic, and you want to sinter it conventionally, then you have to heat the green bodies to a temperature of 1450 degrees C, and you have to hold the green bodies there for about a few hours. But by flash sintering, you can sinter the same material at a furnace temperature of 850 degrees C, just by applying an electric field of 120 volt per centimeter, and the sintering happens in less than 5 seconds. So here is a real-time video of the flash sintering process. What we usually do is we deal with dog bone shape geometries. We compact the powder into dog bone shapes, and then we have holes at these ear sections. So we use platinum wires, which use as electrodes, and through the platinum wires, we hang the sample in the furnace. And then when we apply electric field, this is what happens in real time. So this is just a 3-second video, and you can see within 3 seconds the sample sinters. It densifies very fast. I'll play it one more time. Yeah.
So now this process was invented by Professor Rishi Raj at the University of Colorado, and what they did is, the first experiment, they subjected 3 wires to constant heating rate experiments at different applied electric fields. What they observed was at a critical field of something like 60 volt per centimeter, the shrinkage was like sudden. Within few seconds, the sample densified. And as they increased the field strength, the furnace temperature at which the sample was sintering, that decreased further. So now when you compare flash sintering with other conventional and other sintering techniques, like hot press, SPS, and flash, you can see that the furnace temperatures here are very low, and the time is of the order of few seconds. So, this technique can lead to huge energy saving if you are sintering ceramics. Now, these are the 3 characteristic features of any flash sintering experiment. You would see a sudden shrinkage, that the sample will densify in few seconds. Also, you will observe a non-linear rise in the current. So, the ceramics which I'm talking about, they're actually electrically, they are insulators, but under these conditions, you can pass current through them, and the current rises non-linearly. You also see luminescence. That's what the glow we observed in the video. Of course, there's no debate whether the luminescence is of electronic type or it is just thermal luminescence. So, yeah, this is the nature of the current. The current rises non-linearly, and then it can reach, any high value. Of course, we always preset the current limit so that it doesn't cross a certain value. Now, when you compare a flash sintering with, let's say, spark plasma sintering, this is a free sintering process because we do not apply any sort of mechanical pressure onto the sample. It is a high voltage and low current process. The current which I'm talking about is something like less than 1 ampere. And what typically is passed during SPS, I think, is of the order of sometimes hundreds of amperes. Next thing is all the current passes through the sample, so we can quantify, which is a problem in sometimes in SPS, like how much current passes through the die and how much current really passes through the sample. And the setup as such is very simple. We just need a power supply, a furnace, and of course you need an ammeter to measure the current flowing through the circuit, and a camera to measure the real-time shrinkage of the sample. Now, during flash sintering, what we typically do is we apply a constant electric field across the sample in the first step, and we leave the current free because you cannot control both the current and the voltage at the same time. And then the current rises non-linearly. The current reaches a limit what we set, and the moment the current reaches that limit, the power supply switches from constant voltage to constant current. So up to this point, a constant voltage is applied across the sample, the current is left free, and once the current reaches the limit, we leave the voltage free and a constant current passes through the sample. And we usually calculate how much is the power dissipated in the sample by taking the product of the voltage and the current. We normalize that with respect to the volume of the sample, and we always express the power in terms of power density. That is how much power is dissipated per unit volume of the sample. So as I told you, it's a simple process as such because we have only 2 process variable parameters. One is the electric field, and the second one is the current density. The electric field controls the temperature at which the sample will sinter. So if you apply very strong electric fields, you can decrease the furnace temperature at which your sample will sinter. So if you have a very powerful power supply, you can lower the furnace temperature to a great extent. And the current density is something which controls the extent of densification. So typically, higher is the current, you get more densification. In zirconia ceramics, what we have seen is at a current density of something like 100 milliamp per millimeter square, you get very good density. Beyond this, we observe some grain growth in the samples. Now, this is Arrhenius plot of the power density, and this is something which is we don't understand. So here, if you look at a variety of materials which have been flash sintered, all the materials that dissipate the same level of power at the onset of flash. What I mean by onset of flash is the point where the current starts to rise non-linearly. And at that point, if you look at the materials which I'm talking about like cobalt manganese oxide, which is a semiconductor, and then we have alumina, which is a MgO doped alumina, which is sort of an insulator. So they all dissipate the same level of power in a narrow range. At the sinter at different furnace temperatures with different applied electric fields. So this is something which gives us an indication that there is definitely Joule heating, but why exactly in this range is something which is not clear. We carried out flash sintering work on 3 mole % ultra-stabilized zirconia. We looked at the microstructure, and this is what we got in the microstructure. We got a narrow, sorry, we got a narrow grain size distribution, and the microstructure was fairly homogeneous at different locations of the dog bone shaped sample. Of course, this is not always the case with all the materials. Sometimes we do get heterogeneous microstructures. Now, when you pass current through the sample, there's definitely Joule heating. There's a lot of resistive heating because these ceramics are having very high resistance. And there is a lot of debate in the literature, what is the real sample temperature when you pass a lot of current through the sample. So we measured the current, we measured the temperature of the sample through in situ X-ray diffraction experiments. So we did the X-ray diffraction experiments at the argon photon source, and first we calibrated our sample with respect to a platinum standard. So what is the peak shift in the 111 reflection of platinum that we measured, and then we applied a small sliver of platinum on our sample during the flash experiment or just before the flash experiment. And we measured the displacement or the shift in the platinum peak, and from that we estimated the sample temperature in the state of flash. So the temperature came out to be something like 1370 degrees C. We also estimated the sample temperature by black body radiation equation, and that gave us a value of like 1361, so quite close. And we also measured the sample temperature by laser pyrometer, which is around 1250. But this temperature is the surface temperature. So the surface may be something like 100 degrees colder than the core sample temperature. The furnace was at 900 degrees C. Yeah, this is the equation for calculating the temperature by black body radiation equation, which is basically the temperature depends on how much power is dissipated in the sample. Another thing is, when we look at the luminescence during flash, when you pass different amount of current, the luminescence spectra showed us that the peak position does not change with the amount of current. So as you increase the current, the sample temperature is rising. I'm talking about something like 1000 degrees C to something here which is 1500 degrees C. And there's no shift in the peak position. So that again gave us one indication that this may not be really black body radiation. There could be something else other than that. Then, yeah, one thing I forgot to mention earlier, that even the dense sample, they exhibit the flash phenomena. For example, even if you take a dense sample, it will show you two effects. It will show you the non-linear rise in the current, and it will also show you luminescence. It will not sinter because it's already dense. So we measured the atomic displacement by looking at the total scattering at Brookhaven National Lab, and the main result from that work was when we subjected TiO2, a dense TiO2, conventionally sintered TiO2 sample, to on-off flash experiment. That is, we flash it, we turn off the flash. That means we apply the electric field, hold the sample in the state of flash for about 100 seconds, and then turn it off. So we measured the atomic displacement of oxygen and titanium. The interesting thing was the displacement of oxygen atoms was far greater than what you would expect from the thermal conditions. So for example, if the sample is at a temperature of 1500, you would expect the oxygen displacement to be in this range. And for titanium, it is in this range. But the displacement of oxygen was far greater than that. So this gave us one indication that maybe the displacements are far high in the state of flash. Of course, if both titanium and oxygen atoms are displaced by this much extent, this would actually melt the sample. But it's the titanium atoms which hold the crystal because they do not displace from their positions much, whereas the displacement in oxygen was huge. Then we just started looking at the mechanical properties of flash sintered sample and then compared them with the conventionally sintered sample. So the results are quite promising. Sorry. So the average Wicker hardness of the flash sintered sample, we got around 13 GPa, and that of the conventionally sintered sample was 13.7, so not very bad. Interestingly, the indentation fracture toughness was slightly better than the conventionally sintered sample. So we do not really compromise much on the mechanical properties when you compare flash sintering and conventional sintering. Now this is something which we started working recently. we wanted to actually flash spinel, and we could not flash it with the power supply we had. Actually, it requires very huge power. So we started with the powders of alumina and magnesia, and during flash, what we observed is this phase reaction happened very quickly. At the same time, the sample also sintered. When we tried to sinter, or when we tried to flash sinter Mg-Al2O4, we had no success. And then when we added small amount of zirconia, just 20 volume %, we could not flash sinter, but then at 30 volume %, the sample flash sintered. And then this reaction actually happened during flash sintering. So during flash sintering, now the single phase is formed, the spinel is formed. At the same time, it also underwent gasification. So sintering and phase reaction happen basically together. So this study we carried out at the synchronous source to capture in real time what happens during reaction and sintering. So we observed that when you take this powder mixture of alumina and MgO, the spinel is formed something at point number 4, which is somewhere over here. So within 20 seconds, you could see a peak from spinel coming up. The alumina and magnesia peak disappears, and so here what is happening is both the phase reaction and the sintering happening together, and everything is happening within, let's say, 25 to 30 seconds. We estimated the sample temperature with different emissivities, and the sample temperature was in the range of 1500 degrees C in this case. So here reactive flash sintering turns out to be a one-step material processing synthesis process, where some of the phase reactions which are very sluggish in nature, you can subject it to flash to speed up the reaction. At the same time, sintering will also happen. Of course, here what really happens first, whether the reaction happens first or the sintering happens first, that is something which we need to study because the time scale is very, very small or very short here. This is the in situ XRD pattern where you can see during flash the peaks of spinel will come up and that of alumina and MgO will go down. So we wanted to see if we apply very strong electric fields across the sample, can you reduce the furnace temperature, and can you ever flash a sample at room temperature? Now in that process, we prepared some samples by conventional sintering, and then we subject them to very high electric fields. So here there is no sintering because the sample is already dense. So what we observed was, as we increased the strength of the electric field, the furnace temperature kept on decreasing, but then it reached a lower bound limit, which was falling actually in the range of Debye temperature of the material. This we also checked for TiO2. We subjected TiO2 to various electric fields, and then the temperature dropped to something like 500 Kelvin, but it did not drop further when increasing the electric field. When we increased the electric field further, the sample started to break. Recently, even in gadolinium doped ceria, the similar effect has been observed that the lowest temperature which you can flash a sample is its Debye temperature. So this gave us an indication that, yeah, this is a good system to study a lot of, because there's a lot of physics behind the Debye temperature. Our theory is that above the Debye temperature, the lattice vibration becomes non-linear, and that's the point where it's very easy to create point defects in the sample. So if you want to flash into something at room temperature, you have to check its Debye temperature as well. Now this is the last thing which I want to share with you. So we did some flash phenomena experiment. Once again, here no sintering on single crystals of rutile titania. Here also what we observed was, as we increased the electric field, the furnace temperature kept decreasing, but then a stage came where the sample started to flash, the single crystal started to flash at room temperature. We repeated this many times, and here is a video where you can see the flash in the sample in open air. So this is a TiO2 single crystal, and it has been flashed before at, let's say, high electric fields, and then it starts to conduct electricity even at room temperature. So it's behaving like a conductor at room temperature. So we feel that certainly we have changed the band gap of the material possibly. And this is happening interestingly at an electric field of 450 volt per centimeter only. So if you flash the single crystal once at 450 or let's say above it, then the second time it will flash at room temperature. So you're changing the state of the material now by flashing it once. It starts to behave like a conductor now at room temperature. Our theory is that there are a lot of point defects created in the material which are retained at room temperature, and maybe there is some charge associated with the point defects. And this charge starts to flow when you apply a strong electric field across the sample. So we measured the XRD pattern of the flashed and the pristine single crystals of TiO2, and we observed some extra peaks, minor peaks on either side of the main peak. So we believe that the defects basically cluster and they form some small second phases with a different d-spacing. That's why we get extra peaks on either side. We observed some optical discoloration of the single crystal after the flash, basically. And when we annealed the sample at 1000 degrees C, we observed cracks in the sample. At the same time, the effect was gone. The crystal did not flash at room temperature once it was annealed at 1000 degrees C. So basically, during annealing, the defects were annihilated. So our theory is that we create a lot of oxygen vacancies, which are filled once again during the annealing process. This is the IV characteristics of the single crystal, where you can observe that we get sort of a ohmic behavior in the TiO2 single crystal once it is subjected to flash. Now, this is the last thing which we are doing at my lab. So we see that there are a lot of new phases form at very high temperature, and sometimes it's difficult to retain them at room temperature. So in a try to quench the sample from high temperature to low temperature, we submerge the sample into liquid nitrogen. So here is a sample which you can see is flashing, and then once we dip into liquid nitrogen, it continues to flash. The sample is continues to pass current through it even in liquid nitrogen. Now the sample temperature is very high. We are talking about something like 1400 degrees C. The outside temperature is very low. It does not crack, it does not break, and it continues to pass current through it. So we were thinking the flash will die when we quench in liquid nitrogen, but it did not. And these samples, when we take out of liquid nitrogen, we observe good conductivity now, even in some of the ceramic systems. This is something which we are probing now. And with that, these are the conclusions. So the flash sintering is basically an energy efficient method for sending oxide ceramics because you are reducing both the furnace temperature and the time of sintering. So the technique can be adopted by industries for faster production. Of course, we still have many challenges because the moment you increase the sample size, we are having a lot of problems. The temperature involved during flash are far less than that to require the sample in few seconds. So conventionally, if you want to sinter the sample in few seconds, you should heat the sample to very high temperatures. Formation of point defects appear to be a possible mechanism other than Joule heating, but however, this needs to be proved. We need to really show that there are point defects in the sample. The promising thing is the mechanical properties of the flash sintered samples are comparable, so that's one good sign. And the lower bound temperature of flash is the Debye temperature of the material. Of course, this need to be verified in so many other systems, of course, non-oxides mainly. And flash can change the state of the material through repeated flash experiments. And with that, well, thank you for your attention.
Thanks, Devinder, for this very nice talk, which is now open for discussion. We have time for maybe 2 questions. Please.
Thank you, Professor Yadav. It was a very exciting talk. I have 2 queries. You showed mechanical Vickers hardness was 13.7 for both the methods, like conventionally as well as flash sintering method.
This was the best we got.
Yeah.
I showed you the best results only.
Yeah, thank you. I have do you have any control on the grain size when you're doing this kind of sintering process?
Yes.
And,
so The grain growth is not very much because we're talking about few seconds, and you're not giving sufficient time for the grain growth to happen. So typically in all the flash experiments, our experience is that the grain size the growth is not much. The grain size distribution is quite narrow.
Second thing, is it possible to control the grain size in order to get a transparent ceramics?
So the transparency does not depend on the grain size, it more depends on the porosity, but we have not done those studies. I think that it's very difficult to create transparent ceramic through flash.
Okay.
Yeah.
Yeah, thank you.
So one more question, please.
Yeah, very interesting work. I'm trying to understand how these electrodes are attached to green ceramic components. Is it like by sputtering of platinum something? And what happens during the shrinkage? Because there is a sudden shrinkage, whether it get detached. I'm trying to understand that when you go for a larger scale.
Okay, yeah. So we start with dog-bone shaped samples, and do you see this color difference from here and here? So this is a paint of platinum which we apply onto the sample for better electrical contact. The sintering happens primarily in the gauge section. So it's the gauge section which undergoes shrinkage. We don't observe any shrinkage in the ear section. And once the sample sinters, we cut off the ear sections, and whatever we do are with the middle section here. No, we do not observe any detachment. Of course, in some cases, we observe a sample breakage sometimes. It sinters, typically during reactive flash sintering, where we see that the reaction is also happening and the sintering also happen. But the reaction is of a type, let's say, that causes a volume expansion. And the sintering effect is try to sinter them. These two effects then compete with each other, and the sample sometimes breaks off. So there we observe sample breakage, but in pure single phase ceramic materials, we do not observe any sample breakage. We do observe some bending sometimes. And when the sample length is longer, then we have all sort of problems. So it works very well for very small size samples. Yeah.
Okay, so far we have to end up here. More questions, please, after the session, and let's thank our speaker again.
I would now request Dr. Michael Schaeffler to hand over the memento to Dr. Devendra Yadav.
Ladies and gentlemen, our next speaker comes from University of Bremen, Michaela Wilhelm, and she will giving a talk, multifunctional SiOC, ceramic for phase separation and energy conversion. Michaela is a chemist, and she is head of the group of polymer-derived ceramics at the University in Bremen, and besides of this, she is the CEO of a structured PhD program. Michaela, the stage is yours.
Michael, thank you so much for your introduction, and thank you for being here this afternoon. First of all, I would like to thank the organizers, Ravi Kumar and also Günther Moos, for inviting me. So that is a great pleasure to be here and or to be part of this amazing workshop, and had already a lot of discussions, and I think there will be some more, so thank you for that. So now I would like also to thank the extraordinary students you have, or you are. So thank you for all your support you gave to us during the weeks before and also the days we are here. Thank you so much. So before I start now to talk about PDC materials and some work, share some works with you which we did in Bremen, I would like to give you a short impression of the city of Bremen, where I'm coming from. So actually Bremen is a city in the northern parts of Germany, which is compared to the cities of India, a quite small city with 550,000 inhabitants. It's an old trading center and we have still a lot of industry there. So the historical sites you can see all over the city. So this is an example of the town hall we have. The city is situated at the river Weser, which gave some nice places to be in restaurants or bars in the summertime outside. We have also a local soccer club, which is actually important for Germans, so, but this one is not doing well. So, and we have a lot of companies producing different things in different areas. Some breweries, or just one big brewery, it's the Beck's Brewery. We produce also some chocolate, coffee, and so on. We have a big production site of the Mercedes-Benz in Bremen, and we are also producing all kinds of launching satellites and so on in Bremen, in the companies Airbus and also OHB. So last but not least, we have a community of Indian people in Bremen who just opened up a new Hindu temple. So this is actually the biggest one in the northern parts of Germany. So looking at the university, also the University of Bremen is a rather young one. We have 12 faculties, of which 5 are in the area of natural sciences and production engineering. In these areas, 19,000 students are educated and supported by 3,550 employees of the university, from which 2,300 are scientists and scholars. Yeah, with this I would like to give you a short overview of the work we are doing in the Advanced Ceramic Group at the university, which is headed by Professor Retzan. We have mainly 4 different areas. One is focusing on the development of new processes, not only for biofunctional materials, but also for porous materials in general. We are creating some nanoparticles with different functions. Some of them are also drug delivering nanoparticles or magnetic particles. And we have a third area in which mainly fiber-reinforced ceramics, not just produced, but mainly characterized in means of mechanical characterization, are done, and this up to very high temperatures, which is actually interesting for space industry as well. So the fourth area is then the area of precursor-derived ceramics. We are mainly starting from polysiloxanes, from polycarboxylanes, and also from silazanes to create some new materials. So actually what we were doing during the last years was mainly driven by using, or at first creating porous materials and then using this porosity for different kind of applications. Some methods we are using for creating spherical pores, for example, with the use of emulsions. We created also some membranes by using the phase inversion tape casting, which gave actually membranes with a very thin separation layer. And we created some structures using the freeze casting process, which can be used and were investigated for the capillary transport, which can then be used for the fuel handling in space. That was actually a part of the presentation which I wanted to talk about, but due to time restriction, I will skip it now. But when you are interested in this topic, just feel free and contact me. So one further important point is the creation of materials with different surface characteristic in means of hydrophilicity and hydrophobicity, which is actually possible in using polysiloxanes. This is an example of a membrane which shows 2 different sides. One is more hydrophobic, the other one is more hydrophilic, which can probably fulfill special tasks in some separation application. The second bigger area in which we were working for the last years is the creation of materials containing metal ions. So we created here some monolithic structures like these foam structures, some coatings or also powders, and we added different kind of metals, platinum, copper, cobalt, and some more. And these materials, or these metals, build some very small nanoparticles, as we saw already in some other presentations during the workshop. And they have been applied in different catalytic reactions, like the carbon monoxide oxidation, the methanation reaction, and also Fischer-Tropsch reaction, which is actually a quite interesting example because it requires some hydrophobic surfaces. So the third area we are working on is then the area of materials which are electron conducting due to the combination of PDCs with carbon allotropes. And here we started with some materials, or thin membranes, which we developed for the use in zinc air batteries, actually, as gas diffusion layer. So these materials showed a quite sufficient conductivity, and it was also possible to change the surface characteristic. So that was quite beneficial for this plant application. And when you mix this with metals once again, so you can use these compositions as well as electrocatalyst. Here you see a quite interesting example because it has a quite interesting structure with a lot of carbon nanotubes built due to the existence or presence of nickel in the structure. And this has been applied for the different fuel cell reactions quite successfully. So, but this is just the starting point of what I would like to talk about today. So today I would like to give you an example of how PDC materials can be applied as anode materials in microbial fuel cells. To our knowledge, it's the first time that these materials has been applied to this application, and therefore I hope you will find it interesting as well. So before I start with that, I would like to thank the funding organizations and the people who made that possible. At first, the DFG, who funded the research training group MIME-NIMA, which paid, in this case, one of the PhD students, Pedro. We had another student from Brazil. She was financed by the Brazilian funding agency. And I would like to thank also the Indigo project framework, in which we had the possibility to work together with Professor Gangrika from the IIT Kharagpur in India. So another cooperation partner, which comes into play a little bit later, is the Professor Falk Hanisch from the Helmholtz Institute in Leipzig. Professor Gangrika is actually an expert on wastewater treatment, and Falk Hanisch works with electrogenic bacteria, so he's also an expert in the area of fuel cells with microbes. Okay, so with that, I would like to give you a short introduction to microbial fuel cells for everybody who is not too familiar with that. Microbial fuel cells work with microbes that can actually convert bigger molecules to smaller molecules and give some electrons by that, transfer it to an anode material, and at the cathode side, oxygen is then reduced and the cycle is closed by that. So that means microbial fuel cells can be used for cleaning wastewater and at the same time to gain electricity and this, or energy, and this is a very nice method. So although it looks quite simple, it's actually quite complex because you're working with microbes here at in this area. So the performance of microbial fuel cells is therefore tremendously influenced by the microbial community, also by the substrate you are feeding, so the wastewater and the composition of that. You have to take into account the cell design, so it's really difficult to compare different cell designs with each other. So, and first point is that the material selection can also influence the efficiency. So, and looking now at electrode materials that can be used for microbial fuel cells, we have to look at the requirements, and one really big requirement is, of course, the biocompatibility of the bacteria. of course, the conductivity, the porosity, the surface area, all that plays a role. And looking at the surfaces, we have to consider, of course, the surface chemistry, which can play a role here. The topography of the surfaces, how rough are the surfaces to accommodate the microorganism, and also the 3D structure and the porous structure. Are the pores big enough to transport the needed nutrients and food for the bacteria? So commonly used materials are carbon materials, actually like carbon felt or carbon rods. And these materials are of low cost, as you know, and they are sufficiently conductive, but sometimes they have the limitation that the surfaces are too hydrophobic, and or that some of the action sites which are actually used or needed for the accommodation of bacteria are not there. And therefore, and knowing that PDC materials can be adjusted to different needs and means of porosity and also surface characteristic, we thought that would be a good starting point to analyze the usage and the application of PDC materials in this area. So what we did was we started from a mixture of polysiloxane precursor. We add some additives to prevent shrinkage, and but the most important thing is we added some conductive phases. And here we added different phases like graphite or carbon black. We also added some metal ions or some metal grids, just to have a comparison between all these materials. So after mixing, these materials have been cross-linked, tape cast, and then pyrolyzed at temperatures between 500 and 1,500 degrees. So what we got, that is just an impression of the macrostructure here. For most of the material we created is a structure with macropores in the size of 0.5 to 40 micrometers, which are actually suitable to accommodate most of the bacteria, which are in the range of 0.5 to 5 micrometer, and that having open porosities between 30 to 60%. And additionally, we found some specific surface areas of up to 260 square meters for materials which were pyrolyzed at lower temperatures, and slightly lower specific surface areas for material pyrolyzed at higher temperatures compared to the carbon felt, which has actually a quite low specific surface area. When we now look at the influence of the pyrolysis temperature on the surface characteristic, it can easily be seen that the water contact angle decreases from 120 degrees C after pyrolysis at 500 degrees C to very small values and to a hydrophilic surface when pyrolyzed at higher temperatures. So on the electrical conductivity, the pyrolysis temperature has also an influence. We heard that already, so it can be seen here as well. These materials are without any additional carbon filler. These materials are of the same composition, but then with increasing temperature, you increase the conductivity up to a value of 0.2 Siemens per centimeter, and this is comparable actually already to the activity of the carbon felt. When you add some further metal ions, cobalt or nickel ions, so you can increase the conductivity further. So, but looking now at the biofilm development, the pyrolysis did obviously not play an important role, so the biofilm formation is not influenced, but only for materials with metals, we saw a slightly decrease in the development of the biofilm, which is probably due to leaching of the metal ions, which are then toxic, probably for the bacteria. So with that, we started the application of these anode materials in microbial fuel cells, and we did that in two ways. On the campus of the IIT Kharagpur, they used an aqueous cathode Claire clayware-based MFC, where the anode was placed in the middle of a clear clayware MFC and was there measured. As a synthetic wastewater, we used sucrose here, and as inoculum, an anaerobic sludge, which is actually obtained from the wastewater treatment plant on the campus of IIT, which is a huge community of different bacteria. So that was the drawback, but it was a first trial to see how these materials are performing in an MFC. The second way was then the 3-electrode setup, which is used in the labs of Professor Harnisch. Here we use this wastewater sodium acetate, and as inoculum, a Geobacter bacteria, which is actually just one bacterium and known as, for its very electroactive behavior in such reactions. So that was much more focused on really getting a picture of the performance of the material. So we investigated different materials here. These materials were all pyrolyzed at 1000 degrees C and just showed different carbon fillers. And these materials were the same materials actually, and we added one pyrolyzed at just 500 degrees C. So at first I would like to show you the results from the cathode clayware-based MFC, and I would like to focus on this diagram here where we can see the power density, and actually the red curve is the performance of the carbon felt, and we can see that PDC material, especially the one with graphite and carbon black together, showed a better performance than the carbon felt in this setup, and the material which actually contains metal ions was again less performing actually. So and when we look at some of these properties of the material, the conductivity of the material were more or less in the same range. The difference is that the carbon felt, was much more hydrophobic, and that the best performing material showed a rather high specific surface area here. So when we now look at the results of the 3-electrode setup, we find the best performing material from the investigation before. Again, here on the top, that means it performs best. And the material which was pyrolyzed at just 500 degrees C was the one with the lowest performance, and that, although the specific surface area was the highest here, so that means here the lower conductivity came into play and led to this result at the end. So that means hydrophilicity of the, and actually this material was hydrophobic as well, so that hydrophilicity, that was our conclusion from that, plays obviously quite a big role in the decision if the adhesion of the biofilm on the surface is good and the transfer of the electrons can be arranged for the material. So since this material, or our materials, are in the range of carbon felt materials, obviously, and are also, although there are some other materials which are perform much better, which are actually platinum-based materials, which are quite expensive as well. So it is a compromise, like always, right? So but still, we have had the impression that some of the performance is probably decreased because of pore clogging, and to investigate this, we tried to create some more materials which are made of the same composition, but showed a different, due to the methodology we used for the creation, showed a different pore size distribution. So one material which we created was made by freeze casting. So compared to the tape casted material, we see a slightly bigger pore size here. And the other one was then created by 3D printing of the composition. The pore sizes observed by mercury intrusion is the same actually, but we have this kind of bigger pores due to the structuring of the material by 3D printing. So and when we investigate these materials now with the same 3-electrode setup, we could find that actually the current density of the material, which was 3D printed, is now the best. All the others are in the same range. What gave us the explanation for probably the fact that the biofilm actually could grow very easily on this material, and the transport limitation could also be decreased so that the performance of this material was at the end a bit better than the other materials. Yeah, with this, I'm already at the end of my presentation, and I hope I could give you a little bit of some ideas of how these materials could be applied also for new applications. Here, the hydrophilicity of the material plays an interesting role and is needed for a good performance of the material in MFCs. Furthermore, we could show that the overstructure by using 3D printing, for example, would also be of benefit. And additionally to that, we did some investigation also with some materials which were created in a similar way just by adding metal ions, and that have been applied as electrocatalysts also in microbial fuel cells. And additionally, we created some porous materials which could be used as proton-conducting membranes in these microbial fuel cells as well. So that means we have a lot of possibilities here to create a different and adjusted material for this purpose. So with that, I would like to thank once again the funding agencies and all the persons who were involved in this project. This is actually a picture of our research training group when we had a special meeting at the Baltic Sea, actually. And this is one picture. With that, I would like to close now of the drop tower on the Bremer campus. So this is a facility where you can do some experiments under low gravity. When this would be interesting for you, this could be a solution probably for some of your questions as well. So with that, I would like to thank you for your attention.
Thanks a lot, Michaela, for this very nice and interesting talk, which is now open for maybe 0.8 questions, please.
So you have seen that we have seen that the macro bore is very important for your work. But what about microporosity? It make any influence in the efficiency of the electrolysis?
Of the
microporosity or mesoporosity in the material, because this is the main contribution to the surface area. But you mostly focus in the macro pores.
Yeah, so this is a good question, but it's quite easy to answer because microporosity and mesoporosity is actually not available for the microbes. So we need sizes at least. So when you want to have the ingrowth of the biofilm in the pores, and actually the usage of the inner structure, so the pore sizes should be at least 0.5 micrometer.
Okay, but what about diffusion of the produced hydrogen? It needs micropores also, or mesopores. They could contribute the diffusion of the produced hydrogen in this case.
The produced hydrogen?
Like after the electrolysis. After the electrolysis of, you produce hydrogen, right?
Actually, no. So they, hydrogen atoms, not atoms, right? Ions, right?
Yeah.
So and they should diffuse outside, you mean? Yeah. So but they are produced on the surface. There where actually the electron transfer is occurring. Yeah.
Thank you.
Okay, thanks. These were 1.2 questions. Let's thank our speaker again.
I would now request Dr. Michael Schaeffler to present the memento to Dr. Michaela Williams.
Ladies and gentlemen, I may announce our last speaker for the day, the last speaker also for our PDC workshop here in Chennai. Let's welcome Yuji Iwamoto. He is professor at Nagoya Institute of Technology and holds a PhD from Tokyo University. He is engaged in a large field of ceramic materials, among this also polymer-derived ceramics. And right now he is also vice president of the Nagoya Institute of Science and Technology. Yuji, this is yours.
Thank you. Thank you very much for kind attention. And first of all, I would like to thank Dr. Ravi and Günther for inviting me to this nice workshop, and I'm very much honored to be here. Yeah, this is my first trip to India, and so quite exciting. So today I'd like to talk about my research activity at NITEC, Nagoya, Japan. Oops. What? Which one? Okay, yeah. How can I form? Oh. Yes, and I would like to do forward. Yeah. Okay, good. Yeah. First, I'd like to make some short introduction to Nagoya. Nagoya is located just in between Tokyo and Osaka. Not so big city compared with Tokyo, but may be famous for the headquarters of Toyota Automobile Company. And our university was first established in 1905, and first we invented the motor car just before Toyota Automobile Company started to sell the car. And also there's some laboratory or engine laboratory, oldest one in Japan. And now we have some, developed some new facilities and so on, and not so long history, but we are working with. Yep, and within especially the PDC community, I have several collaboration research work with Jude Darmstadt, and also increase at the time, Alex over there, and also Ravi, and so on, and my dear Günther, and also the Michael Schäfer over there, and Aldo FAU, and Gian Domenico throughout at Trento, and Clemson and Brody. And we have started working with Ravi at IIT MADRAS, and recently we have some big project with the ILC-RCNRS, and yes, and recently we had started a nice project funded by CNRS, the international research program from 2019 to 2023, and working hard with Dr. Samuel Bernard sitting over there. And so today I would like to show some research activity together with him. Okay. And also to show some of our collaboration activity, we also published such kind of book chapters together with Günther and Samuel and so on, and if we can share some interest property of the polymer ceramics and so on. Yes, and at my laboratory, we are also working with several types of polymer-derived materials, including organic inorganic hybrid materials and amorphous membranes for gas separation, and some nanocomposite system for precursor materials, so on. And recently, we are very much interested in the application to the clean energies. Especially, we are focused on some kind of artificial photosynthesis system, and I briefly mentioned about this system. And we are also interested in the water splitting by photocatalyst to get to the green hydrogen. I mean, CO2 emission free. And especially if we use this kind of green hydrogen, we can produce nice electricity without CO2 emission. And of course, if we can capture the CO2 and if we can convert by halogenation to produce sustainable hydrocarbon fuel cells, we can, control the amount of CO2 emission, and this is certain kind of CCUS activity and so on. So if we can develop such kind of functional materials to contribute to develop such kind of systems, it will be good for our future. And this is a recent research work, summary of our research work concerning some CO2 as a solvent or the hydrogen separation membrane for solar hydrogen, or also some catalytic hydrogenation catalysts and so on. Today, I will focus on some hydrogen separation membrane and CO2 affinity materials. Okay. First, I would like to talk about the hydrogen separation membrane for solar hydrogen. So this is a well-known figure for the hydrogen production via water splitting. And maybe one drawback may be the co-production of hydrogen and oxygen. It's quite too dangerous. They can explode at a wide range of concentration. So the immediate separation is necessary. And yeah, of course, there are several technologies for the hydrogen purification, like cryogenic separation or PSC and so on. But if we would like to avoid explanation, so anyway, the immediate separation and simple separation technology is necessary and suggested as a membrane separation. And yeah, this is a brief summary of the, technology of the current membranes. Metal membranes and polymer membranes or some microporous silica-based membranes. But there are several drawbacks to apply for the solar hydrogen production step. As you can see, some the problem of the second reaction or swelling mechanism or some, degradation of the high hydrophilicity of the silica-based material and so on. Okay. And our idea is to apply some superhydrophobic PCS-derived membranes. Yeah, this is the relation between the water vapor pressure and the amount of hydrogen, so the isotherm absorption of the water vapor. Compared with, compared with gamma alumina or the silica, this is the typical materials for the membrane systems for ceramic membranes, and you can see that to the PCS-derived SiCH organic inert hybrid shows a superhydrophobicity like this. And we briefly fabricate such kind of inorganic hybrid membrane on the porous membrane. It's the alpha alumina support modified with gamma alumina, mesoporous gamma alumina like this. Yeah. And thickness is around about 50 nanometers. Yes, this is the typical Arrhenius plot of the gas permeances through the membrane. As you can see, this is well fitted to the straight line, so the activated diffusion like this. But the interesting point is that compared with the kinetic diameter of gas molecules, you know that the kinetic diameter of hydrogen is larger than the helium, but the hydrogen permeance is always higher than that of helium. So this shows that this membrane shows some hydrogen affinity or the preferential hydrogen permeation through this membrane. This is quite interesting point. And yeah, after we studied a lot about the permeability set, we found that this hydrogen permeation can be governed by the solid state diffusion through the porous, not non-porous, but dense membrane. Yeah, then we briefly fitted to the theoretical analysis for the calculation and so on. And for example, if we fit it using this theoretical equation, there are many, many parameters, but the important point is some vibration frequency or the activation energy for preparation or a number of sorbidity site for per area and so on. And we succeeded in the nice fitting like that for the hydrogen or helium and so on. And we also fitted some parameters just follow this theoretical solid state diffusion model. And the conclusion is that anyway, the activation energy for hydrogen is just a little bit smaller than that of helium. So this means that this membrane shows some preferential hydrogen permeation. And one idea is that it's technical issues, and it's very difficult to fabricate defect-free, such kind of defect-free membrane easily on the polar support. But if we combine the double layer composed of superhydrophobic SiCH membrane on the highly hydrophilic mesoporous gamma alumina, in this case, only the nitrogen and the water vapor can permeate through such kind of defect. But the interesting point is that the water vapor can be easily trapped within the gamma aluminum porous layer, and then this will be blocked by the water vapor. And so the nitrogen will no chance to permeate through. This is one idea. Yeah, this is the some kind of model gas, mixed gas with hydrogen and nitrogen with a molar ratio of 2:1. This is the, yeah, because we try to test the oxygen, it's very dangerous with this kind of mixture. And the interesting point is that at the saturated humidity at 50 degrees C, you can see that the permeance of nitrogen is below the detection limit. I mean that only the hydrogen can permeate through the solid state diffusion model, and this defect can be successfully blocked with a high partial pressure of water vapor. So that now we are trying to apply this membrane for the purification of solar hydrogen in Japan. Okay, so maybe I have to a little bit skip it, hurry up. Okay, so next I will talk about some polymer-derived materials with hydrogen affinity, which can be applied for some hydrogen storage or the catalyst for hydrogenation reaction. Okay, and I will today focus on the aluminum-doped silicon nitride materials. Okay. Yeah. So we together with Samuel, we studied on some how to say the interesting point of the use of the polymer-derived nitride materials as a catalytic support, which shows some electron donation property together with titanium nitride and so on. And so compared with oxide system, nitrogen can have more chance to control the certain electroconductivity of the metal nanoparticle. So this is the first idea of our foundation. But another interesting point is that if we can fabricate such kind of materials without noble metals or transition metal element. Yeah, so I will talk about this aluminum-doped silicon nitride system. Okay, yeah. So this is some kind of background for maybe students. And yeah, I will first talk about the D-block element. This element can activate small gas molecule like the interaction between the hydrogen, in this case for the donation and back donation of the electron like this. This can activate to the small gas molecule like this. Yeah. So, but in the case of main group element, generally we can identify it as some acid-base character, only the donation of 2 electrons like this. So this is the end of the some elect formation, acid-base catalyst. But the interesting idea is such kind of frustrated-Lewis acid pair. Yeah, this is quite interesting because the strict hindrance, they will lose the chance to be the formation of educt. So they can keep the space like this. And so if we can apply the hydrogen can be activated dipole interaction, then to be some cleavage of calcite like this. So this is quite interesting. And also another report is the calculation for the 2D aluminum nitride. So in this case, in the case of 2D nanosheet, there are some vacant aluminum sites like this. Yeah. So this is also the combination of some kind of FLP pairs like this. And they can dissociate the hydrogen like this. But this is only the calculation. Not the real material, because such kind of material is quite unstable and difficult to manipulate in air. So, oops. Yeah, our idea is that anyway, we would like to keep such kind of Lewis acid pair of the part within the material. So if they are free from other material system, they will be stabilized to form crystalline aluminum nitride, like the N4 unit, like this. So, but our idea is that if we can have some other big ligand or other network, of amorphous network, maybe we can preserve such kind of weak combination of aluminum nitrogen system like this. Here? Yeah. So we tested to the hydrogen affinity of the aluminum-doped silicon aluminum nitride system like this. Yeah. Okay. So the material synthesis is quite easy. Chemical modification of commercially available polysilazanes using the aluminum monomer element like ADMA, like this. Yeah. And after pyrolysis in ammonia, we can get a nice X-ray amorphous aluminum-doped silicon nitride system. Yeah. Yeah, like this. This is a well-known material system. So then we tested some hydrogen TPD profile. I mean that after exposure to hydrogen at 150 degrees C for 5 minutes, then we apply the TPD profile. And you can see that only the aluminum silicon nitrogen system can show the nice hydrogen release of the peak like this. Yeah. And of course, because of the high temperatures, there's no such kind of peak for the silicon nitride or zeolite or aluminum crystalline materials like this. Yes, and so we also tested the temperature defense of the hydrogen uptake, and yeah, we confirmed that with increasing the temperature, the amount of release of hydrogen increases like this. So it's a sign of the chemsorption of hydrogen. And also, according to our redhead analysis, we can calculate the activation energy for the hydrogen diffusion, hydrogen desorption as 44 kilojoule per mole. So this is quite high, enough to treat as the chemsorption of hydrogen. Yeah. Then we carefully check the local structure analysis before and after hydrogen exposure and so on. And we found that when we exposure to the hydrogen at 100 degrees C, the typical signal shift, sorry. Yep. Typical increase in the peak shift of the fiber coordination like this. But after desorption, this peak intensity decreases like that. So this means that because other peak position never changed and so on. So it means that the active hydrogen adsorption site couldn't see by FTI NMR spectroscopic analysis. So we conclude that it's a highly distorted part of the materials, and we propose such kind of pseudo-ternary coordination of the aluminum nitride within the silicon aluminum nitride system like this. Yep. And probably hydrogen can absorb onto the aluminum nitrogen bond using the D orbital like this. Okay. And after that, we also tested some possibility of the hydrogenation reaction on this material. So after exposure to hydrogen, we also applied the CO2. And we found that after reaction completed, we got a nice CO2 TPD peak at higher temperature range like this. This is quite different from the CO2 of the physically solved CO2 like this. So it's a sign of the decomposition of formate over formic acid formed in situ by the hydrogenation of the CO2 like this. So we are carefully checking some kind of reaction, and one key factor may be the dipole-dipole interaction like this. and they will give a chance to the hydrogenation of CO2 to afford formate or a formic acid like this. Then decomposition of the formate to release the CO2 occurs around about 400 to 600 degrees C like this. So this is a brief data for this material, but our interest is anyway that try to increase the capacity of hydrogen adsorption, and also they enhance such kind of catalytic performance of the CO2 hydrogenation to increase the polarity of these bonds, right? These bonds like this. Okay. Yep. So today, anyway, I would like to briefly show our research activity. And yeah, today I talk about some application to the clean energy application. But we are also working with some nanocomposite system, and also extend this work to fabricate some europium-doped cyanide-based phosphates like this. So also PHPS or polysilazanes is quite useful for the silicon nitride-based ceramics. So that if this polymer can be modified with aluminum species and europium species, we can fabricate a nice single-source precursor for the europium-doped cyanide ceramics, and successfully fabricated like the polycrystalline materials with green emission like this. Okay. We carefully check the distribution of the europium, and this is the same, and we found that they must be located within the 6-member ring of the cyanide structure ring, and this is quite normal, but we found that we have some advantage to increase the amount of europium within such kind of position compared with the sample fabricated by powder metallurgy route and so on. Yeah. So I think PDC route is quite powerful to invest to fabricate not only amorphous materials but to the organic inorganic materials and polycrystalline ceramics with the exact control of microstructure or the some molecular structure of the materials to enhance or to get the new functionality and so on. Yep. Finally, I would like to thank the funding agencies, and especially, I and Samuel would like to thank CNRS for the support through the IRLP project, and also my colleagues at NITEC. And finally, thank you for your kind attention. Thank you.
Thanks, Yuji, for this very nice talk. We have time for a couple of questions. The talk is open for discussion. Any questions? Sanji.
Yeah, very nice talk, and I was really impressed with the how you are modulating the Lewis acidity and basicity of the aluminum. But is it like proven that your hydrogen molecule is attached to the aluminum and not interacting with the nitrogen dipoles? Because I think the higher electron, you showed the aluminum NMR, that can also, the broadening can come from just the loose interaction, right? So.
Yeah, so according to the activity, reactivity, we also, how to say, test with some species, not only the hydrogen and so on, and we found that very reactive, So honestly speaking, this is very reactive and difficult to manipulate and so on. So now we are, how to say, studying with other systems to stabilize the material system enough reactivity to our hydrogen and so on. Yeah, we have to control the reactivity.
Because I think aluminum hydride has a very characteristic peak in infrared. That might be a very, and if you use deuterated system, then also you will see it's more conclusive than aluminum NMR. I would personally say that.
I see. So, I see. I agree with your suggestion and so on. So that honestly speaking, we are working with other systems to control the stability and the reactivity and so on.
Right. Thank you. And a very quick second question on, I mean, this is a molecular adsorption process.
Yes.
So if you look for long-term application, people have done work on metal organic frameworks for hydrogen storage. So how do you see in terms of the amount of hydrogen that's absorbed? Do you, I mean, in terms of scaling it up?
Yeah, honestly speaking, the amount of hydrogen is quite limited in this case because of the limitation of the active site within the material. So so ideally, such kind of 2D aluminum nitride must be the highest one. But it's difficult to manipulate. I mean, it's a very unstable one. So again, we have to combine some combination of the stabilized part and active site and so on. But another idea is that if we can, control some nanospace to preserve the hydrogen gas and so on, this may be interesting.
Right, so porosity could be one, yeah.
Right.
Thank you, thank you.
Thank you very much, thank you.
So, last question.
Yeah, first of all, thank you, Professor. I think started from the very basic, dipole moment, back donation, sigma bond, pi bond, then I think you have started with the basic of chemistry and reached to the PDC, right?
Yeah.
Wonderful presentation. I appreciate that.
Thank you very much.
Just one basic question from Sanjay, whatever he's discussed. No? What is the, you think, what should be the pressure of hydrogen if we need to use it for any application? What is the standard in Japan?
Okay, it's a big question for me. And anyway, we would like to serve the electric power as like the fuel cell using hydrogen. And also, you know, the Toyota Automobile company developed the FC hybrid system. So in this case, we use hydrogen as an energy carrier directly to the automobile. But according to my recognition, it's not so efficient. So maybe the hydrogen gas station may be not so, convenient for our future life. But anyway, in industry, compared with other fuel cells, we can store the hydrogen. And especially you mean some kind of SDGs. Anyways, we have to decrease the amount of CO2 emission at the certain faculty and so on. So in such a case, within the faculty system, we can collect the hydrogen and convert the CO2 to hydrocarbon and so on and so on. This may be realistic to reduce the total amount of CO2 as a transient state of our industry and so on. So in such a case, maybe we need such kind of technology of the solid hydrogen adsorbent to collect the hydrogen or to store the hydrogen and so on. So this is a new idea, and also to reduce the amount of CO2 emission anyway, it will be good or something new technology to develop to reduce the CO2 emission. This is our idea.
Okay, let's move away from the standard pressure of hydrogen in Japan, which is 0.0 megapascals, also in Germany at ambient temperature. And let's thank our speaker again.
Thank you. Thank you.
I would now request Dr. Michael Schaeffler to present the memento to Dr. Yuji Iwamoto.
Thank you very much. Thank you.
One more.
Thank you. Thank you again.
I would now request Professor Ravi Kumar to present the memento to Dr. Michael Schaeffler.
Thank you for kind help. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you.
I would now like to hand over the session to Professor Ravi Kumar.
We have come to the end of the Indo-German workshop. We were supposed to complete at 4:55. We are 10 minutes delayed. But otherwise, I think we are more or less on time. Thank you very much for attending all the lectures. Before we conclude, I request for a group photo once again. I think Samuel and Oliver will be leaving very soon, so it's better to take a photograph once and then we conclude in the next 10 minutes. So please hold on, come for the group photo, please. And thanks, Yuji, you just landed from Japan, and then straight away came to the hall to give your lecture. Thank you so much for your,
Projector.
Are you gone?
Boarding passes and an important announcement. I request all the speakers to hand over their boarding passes at the registration desk. Otherwise, it will be difficult for us to reimburse your travel fare. Yeah. And the fee receipts can be collected from the registration desk itself. One more announcement. Yeah. No, it's not.
Yeah, good evening once again. So I think we are at the end of the program. We are closing the session. May I now request Dr. Motz to come so that we summarize the outcomes of the IGSTC workshop, and then we conclude. And of course, we have to thank a lot of people. I think we have done the thanking ceremony yesterday, but let me thank everybody once again for coming to this workshop. Thanks to IGSTC for sponsoring this event. Thanks to Carbide Universal for being the gold sponsor. And thanks to Netch and as well as Bruker for co-sponsoring the event. We also thank the Institute for allowing us to use the facilities. We thank the Taramani Guest House for accommodating nearly 40 to 45 people on campus. We thank the industrial consultancy and sponsored research for allowing us to use this hall. I would like to thank Dean ICSR for helping this and making this possible. I would like to thank the photographers and videographers who have done an amazing job continuously covering the last 3 days. I would also like to thank the Ministry of External Affairs. The ministry made extraordinary effort in getting the visas quite fast. So I would like of Education, Government of India. Thanks to the consulates in Germany, France, and Japan for again issuing visas on time. Otherwise, it would not have been possible for the foreign visitors to come. Again, thanks to everybody. Thanks to the Raintree hotel staff who brought some excellent food. I assume and I hope the food was not that too bad, and I hope you enjoyed eating Indian food. We tried to also provide you some continental food as well so that you don't really get bored. So I think overall it was an excellent interaction, scientific interaction. So thanks to everybody, and we will thank all the volunteers once again later, but I would like to now call upon Günther Motz to take over. Yeah.
Yeah, one task of this workshop is also what IGSTC required is that the attendees should be asked what was the feeling about this workshop, what do they think, what was very good, what should be improved, what other expectations are fulfilled or not. And if there are already some plans for the future to work together between Indian institutions and German institutions, and therefore it would be nice if some attendees would give some recommendations or some summaries. Is there someone who would like to start?
Yeah, first of all, thank you very much. I think special thanks goes to Professor Ravi Kumar and Gunter, you for arranging the excellent workshop. I think we are all actually taken all the care, and thank you so much. Just for, I think the pillar was, I could see that there are 3 pillars for this workshop. One is energy, one is environment, one is aerospace, right? What I feel that yesterday we had a discussion also, whether the PDC, what is the use we can think of, right? PDC we may think of it when we cannot use as a bulk application. PDC by pyrolysis, then crystallization, we don't see that it can be used for a bulk application, right? And any industry will do what customer wants. So I think there will be the best way to move through if PDC can be useful for a functional application. I think today we have few talk regarding that. Maybe the energy or functional application can be the use for PDC. Control porosity, separation, gas separation, fluid separation, anything, right? I think that is the thing, maybe the way we move forward. It is quite incidental, actually. My PhD was sponsored by ISRO, and my topic was sintering of silicon carbide with pre-ceramic polymer and inorganic sintering aids. So pre-ceramic polymer is coming from that time, but I'm sure that today it has been much more matured. I think nearly a lot of inquiries coming up. We are also talking to Professor Ravi Kumar and his team for getting the pre-ceramic polymer suspension for certain application. But I think that functional application is the way to move forward. Functional application, control porosity, gas separation, fluid separation, whatever, right? I think that is the thing we should move forward. I think that is the opportunity for PDC going forward.
Okay.
Thank you.
Thank you very much. Is there anybody who can add some words?
So I was firstly deeply impressed by this 100% care and this excellent organization. So this is the one point. The other point, or maybe a point which belongs to this, is the food was excellent, the beer was good. But I have also realized that after Corona, the PDC community is still alive. So this is the first important point for me. I guess everybody has generated new ideas when hearing talks of others, and we are now in the situation where we can shape our ideas and can sharpen this and can actually try getting this written down to proposals for continuing our international collaboration.
Thank you, Michael.
Anybody else?
Sanjay?
Yeah, I think, first of all, I'm not sure which side I am representing, but for me, it's really a chance to connect to my own academic roots, so I'm thankful for the possibility. Besides the academic focus, which was excellent, and I think I like the idea of involving young professionals with the small or brief talks. And now you were asking in terms of continuity, and I said in my talk that somebody now has to take the baton and run further. The area is potentially very active. You can go to the next workshop, could be on functional application. What I would also suggest is looking at IIT, the biggest pleasure for me was to see these highly motivated young people. So maybe if there is a next workshop, there should be a poster session also, where we'd have more interaction. So there are two ways of, you said bilateral collaboration or multilateral. This could be by exchanging samples, but more frequently and more productively by exchanging students. So I think there are a lot of talks, which at least I had, and everyone was talking to the German host or potential host. So I think that's definitely going to come. Now, in terms of, I just wanted to say that there are two instruments, and they are known to everyone. One is the agreement between DST and DFG. So you can always have bilateral projects which can be funded. The second instrument is where the industry can come, is the 2+2 instrument, where one industry from India and an academic institution can tie up with the same constellation on the German side. That goes a long way. So if you are really looking for the progress from your PhD to now and you want to assess that, that's a chance. Like Merck coming forward and saying, okay, we tie up with an IIT, and then we have the same constellation on the German side, this works. For long term, there is the new MOU in place between the DST and DFG for international research training groups. Then obviously there are, and I think which is not so well known in India, is that India is fully eligible partner for European projects. So you get 100% funding, and in every call, it's possible. There are specifically dedicated calls for international collaboration, but even in a general call. So if there is a European call, it's always very beneficial to have Indian partners. I'm just saying from the European perspective. So I'm sure, I just wanted to say that this has always continued and this will continue. I just want to thank you, Gunther and Ravi, for putting one more milestone here. But yeah, thank you very much.
Thank you, Sanjay, for your kind words. I think also that this workshop contributes to make the cooperation between India and Germany closer, and also the attendance of the industry, of younger students, of PhD students, postdocs, and so on. I think it was a good mixture to make an exchange in knowledge, but also to get an impression what the industry needs, that our research can be transferred also to industry, that it not only remains on an academic level, that also goes to the economy. And this is very important, and I hope some collaborations will result from this workshop also in the future. And maybe someone from the industry can say some words about their experience about the workshop. What do you think? Ulrich or Jürgen?
Thanks first to Ravi and to Günther for this nice workshop, for the organization, also to the team. Yes, it was quite interesting to stay here. And for me, I'm mostly focused on monolithic ceramics, but I see the potential of the functional coating. I have shown this in the presentation, and I hope and I see that this will be moving on. It takes also some time sometimes, but I'm looking forward to have more projects with this, with functional coatings, for example, and also to see some porous materials which will be in the future. Yes, this is what I can say.
Okay, thank you, Ulrich. And now I'm very interested in the thinking of the young students, maybe also from India. What do you think about this workshop? Was it helpful for you? And now you have a greater interest in Germany, or what do you think? Was it good for the intercultural exchange?
Hello. First of all, thank you everyone and for this wonderful workshop. I'm Nisar Khan from IIT Tirupati. I'm pursuing my PhD and it is my first year. So through this workshop, I see the opportunity to visit Germany, be in the form of workshop or a conference, or even visit to any research lab. So I will be looking for the opportunity to visit Germany, and thank you.
Yeah. Now, Ravi, do you have some additions or? Otherwise, I have, at the last but not least, I would like to thank again all speakers and the audience, and almost of the speakers were in time. We had sometimes a little bit delay, but this was also because of very fruitful discussions, and that can happen. It was not a problem, but all in all, it was, for me, from my side, a fantastic workshop, and especially our hosts here in India was the best I think I ever had in my life, and my scientific life is already a little bit longer. And therefore, I can value this. And the team was so good, therefore, the German team and all our Germans, and also the French team. The French team was not only French, was also half of German somewhere. Unfortunately, he is not here. And we raised some money and a gift for the students organized this workshop. I think it was a very hard work. You worked couples of weeks or months for this, and you made it to an excellent event for us, and we felt at home, or much better at home. And we would like to thank you, and it was an exhausting time for you, and to relax afterwards a little bit. I think you can use the money to organize some parties. And also some German chocolates are inside. It's not so much because our luggage is limited. Otherwise, we would bring more. But I hope you can have a very nice party, or maybe it's money for 2 parties. And you will think of us as good guests, as friendly guests. And I hope we can continue the relationship with you. For us, it was a great experience, and therefore I would like to say again thank you to you. We will come back.
We can call all the volunteers because they really worked very hard.
Yeah.
So please come to the stage because these people really worked very hard, very hard.
But I need a representative. So, to hand over.
You can. Distributors. The program ends, but the plan was to take you to the Heritage Center. The Heritage Center is just opposite to this building. You will see that once you cross the road, it's just beside the administration block. The Heritage Center was created basically to give an idea of what kind of connections that we have with Germany. So please do visit the Heritage Center. In fact, we have informed them that you will be coming there. So they have maybe artifacts and photos of the past. And you will have a nice time knowing how IIT Madras has been connected with Germany for a long time. So after you go to the Heritage Center, if you are interested, you can go to the Students Activity Center, where the classical dance program is going to start at 6:30. I mean, that's left to you. If you are interested, you can go there. The Student Activity Center, to repeat once again, it is behind the Taramani Guest House, very close to the swimming pool. So if you are keen on watching the dance program, you can go there. It's just walkable distance. You can go to the Students Activity Center to watch the dance program, which is going to start at 6:30 p.m. And we have arranged a special dinner for the speakers in Taramani Guest House. So the dinner, I think, should be ready by 7:45 at that time. In case you are going to watch the dance program, you can just walk back for the dance program and walk back to the guest house for dinner. Otherwise, the Indo-German workshop ends today. However, we have one more workshop which is starting tomorrow. You are welcome to attend that as well. But that's happening in Hall 2, which is adjacent to this room. In Hall 2, we start at 9 a.m. tomorrow. So those people who are still around in the campus can come. Of course, Gunther, we are not allowing him to go. And some of them, we are not allowing them to go. In case you have fallen in love with this place, you can still come back at 9 a.m. tomorrow to Hall 2. We have a few more lectures which are very interesting. In fact, very unconventional, I would say, lectures which you will hear tomorrow. Yeah, that's it. And I wish you come back to IIT Madras once again. And thank you so much. Yeah.